You made it all the way to the 5th course of the certificate. 4 down, 2 to go. You're almost there. You guys might remember me from earlier. I'm Phelan Vendeville, and I introduced you to software in course 1. Maybe you skipped those lessons and you're meeting me for the first time. Don't worry, I won't tell. I just wanted to share with you a little bit about me and my experience in IT. I'm a systems engineer in the Site Reliability Organization at Google. SREs create solutions to design, build, and run large-scale systems, like Gmail, scalably, reliably, and efficiently. My journey to being a systems engineer started way back in a small town in California. I grew up in a very isolated area, so in school, we relied on technology to provide us with more exposure to the world. This was critical in connecting us with ideas and opportunities that weren't available there. We took virtual field trips and learned things from remote classes, kind of like this one. After high school, I enlisted in the United States Navy as an information systems technician, responsible for maintaining computer and network systems. In that role, I did everything from helping coordinate ship movements during training exercises to connecting my fellow sailors to loved ones through video chats. From when I grew up in a small town to being away on a long deployment, the ability of technology to build connections and broaden worldviews made a big impact on me. My first job at Google was in IT support, and it was there I first learned about SRE. SRE has a great blend of software engineering and systems administration work, which really attracted me to the role. Having great coworkers helped too. I'm excited to be back to teach you a course that I really get excited about: automation. As an SRE, creating and using automation is a vital part of my job, since it would be next to impossible to run a large service like Gmail without it. But automation can have all kinds of applications outside of work too. For example, I've written scripts to reboot my Wi-Fi router automatically when it goes down, without leaving the comfort of my couch. In the last few courses, you learned about the history of computers and about how they work. You've seen how they talk to one another to form networks, and you've explored the ways they can be configured, managed, and deployed in the workplace. In this course, we'll take it one step further to examine how computers can be used to manage themselves and each other through a process called automation. As an IT support specialist, you'll probably need to install internet browser software on new users' computers. Let's say each time you do that, it takes 10 minutes. If there are 10 users, you'll spend 100 minutes just installing software. If the company you work for is growing, it'll eat up even more of your time to do what's essentially a simple job. This is when automation becomes your new best friend. By automating the manual task of installing an internet browser, you'll free up your time to tackle bigger problems. By the end of this course, you'll understand how concepts like automation and centralized monitoring can help make your IT work easier and much more efficient. In this course, we'll cover the basics of writing a program and work our way through practical exercises and industry examples. We'll also talk about how automation can be done on a larger scale, and we'll introduce you to concepts like configuration management at scale and centralized monitoring. Soon, you'll start to see how computers can perform almost anything you want them to. All you have to do is tell them what to do by writing code. Yeah, I said writing code, and yes, you're going to learn to write some code. That thought might get you really excited or feeling slightly terrified. It's okay to feel that way. I've felt that way myself. Things like scripting and automation may seem complex, and we're going to throw a lot of new terms out there, but don't worry. Our goal isn't to teach you everything there is to know about software engineering or even automation. We just want to expose you to some of the central concepts of programming and scripting, so you're empowered to spot opportunities for automation in real-world scenarios. These new skills will not only make your work easier and much more efficient, they'll also help set you apart in the IT field. Are you ready? Let's get started. So, What exactly is automation? Automation is the process of replacing a manual step with one that happens automatically. Although we may not realize it, we reap the benefits of automation every day. For example, think of a traffic light. It regulates the flow of vehicles at an intersection. A traffic light only requires human intervention when it needs repairs or maintenance. The automatic regulation of traffic means that humans don't have to stand at the intersection manually signaling whether or not the cars should proceed. Instead, people can focus their energy on more complex, creative, or difficult tasks, like focusing on where you're driving. Another great thing about traffic lights, they won't get tired, bored, or accidentally display one color of light when they really mean another. This highlights another benefit of automation, consistency. Let's face it, as humans, we're all flawed. We make mistakes. A human performing the same task hundreds of times will never be as consistent as a machine doing the same thing. But for all of its advantages, automation isn't a solution to every situation. Some tasks just aren't suited for automation because they might require a degree of creativity or flexibility that automatic systems just can't provide. For more complicated or less frequently executed tasks, creating the automation may actually be more effort or cost than the automation is worth. Let's consider the process of getting a haircut. What would it take to automate the actions of cutting hair with a machine? The height of the client, the shape of the head, the current length and style of hair, and the new desired haircut would all need to be taken into account when designing the automatic system. Extensive testing would need to be performed to ensure the safety of the client and the quality of the haircut, although this validation can be subjective. Finally, the creativity and skill of a trained specialist would need to be replicated. In this case, the cost to develop and implement the automation is probably not worth the benefits that an automatic haircut would provide, so the task remains a manual process. In this course, we'll talk about different ways you can leverage automation for your role in information technology. We'll learn about configuration management tools like Chef, which are useful for both completing tasks automatically and encoding institutional knowledge within a company. Configuration management tools provide an out-of-the-box abstraction through which you can manipulate high-level objects like machines and services. For example, you can write a Chef recipe or script to automatically provision a web server. But what if your web server depends on having a database server running SQL installed first? Or you need to provision multiple web servers at the same time, along with their corresponding databases. If you have a task that requires more granular control or isn't covered by the use cases offered by the configuration management system, the idea of custom automation using scripts comes into play. In information technology, the automation of these tasks is commonly accomplished by encoding the logic to perform the task into a program or script. Don't worry, we'll talk about both these things later on in this module. Anyway, the script is then run on a computer, which follows the directions it finds there to accomplish the task. Automation is a super powerful tool when used in the right place at the right time. It can save time, reduce errors, increase consistency, and provide a way to centralize solutions and mistakes, making them much easier to tackle and fix. But before we can dive into automation, we're going to need to talk a little bit about programming and how it ties into automation in the workplace. So what's programming? Well, at a basic level, a computer program is a recipe of instructions that are executed by a computer. The recipe is written in a code called a programming language, which is similar to human-spoken languages in a couple ways. It has a syntax, which are the rules for how it's written, and semantics, which are the meaning of the statements. I bet you didn't think that you'd get a grammar lesson in an automation course. The rules you follow when you construct a sentence in a human language are called the syntax. In English, sentences generally have both a subject and a predicate. In the next sentence, temeraire is the subject, and loves to program in Ruby is the predicate. Knowing which part is the subject and which part is the predicate won't help with the semantics of the sentence, though, as its structure is independent from what it actually means. There are over 6,500 spoken languages in the world today. There are also lots of programming languages to choose from, but not quite 6,500. Each programming language has its own history, features, and applications. But once you understand the basic concepts of programming, it becomes easier to switch between them. You might actually find it's easier to learn lots of programming languages rather than spoken languages. Since computers always do exactly what they're told to do, it's important to clearly express what you want the computer to do when writing a program. Automation in the technology industry is normally done through the implementation of programs and scripts. Some tools like Chef or Puppet provide an out-of-the-box solution to automate repetitive tasks without requiring much programming knowledge. In a situation where you need to perform a task that these tools don't support, you can create your own custom automation by using a programming language to manipulate the underlying systems. Before we move on, let's spend a moment on terminology. In the coming lessons, you'll hear the term script being used frequently in the context of automation. So what's the difference between a script and a program? The line between the two can be blurry, and in this course, we'll usually use the terms interchangeably. But you can think of scripts as programs with a short development cycle that can be created and deployed quickly. Scripts are usually written in an interpreted language and have a single or limited range of tasks to perform. You might be thinking, interpreted language, what the heck does that mean? Well, when you want to run a program written in a traditional programming language like C, the source code is fed into a piece of software called a compiler. The compiler translates this code into a machine-level language, specific to the underlying architecture of the computer on which it's running, which the computer can then read and execute directly. This makes compiled programs very fast to run, but the compilation process itself can take some time. Some examples of commonly used compiled programming languages are C++, Go, and Objective-C. On the other hand, programs written in a scripting language usually rely on an intermediary program called an interpreter to execute the instructions specified in code, rather than running them through a compiler first. This means that the development cycle for a program written in a scripting language can be faster, as the developer doesn't need to wait for the code to be compiled first in order to execute it. The trade-off is that interpreted languages generally run slower than compiled ones. Some examples of interpreted languages are Ruby, Python, JavaScript, and PowerShell. Whether you use an interpreted or compiled language, the ability to program is one of the most powerful tools in the IT support specialist toolbox, which is why we'll continue to explore this together in future lessons. In this course, we'll be focusing on a particular scripting language called Ruby, which we'll use to learn the basics of programming. But before we get too deep into learning how to code, let's talk more about why automation is so useful and what it is. Soon, you're going to be a full-fledged IT support specialist. And as an IT support specialist, thoughtfully applied automation can play an important role in your work. You can view automation as an IT force multiplier, a tool that can increase the effectiveness of an IT team without needing to increase the number of team members. Basically, automation can allow IT infrastructure to scale and keep pace with growth and demand. Scalability means that when more work is thrown at it, a system can do that work and increase its output. And that's something that everybody wants. Let's consider the information technology implications of hiring new employees. When a new employee is hired by a company, several tasks may have to be performed to provide them with access to the technology resources that they need to do their jobs. They'll probably need a user account, mailbox, and a home folder, maybe permissions to control access to various systems and resources. If only a couple employees are hired in a given period, an IT support specialist could manually execute these steps each time somebody is brought on board, although this could easily become tedious work. But as the number of new employees increases, so does the time it takes to provision the resources required for them. If your company hires 10 times its normal number of new employees in a week, you may find yourself doing nothing but what's required for new employee account setup. That's not going to make the higher-ups happy, and any projects you've been working on will need to be put on hold until the operational work of setting up accounts is completed. You might also make mistakes during the provisioning process, like misspelling a name or forgetting a step, or giving a user account the wrong permissions. These mistakes will need to be fixed, making an already overwhelming workload even worse. It's not good. If the company continues to hire at this pace, another IT support specialist might need to be assigned to pick up the work that isn't getting done, or perhaps be dedicated to performing the processes themselves. This is a practice that doesn't scale very well in terms of monetary resources, mental investment, or reliability, especially if the company continues to grow. What happens if the rate of new hires doubles, triples, or even more? Throwing more people at the problem quickly becomes impractical and expensive. Let's think about how automation could be used to improve this process. Instead of having the IT support specialist interact independently with each of the systems that create a new user, account, mailbox, shared folder, and permissions, there could be a better way. What if instead, the IT support specialist created a list of the steps and actions that needed to be taken, and then had a computer perform them each time a new employee was hired by the company? We can refer to this list of steps as a script, which we mentioned briefly in the last video. Think of the script as a series of instructions written in code to be used by a computer. When given some initial information, like the new employee's name and job function, this script could perform each step automatically, requiring human intervention only if a task failed for some reason. The computer would execute each step in the script in the given order and exactly the same way, never deviating from its instructions. We can go a step further and make the script even better. Instead of having the IT support specialist enter the new employee's name and information into the script each time it was run, the script could read that data from the company's human resources system and begin the entire workflow automatically itself on the employee's start date, which is pretty nice and easy. Do you see how in this example of using automation, we've transformed a repetitive, time-consuming task and made it faster and more reliable? We've also freed up human resources, allowing IT support specialists to focus on other work that's more appropriate to be done by a human. What might be more subtle and harder to see are the benefits of centralizing mistakes in the automation. If there's an error in the script, you can fix it there once and fix it forever, which unfortunately is not the case for mistakes made by humans. I hope the benefits of automation are becoming more clear to you now. But as we've said before, automation isn't a fix-all. Improperly executed, automation can cause as many problems as it can solve. Next, we'll examine some of the ways it can fail. Automation is super beneficial, but if it's implemented without a thoughtful design, it can have some serious drawbacks and consequences. Let's check out some of the ways automation can go wrong and what you can do to avoid them. Any task or process you decide to automate comes with a trade-off. Is the time and effort that will go into creating it worth the potential benefits that having the automation will provide? A simple and hands-on way that can help you decide is to estimate the amount of time you spend doing a given task, then multiply that by the frequency that the task is performed. If your estimate of the time it will take to automate the task is less than the time spent performing the task, it's likely a good candidate for automation. Unfortunately, the decision of whether or not to automate is usually not so straightforward. If a task is complex and performed infrequently, it may seem like automating it is more trouble than it's worth. Keep in mind that once a task is wrapped in automation, anyone can do it. A complex, error-prone task can be very useful to automate if it's critical that the task is done correctly, even though it may be executed infrequently. There are no hard and fast rules for making these choices about what to automate, but keeping in mind the trade-off in cost and time will help guide your decisions. A concept called the Pareto principle can provide a useful guideline to help you decide which tasks to automate. I've included a link to the Pareto principle in the reading right after this video. When applied to automation in IT, the Pareto principle states that 20% of the system administration tasks you perform are responsible for about 80% of your work. If you can identify and automate those 20% of tasks, you could be saving yourself a lot of time, which is what we all want at the end of the day. It can be really difficult to decide where to automate. And automation that has been implemented can be fragile. If underlying systems change and the automation isn't updated accordingly, workflows can break. Let's take another example where an automated backup system periodically saves the contents of the sales database. If the automatic backup program knows where the data it needs to save is stored based on a disk identifier like /dev/SDA1, what happens if a new disk is added to the server and the disk identifier changes to /dev/SDA2? The automation will no longer be able to access the disk it thinks it should be backing up and will fail. This process of software falling out of phase with its environment is sometimes referred to as bit rot. The actual bits of the script don't decay, but its assumptions about the implicit signals it relies on do. It's really important to consider how your automation will handle errors. Automated systems perform actions independent of human intervention, so it can be easy to set and forget them. Always remember that if the failure of an automated system goes unnoticed, the consequences can be severe. Let's revisit our backup example. If the backups begin to fail because the disk identifier has changed and no one notices, the next time the data needs to be restored, like after a crash of the sales database server, the IT support specialist responsible for the restore will be in for an unpleasant surprise. They'll discover that the automated system hasn't produced the backups they thought. False confidence in an automated system may also factor into decision-making. For example, if the sales database needs to be upgraded, systems administrators may be more willing to proceed with the potentially risky operations, since they believe that they can recover the database from backups. To reduce silent failures, you can build a method of notification into your automated systems. This way, when automation fails, a human is made aware of it and can investigate the failure. This notification method could be anything, from an email to an update on a dashboard, but its key feature is that it surfaces the error so a person can fix the automation. We'll talk more about monitoring and alerting later in this course. Even worse is if the automation succeeds but performs the wrong action. Let's go a little further. What if the backup system was correctly performing its task but was configured to back up the wrong data? A restore of incorrect sales data could result in data loss or even data corruption, where customers could get charged the incorrect amount for using products they haven't purchased, and that would be a big mess. For the more subtle class of failures where the task completes incorrectly, a periodic test to validate the behavior of your automated system could be really useful. In our backup system example, one helpful method of validation would be to schedule a regular restore of data from the sales database, then check that the restored data is the data you expected to be backed up. This testing process could also be automated, with scripts written to schedule the restore and compare the data against some master dataset. Again, if any part of the restore process were to fail, the automated system could halt to prevent further data corruption, and then send a notification to a human to investigate the problem. Along with notifying someone that there's a problem, good automation will make debugging easier by logging the actions it takes. As you saw in the System Administration and IT Infrastructure course, the system log can be a super useful source of information for an IT support specialist investigating an issue. Automation can be configured to create similar logs or even write to the system log, creating an audit trail of useful troubleshooting information, which will assist the debugging process. Automation can also be a victim of its own success. If humans don't directly interact with a system that has been automated on a regular basis, when the automation fails, the humans may have forgotten how to run the system or accomplish the task that's been handled automatically up until that point. Yikes. This type of pitfall can be avoided with regular training on the operation of the system when the automation that manages it normally has failed. Automation is an incredibly powerful tool that saves time, reduces mistakes, and facilitates growth and scalability. But it should be applied thoughtfully to avoid some of the dangers that can arise from its use. As an up-and-coming IT support specialist, keep these things in mind, and automation can be an invaluable asset in your toolbox.
SRE is about being a problem solver, right? We have to look how the products are running, how the users are interacting with them, and you don't really normally get like beep, 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 like here's where the problem is. You have to dig in I am Sabrina Farmer, and I am an engineering director in the Site Reliability organization. Site Reliability is the group of people who are responsible for running Google's products that the users interact with every day. We've been doing site reliability for more than a decade, and I think we understand the interaction of how our users go through the web and interface with that. But what's changing is, what does site reliability, what does resilience look like for users using the mobile as a platform? This is a large distributed system that our products run on. And we have to think about, how are we monitoring it? How do we know when people are having problems? How do we know when they're experiencing something and getting that signal back? I think that's a really hard problem, and it's exciting to think about this new platform and how we're thinking about reliability there. When you start in IT, that's what you're doing. You're solving problems for users. You're solving problems with the platforms that they're working on. And I think site reliability just raises the level and gives you a bigger problem to solve, but you still need to use the same skills that you did in IT.
In this lesson, we're going to be covering how to script with Ruby. We'll start by using the Ruby programming language to demonstrate the basics of scripting and automation. So, why Ruby? We chose Ruby for a few important reasons. First, programming in Ruby usually feels similar to using a natural language. Check out this line of code. Even if you've never programmed before, you might be able to guess what this code does. I'll give you a hint. Read it out loud a few times. If you guess that it prints the word noon, then you'd be right. If you didn't get it, don't worry. We're going to dive into exactly how to read and write statements like this soon. But back to Ruby. Because of the natural way Ruby code is written and its emphasis on simplicity and ease of use, Ruby is a great language to learn programming concepts in. There are other reasons that Ruby is a great choice. Ruby is a popular language in the IT industry and is usually ranked as one of the most common languages in use today. Because it's used so widely, the odds are pretty good that you'll encounter it in the workplace. You can use Ruby on any platform, as there are installation packages for Windows, Linux, and OS X. Although Ruby is the language we've chosen for this course, it's important to call out that it's not the only one out there. You should think about any given programming language as being just one of the potential tools in the IT support specialist toolbox. From traditionally platform-specific scripting languages like PowerShell for Windows and Bash for Linux, to more general-purpose scripting languages similar to Ruby like Python and Perl. There are many options available to the IT support specialist who's interested in automation. If you want, there's also a whole world of more traditionally compiled languages like C, C++, Java, and Go to explore. One nice feature of learning the basics of programming in one language is that the concepts you learn can generally be applied to other languages. This transferability means that becoming familiar with a language like Ruby will help you pick up new languages in the future, because you'll be able to spot similarities between them and understand their differences. After all, every language needs a way to do common things like create variables, control the flow of a program, read input, and display output, even though they may go about them using very different approaches. Also keep in mind that a large part of programming is learning through trial and error, and even more importantly, asking questions. If you get stuck, don't get discouraged. Making mistakes when programming is part of the process. The more you embrace the failure or broken code as a means for feedback, the easier your programming journey will become. You should also always remember that even experienced programmers may need to ask a question from a colleague or look up something on the internet. Whether you're a programming novice or have some experience in software development, it's important to learn how to overcome programming challenges by seeking help or using other resources. There's also a wealth of information on the internet about learning to program. You can find some specific programming language courses on Coursera. You'll find Ruby-specific answers in the official Ruby documentation. You can use sites like Stack Overflow to discuss and share with other developers, and you can ask questions in our Coursera class forums. You can even subscribe to a Ruby mailing list like Ruby Talk to ask questions and read about the latest updates in the language. There are all kinds of resources available to help you throughout your development lifecycle, whether you're programming for the first time or an experienced developer. I've linked to all these in the next reading. I want to call out some of the differences and similarities between various scripting languages. Let's compare a simple program that prints the words "Hello World" 10 times. We'll look at the script implemented in Ruby, Bash, and PowerShell. Do you see how each language goes about printing "Hello World" in a different way? Just like someone who speaks 3 different languages would say "Hello World" differently. Look closer at the scripts though, and you'll see some similarities too. Each language must put text on the screen somehow. Puts for Ruby, echo for Bash, and write host for PowerShell. Notice that each must also count to 10. While Ruby does this by specifying 10 dot times, Bash uses a sequence notation to count from 1 to 10. PowerShell has the most complex syntax in this example, but it also boils down to starting at 1 and counting up until 10. Hello, you. In this lesson, we're going to take a closer look at Ruby code. Now that you've got an idea of what Ruby code blocks look like, let's dive a little deeper with another example. Check out this line of code. If you were to run this code, either from a script in your terminal or from IRB, the Ruby interpreter we talked about earlier, you'd see the words "Hello World" appear on your console. This is because puts is a special method that Ruby has defined to print things to the screen, like the statement "Hello World." Methods are pieces of Ruby code that perform some kind of work. We'll come back to methods in their own video later on, but it's worth calling out that many other programming languages distinguish between methods and functions. Ruby doesn't make that distinction, and just uses the concept of a method. Since we'll be running many of the examples in this course from the Ruby interpreter, let's take a closer look at what the IRB prompt looks like. If you typed in IRB on your terminal, you'd see something like this. This might seem a little confusing at first glance, but all that it means is you're in the IRB program. You're on the first line, 001, and your current depth is 0. Don't worry, there's no need to worry about depth at this time. When you type in an expression at the IRB prompt, you'll get an immediate response, like this. You can see that "Hello World" gets printed to the screen. What's up with that weird line? That line indicates the return value of the statement. In this case, puts "Hello World" doesn't return anything, so we get nil. We'll dive into return values and nil soon. When a programmer uses a keyword or method in a script, it means that she is making use of the computer language syntax to tell the computer what to do. The methods and keywords that the Ruby language assigns special meaning to are what make up the language's syntax. Another example of a predefined method is print, which performs a similar function to puts, but with a key difference. Puts will automatically start a new line after displaying a statement on the screen, while print will continue printing output on the same line. Examples of reserved keywords include if, while, and do. We'll talk about all of these reserved keywords in videos a little further down the road. Have you noticed that the "Hello World" statement is delimited or bookended by double quotation marks? Wrapping text in quotation marks indicates that the text is considered a string, which is a programming term for a collection of text. A string is what is known in programming terminology as a data type, whether it's a script used to automatically create user accounts or a mobile game. Most programs need to manipulate some kind of data, which can come in many forms or data types. You'll find out all about data types in the next video. Feel free to get up, stretch, grab a snack, and then meet me back here for a rundown on data types. All right, let's get back into data types. A string is one type of data in Ruby. Others include integer and float, which represent integers and real numbers respectively. A real number is just a number with a fractional part, as indicated by the decimal. Generally, your computer doesn't know how to mix data types together. Adding 2 integers together makes perfect sense. But adding an integer and a string together isn't something the computer knows how to do, and will result in an error. Look, it's our first error. Don't panic though. Mistakes and errors are a normal part of the process of writing a program, and you'll probably encounter them a lot. The trick is to read them carefully, understand what they are telling you, and apply that knowledge back to your code to help you find the mistake. In this case, the first line of the error message indicates we've encountered something called a type error, followed by a bit of explanatory text which says, string can't be coerced into integer. If we take what we've learned so far about strings, integers, and mixing data types, you might be able to infer that the error is telling us we can't add the string 1 and the integer 1 together because they're different data types. But what if you didn't have an instructor like me to helpfully point that out? How would you know? Remember what we said in the last video about asking questions. Don't hesitate to use the resources available to you in order to do some investigation. For instance, you could begin looking into the error by opening up your favorite search engine and pasting the text of the type error message into the search bar. This is a common trick used by many IT support specialists. You'll usually find that other people on the internet have reported and solved similar errors. Harness that brain power to save yourself some time. Let's get back to our example. Even though it might seem like we're adding two numbers together in the previous statement, look carefully and remember that anything wrapped in quotation marks is considered to be a string in Ruby. To the computer, adding 1 plus 1 is just as strange as adding 1 plus a. It might be helpful to think about data types in terms of the information they can be used to represent. For example, the name of a file would be represented as a string data type, while the size of that file might be an integer. All right, it's quiz time. I'd say good luck, but use your resources is probably more fitting. How'd the quiz go? If you nailed it, great. If it was tough, feel free to review the video. It's all about having the persistence to keep trying until you get comfortable with the stuff. In this lesson, we're going to tackle expressions and numbers. One of the building blocks of Ruby is the expression. You've probably seen expressions before in a math class. They're combinations of numbers, symbols, and variables that, when evaluated, produce a result. You can do arithmetic in Ruby by defining expressions in a familiar way. The basic arithmetic operators, plus, minus, times, and divide, all work as you'd expect, and the general mathematical order of operations also apply. To demonstrate, we could do something like puts 1 minus 1 multiplied by 1 plus 1 in parentheses, and we get -1. Alternatively, we could write puts 1 minus 1 multiplied by 1 plus 1 with no parentheses, and we get 1. Ruby supports exponentiation using the ** operator, and an operator called modulus, which is indicated by the % symbol. It returns the remainder after dividing two numbers. For this, we can see exponentiation in practice with the double star sign. 8 to the power of 2 gives us 64. To demonstrate modulus, we can use 9 % 2, which gives us a remainder of 1. On the other hand, if we divided 9 by 3, the remainder is 0, so that's what modulus gives us. You can perform calculations on either integers or float data types, which can be negative or positive. Remember that floats are the data type that represents fractional numbers. So in our first example, we can see that we're adding 1.5 plus -0.5, which gives us 1. In our next example, we take 0.5 and add it to 0.5, which also gives us 1. But wait a second. Look closely at that third example. You'll notice we've created an expression with two different data types, integer and float. And the computer had no problem evaluating it. This seems to contradict what we said earlier about not being able to perform operations on mixed data types. So what gives? In this case, Ruby is giving us a hand by making some assumptions when evaluating the expression. The Ruby interpreter reads our code and notices we're trying to add two different kinds of data together. But it sees that the data types are in fact both numbers. It knows that if it changes these numbers to the same type, it can add them. To allow this kind of conversion, all integers have a special ability that lets the interpreter convert them to floats, and vice versa, on the fly. This means that although our code says 1.1 plus 1, the interpreter changes it to 1.1 plus 1.0, and the number 2.1 is printed on the screen instead of an error. This process is called implicit conversion because the interpreter just goes ahead and changes the data type of one of the numbers without asking us. For some data types like integer and float, the interpreter can make this decision pretty easily. For other data types, the interpreter won't be sure how to perform the conversion, like adding a string and an integer together. If we wanted those kinds of data types converted into one another, we'd need to tell the interpreter how to do it. Ruby operations aren't just restricted to numbers. You can also add strings together with the plus operator. This means you can do things like assemble sentences from individual words. Just don't forget to add spaces to the words to make them legible. Let's take a look at this example. In the first example, we're using the puts method to put the following expression onto the screen. A plus B plus C are all strings. Added together, they give us ABC. In our second example, we can see that we're doing pretty much the same thing, except this time we're adding spaces after each word, then adding the words together to create a coherent sentence. This is pretty neat. Not only can Ruby perform arithmetic expressions, it's also able to perform comparisons. This means that programmers can take the results of their expressions and use them to make decisions. Check out these examples. Data and data types can be compared in many different ways. In the first example, 10 is greater than 1, so the result true is printed. True is itself another data type, referred to as a Boolean. Booleans represent one of two possible states, either true or false. Every time you perform a comparison in Ruby, its result is a Boolean of the appropriate value. The next example demonstrates the usage of the equality operator, or the double equal sign, which is a test to see if two things are equal. In this case, the string cat is not equal to the string dog, so the Boolean false is printed. In our last example, we perform the opposite comparison using the negated form of the equality operator, not equals, represented as exclamation point equals, which verifies that 1 is indeed not equal to 2. There are several more types of logical operators in Ruby, which allow you to connect multiple statements together and perform more complex comparisons. There are several more types of logical operators in Ruby, which allow you to connect multiple statements together and perform more complex comparisons. The logical operators are indicated by the ampersand ampersand, logical and, pipe pipe, logical or, and exclamation point, for not, symbols. Let's look at some examples. The logical AND operator will evaluate to true only when both sides of the expression are true. The logical OR operator will evaluate to true if either side of the expression is true. Finally, the logical NOT operator will evaluate to true when its operand, or the data that the operator works on, is false, and evaluate to false when its operand is true. Logical operators are important because they help us write more complex instructions for the computer, which we'll see in action in the upcoming lessons. That seems pretty logical to me. When evaluating logical expressions, Ruby uses rules of operator precedence, just like it does for mathematical order of operations. Each operator has a precedence, and the order of evaluation of operators in a logical expression is determined by that precedence. In Ruby, logical AND has a higher precedence than logical OR, and logical NOT has a higher precedence than both of them. High precedence operators happen before lower ones. In this example, Since logical AND has a higher precedence, true, logical AND, false is evaluated first, which results in a false. Then the logical OR is applied to false, or false, which finally results in false. The logical operators can also be represented by the AND, OR, and NOT keywords, but at a lower precedence. This means they're evaluated after the symbolic operators in an expression, which can lead to some tricky and surprising behavior. Check this out. Weird, right? For this reason, in Ruby, the plain English operators are more commonly used to control the flow of a program, rather than as Boolean logic operators. Using these plain language operators in this way makes Ruby programs more natural to read. For example, compare the use of Boolean logic operators in the first snippet to the use of plain English language operators in the second. A full list that includes every operator available in Ruby can be found all over the internet, including the Tutorials Point website, so make sure to check it out. By now, you've seen the potential power of using expressions and comparators in Ruby. But your computer is way more than just a simple calculator, and the scripts you write will probably need to perform actions on values you might not know beforehand. This is where the concept of variables comes in handy, and that's what we'll cover in this lesson. In a computer program, a variable is a placeholder for a value. That value can be a number, a string, or even another variable. You can think of variables as containers for data. So when you create a variable in your code, under the hood, the computer is reserving a chunk of its own memory to store that value. This means the computer can also access the variable later to read or modify the value. Consider a simple script that calculates the area of a rectangle using the formula area equals length times width. Area, length, and width can all be represented by variables. Let's look at an example. In this script, we're creating 3 variables and storing different values in each. The process of storing a value inside a variable is called assignment. Here, we assign the length variable the value of 10, the width variable the value of 2, and the area variable with the result of the expression length times width. As you can see, expressions can be created using variables and the result stored in other variables. Finally, we print the value of the area variable to the screen with our old friend puts. Hey puts, I missed you. Variables are important in programming because they allow you to perform operations on data that may change. If the script that calculates the area of a rectangle was extended to accept any input as the value of the length and width variables, you could calculate the area of any rectangle. Or to give it a more IT-focused example, a script that performed an operation on a file could be extended to perform the operation on any file, if the program used a variable to store the file name. Variables are super useful because you can store almost anything in them, including strings, integers, and other data types. Assignment to a variable is done by using the equal sign in the form of variable equals value. Generally, you can name variables however you want, but there are some restrictions. First, keep in mind that you shouldn't use any of the keywords or methods Ruby reserves for itself as variable names, like puts. Using these reserved terms can make your program very confusing to read and result in errors from unexpected behavior, so steer clear. Ruby has a few restrictions on the characters that you can use to define a variable. Variable names can't have any spaces and must start with either a letter or an underscore. They sound like they'd make good passwords, right? Variables can also be made up of only letters, numbers, and underscores. Remember that precision is important when programming. Ruby variables are case sensitive, so capitalization matters. Let's look at some examples of valid and invalid variable names. I_m_a_variable is a valid variable name. I am a variable too is also a valid variable name. 1_is_a_number is invalid, as variable names must start with a letter or underscore. Apples underscore ampersand underscore oranges is also invalid, as the special character ampersand is present in the name. You can use variables in expressions just like we did with plain numbers and strings in the previous video. For example, what do you think this code snippet evaluates to? If you guessed true, then congratulations, you're correct. This is a tricky statement, so don't worry if you didn't understand it right away. Let's unpack what's going on here. First, we set the values of variables x and y to 10 and 5, respectively, by using the equal sign. Then we create an expression. This expression uses the logical AND operator. This means that if the statements on both sides of the AND symbols are true, then the entire expression evaluates to true. Since we set x equal to 10 in the first line, the statement x equals 10 is true. On the second line, we set y equals to 5. So when we evaluate the expression y times 2 equals x, it really means 5 times 2 equals 10. This also evaluates to true, so the entire expression is true. Now that you've learned a bit about variables, let's solidify your knowledge with a quiz. Now that you're armed with knowledge of expressions, comparators, and variables in Ruby, we're going to spend this lesson diving into how we can combine them in our scripts to perform different actions based on their values. The ability of a program to alter its execution sequence is called branching or flow control, and it's a key component in making your scripts and automation useful. You probably use the concept of branching often in your everyday life. So say it's before noon, you usually make the choice to greet someone with good morning instead of good evening. If it's raining outside, you might choose to take an umbrella. If it's cold, you'd probably wear a jacket. In your scripts, you can also instruct your computer to make decisions based on inputs so that it's tailor-made to your needs. Let's imagine that you were given the task of writing a program that could decide if a person was old enough to vote. You'd want them to be able to type in their age and have their computer print out a message indicating their eligibility to vote. In the United States, the voting age is 18, so we'll use that as our voting criteria. That type of program might look something like this. There are a few things in this program that we haven't seen before, so let's walk through it line by line. First, we display a message on the screen asking the user how old they are. Next, we save the result of something called gets.chomp into a variable named age. Let's take a closer look at gets.chomp. You can think of gets as the opposite of the puts keyword. If puts prints something to the terminal, then gets does the opposite by reading in what you type into the terminal as a string. This is how you make your scripts interactive and accept user input. When you use gets, it returns the line of text as a string value. When it does this, it will also include a line break or new line character at the end of the string. Meanwhile, chomp does some cleanup on that string, chopping off the extra new line character that comes along with your input when you press enter. In other words, calling chomp on that value will remove the line break. Going back to our voting example, now we have the age that the user typed in. But since gets reads everything typed into the terminal as a string, we can't compare the value of age to another number yet. Do you remember our lesson about expressions in previous videos? Although some data types can be converted automatically, like float to integer, others, like string to integer, can't be. If you want to perform a conversion, you need to tell the computer what to do. This is one of the latter cases. We need to tell the computer that it should treat the value typed in by the user as an integer instead of as a string. We do this by using the age.toI notation, which does that conversion for us. Now that we've got the data in the right format, we can actually do a comparison and make a decision. To do this, we use the if statement. If the expression that comes after the if statement is true, in this case, if the age of the user is less than 18, then the code between if and n is executed, and the message, "Sorry, you are not old enough to vote yet," is printed to the terminal. Nil is a reserved word to represent the concept nothing in Ruby. It's also worth noting that nil is the only value ever coerced or changed into false when evaluating a Boolean expression, while everything else counts as true. Take, for example, the following code snippet. First, we set the variable SomeValue to a string. There is something here. Then, we perform an if evaluation on that variable. If SomeValue, then print the statement evaluated to true. SomeValue is automatically coerced into a true Boolean value. Therefore, the statement evaluated to true is printed. On the other hand, if we set SomeValue equal to nil, then when the expression is evaluated, SomeValue is coerced to false, and the statement evaluated to true is not printed. The if statement is already a super useful construct, but it can be extended even more. What if you wanted to print out a message if the user's age was greater than 18? You could update the program like this. The program can now go in two directions based on the input of the user. If the user's age is less than 18, it will print a message indicating the user isn't old enough to vote yet. On the other hand, if the user's age is greater than or equal to 18, a message will be displayed indicating they're eligible to vote. If you need to handle more than two comparison cases, more branches can be added to your code using the else if statement, written like else if. What if we wanted to print a special message to voters who were teenagers? Well, we'd want to check if their age was either 18 or 19 and print the message accordingly. This is what this code does. If the user types 19 at the terminal, the program will start by evaluating the expression in the first if statement. It will see that 19 is greater than 18 is false, so it will skip the else if statement. 19 greater than equal to 18 and 19 less than equal to 19 are both true. Remember the logical AND comparator we talked about in the video about variables? So now the computer prints out "you are a teenage voter," then skips down to the end keyword and exits. What if the voting age of your country is something other than 18? This is the perfect time to use a variable. Instead of hard-coding the value 18 into the script, we could instead use a variable to represent it, like this. If we need to change the voting age in the future, or even enhance our program to accept the voting age and the user's age at the terminal, we can use the voting_age variable to keep our code working. Hard-coded numbers in a program like 18 are referred to as magic numbers, and it's best to avoid them because they make your code less adaptive to change. Also, they're magic, and you just don't want to mess with magic. So, what do you think about branching? Pretty useful stuff, huh? Using branching to determine the flow of your program opens up a whole realm of possibilities in your scripts. By using comparisons, you can pick between executing different pieces of code, which makes your scripts flexible. You can use branching to do all kinds of practical things, like only backing up files with a certain extension or allowing login access to a server only during certain times of the day. Anytime your program needs to make a decision, you can specify its behavior with a branching statement. But before we branch out and move on to the next video, let's take another look at the voting age program we wrote earlier. It gets the job done, but there sure are a lot of to_i statements to convert the input to an integer. What if we cleaned it up a bit, like this? That looks a lot better, don't you think? We're also only doing the conversion once, But how? What does the dot notation mean? And why can we add the to_i conversion to chump by using it? This is part of the magic of object-oriented programming, which we'll explore together in the next set of videos. Don't confuse this magic with the magic numbers we talked about before. You'll find that in the world of IT, magic is an everyday occurrence. Now let's see if you can magically ace this quiz. Welcome back! In this lesson, we're going to talk about object orientation. Imagine if you had to describe an apple to someone who had never heard of one before. How would you do it? What would you say? You could start by mentioning that an apple is a type of fruit. You might talk about how there are many different kinds of apples, each with its own color, flavor, and name. And you might mention that teachers love apples. I just gotta swallow it. Tart. You can think of explaining concepts to your computer in similar terms. Your computer has no knowledge of what an apple is, or any notion of what makes up a fruit. If you want your computer to know what these things are, you have to describe them in your programs and scripts. Variables and expressions are both powerful tools in a programmer's toolbox, but it can be difficult to translate real-world concepts like what is an apple, or what is a user account, or what is a file, into programs using just variables and expressions. To help with this, Ruby follows a programming pattern called object-oriented programming, which models concepts using classes and objects. You'll sometimes see this shortened to OOP or OOP. OOP is a flexible, powerful paradigm where classes represent and define concepts, while objects are instances of classes. Oops, I did it again. I threw some knowledge your way. The idea of object-oriented programming might sound a little weird and sort of confusing, but you've actually been using objects already without even realizing it. See, almost everything in Ruby is an object. All of the numbers, the strings, and variables you've learned about so far and have used in your exercises and quizzes have been objects. Instances of some class representing a concept. So you're already ahead of the game. Defining a real-world concept in code can be tricky, so let's look at how we might translate our ideas about how to represent the concept of an apple in Ruby code. We'll take it step by step and keep it simple. Defining your own classes isn't always necessary when writing scripts, but exposure to object orientation is really useful when programming in an object-oriented language like Ruby. We could use this code to define our basic apple. It might not look like much, but with these 2 lines, we've defined our first class. Look at the syntax. In Ruby, you use the class reserved keyword to indicate you're beginning a new class, and follow up with the name of the class. The first character of the class name must be a capital letter according to the Ruby syntax rules. In this case, our class is called apple. The end keyword indicates the end of your class definition, and it should line up with the class keyword. Let's think about how we might expand our definition of the apple class. It should probably have some attributes that represent information we want to associate with the concept of an apple, like color and flavor. We can add this information like so. The attr accessor is a special method that does some work under the hood to let us set and retrieve the attributes of our apple, which in this case we've assigned to color and flavor. The class and end keywords still line up, but you might notice that we've indented the second line of the class. This isn't strictly necessary, but makes our code easier to read. I really recommend it. Now that we've got an apple class and some attributes, let's see our apple in action. In the first line, we're creating a new instance of our apple class and assigning it to a variable called Gala. After we've got our shiny new apple object, we then set both the color and flavor as string values, then retrieve them both and print them to the screen. Congrats, you've made your first class. Now that you've seen how to define a class, let's revisit a statement we made earlier. We said that almost everything in Ruby is an object, including strings and numbers. What exactly did we mean by that? Check out this example. If nearly everything in Ruby is an object, it follows that the integer 10 is no exception. Since objects are instances of classes, in the most precise terms, we could say that 10 is an instance of the class integer, just like Gala is an instance of the class apple. This is supported by the code we just saw, which, because of Ruby's relatively natural-looking syntax, reads almost like a question asked in English. Is 10 an instance of integer? The answer is yes, or in more computer-friendly terms, true. It seems that the number 10, or any number, has a lot more going on than you might think. You might recognize the dot syntax from earlier examples, like our voting age program or Apple example. This syntax is usually called dot notation because of the period symbol used in the expression. Dot notation allows you to access any of the abilities the object might have, called methods, or information it might store, called attributes, like flavor. The attributes and methods of some objects even have attributes and methods of their own. This is how we were able to use the gets.chomp.to_i notation to read user input, clean it up, and then convert it to an integer all in one line. So what exactly is happening when we write 10.instance of integer? First, it's helpful to know that by convention, any method in Ruby that returns a Boolean value after it's called has a name that ends in a question mark. This means that the result of instance underscore of question mark will likely either be true or false. Any class name you add after the question mark will be read by the method and evaluated, and true or false will be returned, based on whether or not 10 is an instance of that class. It was a lot to digest. Apple pun totally intended. Here's an example. We can verify that 10 is not an instance of a string with this code. What if you don't have the foggiest idea about what class an object might belong to? Don't worry, there's another method that will help you figure that out. Looking into objects to figure out what class they belong to is a process called introspection. It's a complicated topic, and we'll just scratch the surface here. It's enough to know, for now, that you can look at an object's type by using the .class method. Another key aspect of object-oriented programming is something called inheritance. Just like people have parents, grandparents, and so on, objects also have an ancestry. The principle of inheritance lets a programmer build relationships between concepts and group them together. For example, how could we develop our apple representation to encompass other types of fruit? Well, one thing we know about an apple is that it's a fruit, so we could define a separate fruit class. All fruits have both a color and a taste. So what if we moved our color and flavor attributes into the fruit class? Then we could rewrite our apple class and add another fruit into the mix. In Ruby, in this context, the less than symbol indicates an inheritance relationship. For our two new fruit classes, we've used that symbol to tell our computer that both the apple and grape classes inherit from the fruit class. Because of this, they've both got the same color and flavor attributes available to them. You can think of the fruit class as the parent class, and the apple and grape classes as siblings. Again, let's see this in action. In the first line, we create a new instance of apple and call it Granny_Smith. We set the flavor of Granny Smith to tart and set the color to green. In the next line, we create an instance of the grape class and call it Carnelian. Like we did with apple, we set both the flavor and color to strings of text that are appropriate to the object. You can use the fruit class to store information that applies to all kinds of fruit, and keep the apple or grape-specific attributes in their respective classes. Object orientation is not easy to understand, so you deserve a big congratulations for getting through these concepts. If you ever feel like you're disoriented with object orientation, just remember, in an object-oriented language like Ruby, real-world concepts are represented by classes. Instances of classes are called objects. Objects are organized by inheritance. Objects can have attributes, which are used to store information about them. You can make objects do work by calling their methods using dot notation. Now, let's see how you do on this quiz. Good luck. You've come a really long way. So far, we've created expressions using single instances of objects, single variables, single numbers, and single strings. This works pretty well, up to a point. Eventually in your scripts, you'll want to develop code that manipulates collections of objects, like a list of strings representing all the file names in a directory, or a list of integers representing a bunch of timestamps. This is where the array data type comes in handy. That's what we'll cover in this lesson. You can think of arrays as long boxes, with the space inside the box divided up into different slots. Each slot can contain a different value. In Ruby, you use the square bracket symbols to denote the start and end of an array. Let's look at an example. Here, we've created a new variable called x and set its contents to be that of an array of strings. Remembering what we learned earlier about object orientation, we can verify that x is an array by using the class method, which is defined for all objects by default. You can print the entire array by using the puts method, as we've done with other variables. You can access individual elements by using their position in the array, a process called indexing. In most programming languages, including Ruby, the first element in an array is given the index 0. This means that the last index of the array will be the length of the array, how many elements it has, minus 1. We can get at each of the elements in the array individually, like so. Notice that when we wrote the statement puts x bracket 4, nothing was printed out. This is because there are only 4 elements in our array. Remember that since array indices start at 0, accessing the item at index 4 means we're trying to access the 5th element in the array. There are only 4 elements, so nothing is printed on the screen. If this seems confusing, this visualization might help you out. As you can see, index 4 doesn't point at anything, so there's no slot 4 in our array. In Ruby, the concept of nothing is represented by the nil object. So when you try and print a nil object using puts, Ruby prints out nothing. You can verify this for yourself by looking at the class of the 3rd slot in our array and comparing it to the non-existent 4th one. The 4th element of the array x, the element at the 3rd index, is the string cooking. And look, we see that the string is printed as its class. As there's no 5th element in our array, the 4th index, Ruby helpfully tells us so by showing us the nil class, the class of the nil object. Isn't Ruby the best? Accessing the elements of an array one by one is useful as a demonstration, but in the real world it isn't all that practical. What if your array has hundreds of elements in it? You could print the array using puts, but what if you wanted to manipulate each element somehow instead of just printing it? Luckily for us, Ruby provides a mechanism for looping through arrays using the each method. As with other methods we've seen, you can access the each method using dot notation. Using the each method of the excited_array, we've looped through every string element in the array and printed that element alongside the string ! This is more simple and much faster for us to write than accessing each element individually through its index, especially if the number of items in the array is large. Check out the syntax we used here to perform the iteration. As we step through the contents of the array, we point the word variable at each element we loop through, indicated by the pipe word pipe syntax. This means on the first iteration, the word points at I. The next, it points at M, and so on. Whatever code we put between the do and end keywords, called a block in Ruby, will be executed on each of the elements in the array. We've also introduced a new way to combine strings in this example. Before, we demonstrated how to add strings together using the plus symbol. Here, we used a technique called string interpolation to append the exclamation point string to each word that we print. Instead of adding strings together, string interpolation lets you embed variables and expressions into strings and treat the results of their evaluation as strings themselves. Anything between the hash and brackets gets evaluated this way, even numerical expressions. This means you can do things like this, which is pretty awesome, don't you think? Let's go back to the each method. In Ruby, a method like each that loops through a collection of objects like an array is called an iterator. These iterator methods can be found on all kinds of objects, including numbers. Take, for example, the integer iterator called times. We used it in one of our earliest examples where we compared Ruby to some other languages. Along with times, there are several other methods that you can use to iterate over a range of numbers. You can count up and down with the up to and down to methods respectively, with both numbers and strings. This syntax displays how you can write iterators on a single line. The curly braces symbols are another way to define a block, just like the do and end keywords did in the example above. Everything in the block is executed each time the loop runs. You can access the number indicating the current iteration by naming a variable and putting it between the pipe symbols, just like we did when we used the each method to iterate through an array. We call the variables in between the pipe symbols optional arguments. You can use optional arguments in do and block statements too. For example, the contents of an array don't have to be predefined when you create it. You can start with an empty array and add or remove data as needed. Empty arrays are represented by two square brackets with nothing in them. You can add elements to the end of the array by using the push method like this, and remove elements from the end of the array with the pop method. Arrays even have built-in methods to sort their contents, whether they contain numbers or strings. A super useful method that arrays have is called length. You can use it to find out how many elements there are in an array, and even use that number to retrieve the last value in an array, although Ruby also gives us the .last method to do this for convenience. Pretty cool, huh? Ruby provides all sorts of methods to help you out when you want to work with arrays. You can check out the full list of them in the Ruby documentation. Get ready, because you've got another quiz coming up. Computers are useful in so many ways, and their ability to perform repetitive tasks in an identical way without tiring out is part of what makes them so useful in automation. You've seen how to perform some simple loops using the iterator methods to cycle through arrays, but what if you wanted to execute a task repeatedly until a condition was met, without knowing how many repetitions it would take beforehand? Well, we're about to find out. In this lesson, we'll cover flow control with loops. Iterators aren't the right tool for this job, as loops defined with iterators require you to specify the number of times they run, either directly or by the number of elements in the collection. For example, you know that both of these statements will be executed 5 times. Thankfully, there are other ways to loop through your code. In this video, we're going to talk about a construct called the while loop. While loops give you the ability to continually execute your code based on the result of a comparison. This is similar to how branching if statements work. Check out this program. What do you think it does? Run it a few times to verify your hypothesis. We start out by initializing a variable called age to have a value of 0. Then we enter our while loop, which checks to see if the age value inside of the age variable is less than 18. If that comparison evaluates to true, then the code between while and end is executed. On the first pass through the loop, age is equal to 0, so the comparison 0 is less than 18 is true. And we then enter the block of code within the while loop. In that code, we first convert age, an integer, to a string. Remember that we did the opposite when we talked about branching in the previous lesson. We can then combine the string representation of age with the is not old enough to vote string and print it. Finally, we increase the value of age by using its previous value and adding 1. This process continues until the result of the comparison isn't true anymore, which happens to be when age is set to 18. When age less than 18 evaluates to false, the computer skips directly to the end keyword and continues executing the code from there, which means it will finish by printing 18 is indeed old enough to vote. While loops use a comparison to ensure that they will eventually exit. Without an exit condition, they could execute forever in what's called an infinite loop. If you've used the ping utility on a Linux system, you've actually seen an infinite loop in action. Infinite means exactly that, as ping will keep sending packets and printing the results to the terminal forever, unless you send it the interrupt signal, usually by pressing Ctrl-C. If you were to look at the source code of the ping program, you'd see it contains an infinite loop whose block of code contains the instructions to keep sending those packets forever. All this talk about loops is making me a little loopy. You take a quiz while I take a break, and we'll meet back here in a few. In this lesson, we're going to check out hashes. Like arrays, hashes, which are also known as associative arrays, are used to organize objects into collections. Unlike arrays, though, you don't access elements inside of the hashes using their position. Instead, the data inside of hashes takes the form of pairs of keys and values. To get at a hash value, you use its corresponding key. Also, unlike an array where the index must be a number, in a hash, you can use any kind of object as a key, including strings, integers, floats, and more. It might be helpful for you to think about hashes being similar to dictionaries, where each word has a definition associated with it. In the language of hashes, the word would be the key, and the definition would be the value. Now, how about an example? You can create an empty hash in a similar way to creating an empty list, except instead of square brackets, dictionaries use curly braces to define their content. Once again, you can use the .class method to verify that the type of the variable you've just created is a hash. Creating initialized hashes isn't too different from the syntax we used to create initialized arrays back in a previous example. But instead of a series of slots with values in them, we have a series of keys that point to values. In the file counts hash, we've got string keys like JPG that point at integer values like 10 using this symbol and separated by commas. Mixing and matching key value data types in this way is perfectly fine in a hash and can be really useful like in our example. The file extension information makes sense to be encoded as a string, while it's natural to represent a count as an integer number. In our file counts example, let's say you wanted to find out how many files there were of type txt in the hash. In order to do this, you'd want to use the key txt to access its associated value. The syntax to do this may look familiar, as we've used something similar in our examples of indexing into an array. It probably won't come as a surprise to you to learn that, also like an array, you can use the each method to iterate through the contents of a hash. There's a slight twist though. In your iteration code block, you want to have two variables between the pipe symbols, one for the key and one for the value. There are 10 files with the .jpg extension. There are 14 files with the .txt extension. And there are 2 files with the .csv extension. Finally, there are 23 files with the .rb extension. In this example, on each pass through the array, we put the key parameter into a variable named key and the value parameter into a variable we've called value. We then create a message to be printed on the screen, keeping in mind that we need to convert the value variable from an integer into a string if we want to combine it with the rest of the message. Remember that along with the do end block syntax, we can define blocks using curly braces on one line. We could therefore achieve the same result with this code. Like an array, you can add elements to a hash dynamically. If you want to create a new key-value pair, just use the square brackets to define it. Let's add a file count of 88 for a new GIF file extension in our hash. This brings up an interesting point about hashes. What do you think would happen if you tried to add a key that already existed in the hash? When you use a key that already exists to set a value, the value that was already paired with that key is overwritten. As you can see, the value associated with the RB key used to be 23, but is now 1. This means that the keys inside of a hash must be unique. Duplicate keys will point to the same value. You can delete elements from a hash with the convenient delete method. Just provide the key to the element you want to remove, and delete will take care of the rest. Sometimes you might just be interested in only the keys of a hash. Other times you might just want the values. You can access both with their corresponding hash methods, like this. Conveniently for us, these methods return an array of the data you've requested. You can then use any of the array methods we've already learned about. The ability to retrieve only the keys or values of a hash can be useful in certain situations, but generally it's better to access the values in a hash through their keys. Hashes and arrays are both super useful, and each has their own strengths in different situations. So when would you use an array, and when is a hash the better way to go? Think about the kind of information you can represent in each data structure. If you've got a list of information you'd like to collect together and use in your script, then an array could be the right way to go. For example, if you want to store a list of IP addresses to ping, you could put all of them into an array to iterate over. Alternatively, if you had a list of hosts and their corresponding IP addresses, you might want to pair them as key values in a hash. I know that we've covered a lot, but we've just scratched the surface of what hashes can do for you and your scripts. Remember when I said that hashes can contain any kind of object? This means that the insides of hashes can be made up of lists or even other hashes. You can use this ability to represent more complex data structures like directory trees in a file system. If you're interested, you can find more information on hashes in the Ruby docs. This is an example of where you can get really creative with your coding. I hope your quiz went well. In this lesson, we're going to cover methods. When we dove into object orientation, I mentioned that methods are how you get objects to do work. We've seen several methods in action in our examples so far, like class, each, chomp, and toS. Although it may be clear that methods are pretty useful, we haven't explored how they do what they do or how you can make them on your own. Let's take a closer look now. We'll start by defining a simple class, then create an instance of it. Our new piglet might be cute, but it can't do too much at the moment. What if we wanted this little piggy to speak? In order for Piglet objects to perform actions, they need methods. The act of creating a method is referred to as defining it. Check out our Piglet now. You can see that we begin defining a method with the def keyword, short for define, and end it with the end keyword. This is similar to the syntax we saw earlier when we learned about loops and iterators, where the code is executed and grouped into a block. After the def keyword, we give our method a name. In this case, we call it speak. On the next line, we specify the code that should be executed when our method is called until we reach the end keyword. It's not so bad, right? But wait, there's more. Methods can do a lot more than just print predefined values. What if you wanted to give your pig the ability to say not just one thing, but anything you tell it to? This would require the ability to pass some data to the method in order for the method to carry out the work of printing it out. To allow our method to accept some data, let's change it like this. First, Notice the words variable we've added after our method name, which is wrapped in parentheses. Next, check out how we're calling our speak method. After writing hamlet.speak, we've specified a string that is also wrapped in parentheses. And when the code is executed, the strings are printed. So what's going on here? Instead of predefining the string we want to print on the screen, as we did with oink oink, we've changed our speak method to accept any value we give it. When we call the method by using hamlet.speak, anything we put after the method name gets passed into the words variable of our method, which then uses puts to print to the screen. In programming speak, the data that you pass to a method is called an argument, and the variable that represents that data being read into the method is called a parameter. In Ruby, you optionally wrap method arguments and parameters in parentheses. In our examples, we follow the convention defined in the Ruby Community Style Guide. The guide states that parentheses should be used when there are either parameters to wrap in a method declaration or when there are arguments to wrap in a method call. So, we could just as easily tell our pig to say something by writing our method without parentheses around the arguments or parameters. But doing so makes the code a little harder to read, as the parentheses clearly denote what's being passed to and received by the method. Look at that. The style guide also states that you can go either way you like when using methods like puts, which have an almost keyword-like status. This means that both of these work perfectly fine, although our examples omit the parentheses in this course. Now we've seen how we can pass values into a method as arguments. But what about getting values out of a method? This is where the concept of return values comes into play. The work that methods do can produce new results. Sure, we can print the results to the screen, but what if we wanted to use those results later in our script? Or what if we didn't want to print them at all? We can do this by returning values from the methods we define. As you can see, we've added a pigYears method to our piglet class. When it's called, the pigYears method first calculates a value and stores it in the result variable. Then it returns that result back to the code that called it. It's important to remember that once the flow of execution inside a method hits a return statement, the method is immediately exited and the result is returned. In our case, the return value is stored in the age variable. Don't forget that. Like parentheses around arguments and parameters, specifying the return statement is optional in Ruby. If you don't use return to declare what value you're returning, then Ruby assumes you want to return the last value declared or calculated in the method. With this in mind, we could rewrite our pigYears method and get the same result. In this case, Ruby will assume that you want to return the value of the expression age times 18, which will give us the same functionality as the previous pigYears example. Do you remember our example of the apple class from our lesson on object orientation? We defined some attributes for our object, but aside from setting and printing them, we didn't do too much with their values. Well, the methods that you define for your classes can actually make use of those attributes in what are called instance variables. Instance variables have their own special syntax, which are indicated by the use of the @ symbol. Consider our definition of an apple, with the attributes of color and flavor. If we added a new method to the apple class called description to print a description of our apple to the screen, we would need to be able to access the color and flavor attributes somehow. This is where we can use the instance variables. Here, we see the description method is using the instance variables in conjunction with the technique of string interpolation to print out the message. Remember that anything between the hash and curly brace characters is evaluated just like a Ruby expression, and we're able to access the values of the color and flavor instance variables by putting the @ symbol before their names. This makes the actions that your objects can perform even more useful, as they can also use attributes. Aside from giving objects the ability to perform actions like making piggies talk, Methods can be used to organize the code in your scripts into logical blocks. Using methods in this way will make the code you write easier to use and reuse, and you don't even need to create a class since methods can be defined independently outside of classes. Check out this code. This program calculates the y-intercept of two separate lines using the formula y equals mx plus b. You might notice that some of the code is duplicated. Each time we want to perform the calculation, we change the values of the variables and write the equation, then print some informative text followed by the answer. Code duplication in your scripts is generally a good indication that you can clean things up a bit by using a method. How about we rewrite this code, but use a method to group our calculations and put statements? The updated program gives us the exact same result as our first program when run, but it looks a lot cleaner. First, we've defined a method called calculateIntercept, which does our calculation and printing for us. We can put the numbers we want to use in these calculations directly into the arguments of our method call, and the calculateIntercept method can use them as parameters. Check out how the arguments line up with the positions of the parameters. In the first call, 1 maps to m, 2 maps to x, and 10 maps to b. We've also made use of the return keyword to pass the calculated value back to the calling code, and then printed it with some string interpolation. Since we've grouped the calculation and print statements into a method, our code is not only easier to read but also reusable, which is extremely useful. We can execute the code inside the calculateIntercept method as many times as we need, just by calling it with the numbers we want to calculate. There's no need to write it out over and over again every time we want to figure out the y-intercept of a line, and that's a big time saver. Hopefully these examples have clarified some things about how methods are used and defined. They've also demonstrated how useful they can be. Methods are pretty handy. In the coming lessons, we'll be using many of the methods built into Ruby, like puts and class, and defining our own in our scripts. There's a method to my madness, I promise. I'm really proud of what you've accomplished. So far, we've gone through a lot of the nitty-gritty of how to write code, and I know it wasn't easy. We've talked about using Ruby to construct expressions and use variables, then make decisions based on their values. We've created piggies and apples and learned about the concepts behind object orientation, then looped through arrays and hashes. We've used all kinds of different methods, some built into the Ruby language and others that we wrote on our own. I mean, let's just say it, we nailed it. In this lesson, we're going to talk about a different side of programming: style. Having good or bad style when you write code doesn't generally make the difference between a script succeeding or crashing, but it can make a big difference to the people who have to use it. And who doesn't want to have good style? Bad programming style can make life difficult for the IT support specialists or system administrators who have to read the script after it's written, or make changes to it so that it works with the new system. Bad style can even cause problems for the script's author, who might have just come back from a long vacation and have no memory of why they chose to write such a complicated piece of code in the first place. A bad style just isn't a good look. On the other hand, good style can make a script look almost like a natural human language, making its intent and construction readily apparent to the reader. Good style makes life easier for those who have to maintain the code and helps them understand what it does and how it does it. It can also reduce errors as updates to the code are easier and more straightforward. Bad style can hide problems in code too. If a particular method is a messy knot of nested if statements, it will probably be harder to figure out if the code is working as you intended it. And changing it later will be harder. In short, good style is just a good practice. So let's make sure you've got it. So what makes the style of a piece of code good or bad? Although there are no hard and fast rules that apply to every programming language and situation, keeping a few principles in mind when you write your scripts can go a long way to creating good, well-styled code. First, code that you write should be as self-documenting as possible. Self-documenting code is written in a way that is readable and doesn't conceal its intent. This principle can be applied to all aspects of writing code, from picking your variable names to writing clear, concise expressions. Take this code snippet. The purpose of this code is hard to determine just by looking at it. The names of the variables don't give the reader much information, and although you can likely work out the result of the calculation, there are no clues in this code as to what the result might be used for. What if we rewrote this code to be a bit more self-documenting? In programming terms, this rewriting process is commonly referred to as refactoring. Looking at a refactored code, its intent should be much more clear. The names of the variables and their method reflect their purpose, which helps the reader understand the code quickly. Although it's great if your code is self-documenting, sometimes you may need to use a particularly tricky bit of code in your script. When good naming and clean organization can't make the code clear, you can add a bit of explanatory text to it yourself in the form of something called a comment, which we'll talk about in the next video. See you there. Let's talk about comments and consistency. In Ruby, comments are indicated by the hash character. When your computer sees a hash character, it knows that it should ignore everything on the line that comes after it. Ruby also lets you define blocks of comments that span multiple lines by using the =begin and =end keywords. But in this course, we'll be using the hash character as it provides a nice visual separation of comments and code. Another sign of good coding style is consistency. Consistent code is more visually appealing and easier to read, but it also sets the expectation that things will work pretty similarly across your program. This is especially useful when your scripts start to grow in size and complexity. Some consistency is enforced by the language itself. For example, as all the names of classes in Ruby must start with a capital letter, you can be pretty sure that whenever you see something like A animal, the code is referring to a class. In other situations, you'll need to be disciplined about enforcing consistent rules yourself. If your workplace doesn't already have one, it can be super useful to develop consistency standards into a style guide. This document should lay out some rules for writing code at your company to keep everyone on the same page. It will also ensure the scripts you and your team write are consistent regardless of their author and purpose. If your company doesn't have its own style guide, you can find lots of examples on the internet, including the community-driven guide written specifically for Ruby. You'll find a link to that guide in the next reading. Some companies don't just stop at a style guide. They'll also implement a process called code review. The idea is that after you write some code, you send it to a coworker to proofread it, checking for errors and ensuring it follows the tenets laid out in the style guide. Of course, this can be hard to do if you're the only person who knows how to write code in your company. Hey Self, how does my code look? Looks great, Self. Cool, great review. If you do have potential reviewers available, putting code through a review process is generally a good idea, as it results in higher quality code that's less buggy. Whatever conventions you choose, and whether or not you use a style guide or code reviews, just keep in mind that good code should be readable. If you remember a few of the principles we've talked about here, you should be well on your way to writing high-quality scripts in high style. So one of the automation challenges that I've taken on in SRE so far is revamping the monitoring structure of a large service. That meant going in, looking at all the graphs and alerts and dashboards, and making sure that they actually captured the things that we wanted to know about the system, and that the alerts were actionable and they didn't cause pager fatigue when someone gets paged a bunch of times for things that they can't do anything about. The task was to go through all this stuff, make sure that it was relevant and usable, and then revamp it, refactor it, make it better and faster, and transfer it to new systems and services. So I gained a lot of information and expertise in the monitoring and alerting space, which was really interesting. I think the hardest moment of my career so far was probably the first time that I was on call and got paged. So that happens when like something really serious has gone wrong in a big system, and you are like the person that needs to fix it. Although I felt like that was me, I need to fix it, it was all down to me, it really wasn't. As soon as I got paged, people came in and they asked me what was going on, if I needed help. So it was very hard, but also incredibly reassuring to know that I had this support structure to help me through this problem. Welcome back! Amazing job getting through last week's lesson. We laid down a foundation of programming concepts and got a sneak peek into how an IT support specialist might use programming skills to create automation to save time and cut down on mistakes. Using the Ruby language, we've looked at programming basics like variables, loops, and arrays. We've also covered more advanced topics like object-oriented programming and learned how to spot the difference between a class and a method. This week, we'll build on this new knowledge and look at how we can use our new programming skills to create scripts that perform work for us. We'll start by looking at how we can organize and use code across multiple different Ruby files. Then, we'll learn about libraries of code and how they're packaged, how to read and write files, use subprocesses, and input streams. We'll wrap everything up by writing a script to discover all of the hosts on a local network. You'll be doing real live coding, bringing what you've learned to life, which is super exciting stuff. Are you excited? I'm excited. Let's get started. We talked about code reusability when we examined methods, which provide the ability to group code into logical blocks that can be executed at a later point, and as many times as we need. When our scripts get bigger and more complicated though, we'll probably want to reuse more than just a single method. We might even want to reuse entire scripts in other programs that we write. Let's say that you've created a script that emails a daily summary of IT tickets you completed to your manager. The script has two major jobs. First, it assembles a list of the tickets you finished by interfacing with the company's issue tracking system. And second, it uses that list to create an email and sends it to your manager. In a separate project, let's say you want to automatically parse a system log and search for an event it contains. If the event is found in the log, you want to trigger an email to notify yourself. If you look closely, you can probably spot the functional overlap between these two scripts. Both of these automation projects rely on the ability to send an email message. The most straightforward way to handle this is to just duplicate the email sending code, copying it from one .rb file to another. This might be easy, but duplicating code in this way has some pretty big downsides. You need to maintain the same code in two separate places, which makes implementing updates and fixing any bugs kind of a pain. And if your coworkers want to use the email code you wrote in their own projects, keeping track of all of the places it's copied to quickly becomes tricky, as does sharing different versions. We're trying to make things easier, not harder, so what gives? The desire for code reuse, or to reuse code that you or others have already written, is common in programming. Nearly all languages provide some way of doing it. In the coming videos, we'll check out how Ruby approaches organizing and reusing code across different files. We'll talk about how this can be used to extend the functionality of your scripts without resorting to copy and pasting code. When your scripts grow more complex, you'll probably want to break them out across multiple files. Ideally, the contents of each file would be grouped by their purpose into logical chunks, like a file called email.rb with all the code related to sending emails. You might even want to use parts of someone else's script in your own Ruby files. So how can you include code external to your .rb file in the programs you write? Ruby offers solutions in the form of the load, require, and include methods. Let's talk about require first. The require method is one of the most commonly used ways to include other files into Ruby code. So let's say a coworker has written a simple method that prints the contents of an any array as a string, separated by commas. This method is saved into a file called superusefulmethods.rb, which looks like this. This snippet uses some code that you haven't seen before in the form of the join method. Join is a method that some objects, like arrays as you can see in this case, can use to combine the contents together into a single string based on some delimiter. In this case, the delimiter is the comma symbol. If you're working in another .rb file and want to use the comma joiner method your coworker has created, You can pull it into your file using the require method. Once you load in superusefulmethods.rb with require, you can use any of its code as if it were written out in your own file. You might also have noticed that although we didn't need to add the .rb file extension to the string in our require statement, we did prefix it with the // characters. This indicates the current working directory from where we're executing the script. So how does require find the file we're looking for? First, the require method will stick the .rb extension to the end of the file name and try to resolve it as an absolute path. Remember that absolute paths are just the full path to the file in a file system. If the file name isn't an absolute path, then Ruby will look through a list of directories specified in the special load path variable. If it still can't find the file, then it will raise an error. Using the / characters means that we're giving the method an absolute path, so Ruby knows directly where to look, since the current working directory isn't one of the items listed in the special load path variable. As an alternative, you could use the require relative method, which looks for the file name relative to the file containing the require relative statement. Let's say you have a directory called scripts with two files, one called superusefulmethods.rb and another called masterscript.rb. Masterscript.rb contains this code. Although the superusefulmethods file is not in the load path, it can still be specified as a relative path. This is because require relative will look for it in the same directory as the currently running script, the masterscript.rb file, which is scripts in our example. Super useful, don't you think? Along with require and its friend require relative, Ruby also gives us the load method. Load also includes code and external .rb files into your program, but it needs the full file name including the .rb suffix to do it. The biggest difference between load and require, though, is that code imported with the load method will be reprocessed each time load is used, while require keeps track of what it has imported and then makes sure it's only done once. If you have a file called zoomzoom.rb, which contains the statement, using require multiple times will only result in the put statement being called once, since requires doesn't reload the external code more than once. On the other hand, using load will reprocess the external code each time. In their day-to-day work, programmers don't usually need the functionality that comes with load. They pretty much stick with require and require relative. Load can come in handy if a file you're using in your script has changed since you launched the program, like a data file for use in a test. But these situations are pretty rare. When in doubt, just stick with require. Now that we know how to import and use code written in other files, let's check out what kind of mechanism Ruby offers for organizing that code. We've already learned that you can use methods to group together logical blocks of code, and that these methods can be defined in classes and used on instantiated objects. But what if you had a bunch of loosely related methods that didn't really fit well into a class, or a set of classes that you needed to group together themselves? Don't worry, there is a solution. To do this, Ruby provides an abstraction called a module. Modules can be used to organize classes, methods, and other data together in a structured way. The syntax for creating a module looks pretty similar to the syntax for creating a class, and the names of both must start with an uppercase letter. But it's important to keep in mind that modules are not classes. This means you can't create instances of a module. Here, we've defined a simple module called Spain with both a class and a method in it. Notice that the name of the method uses dot notation to indicate the relationship between the method and the module that contains it, and you can use the same dot notation to call it. The syntax to represent the class uses this operator, which lets you access items and modules like the food class. Methods do provide organizational structure to code, but the real power comes from the other two benefits they provide to programmers: the ability to create namespaces and mixins. We'll learn more about namespaces in the next video. So what's a namespace? Take this example. If you were writing a script to communicate with both Spanish and English speakers, you might put all of the code related to the Spanish language in a file called spanish.rb, and all the code for the English language into another file called english.rb. You need to greet speakers of either language, so both files contain a method called greeting. Remember that in Ruby, the require method is used to load code contained from another file into your program. So what do you think would happen if this snippet was run? Ruby will actually use the method defined in the last file that was loaded, so you'll get the greeting printed in English and only have access to that version in your script. This type of situation is called a naming collision or naming conflict and can introduce subtle, dangerous bugs to your code that can be hard to find and fix. And who wants dangerous bugs in their code? Or anywhere, really. Not me. To avoid these kinds of naming collisions, you can use modules to provide namespaces. We've already seen namespaces in action. Think back to the module we named Spain. We use dot notation syntax to call methods inside the module, like module.method, and the double colon syntax to instantiate an object of the food class. The name of the module is included each time we want to access some property of the module, which makes it clear exactly what we want. If we rewrote the english.rb and spanish.rb files like this, we could make sure both greeting methods could be used without ambiguity. You can use modules to write usable, organized code and prevent clashes between them with namespaces. Because no one wants their names to clash, am I right? Hopefully by now, you're feeling organized and collision-free thanks to Ruby's modules. But they've got one more useful property we haven't talked about yet, the ability to mix in module functionality into your classes. In Ruby, it isn't possible to inherit from multiple classes at the same time. For example, the apple class can't inherit from both the tree and fruit classes at once. This means that it can be hard to share functionality across disparate or unrelated classes, since it may not make sense to place that functionality in the inheritance chain of a class where it doesn't really fit. This is where modules come into play. Modules can themselves be included into other classes through a feature called a mixin. You can use mixins to extend the functionality of a class with all of the methods that you define in the module. For example, it may be useful to have two classes, one which represents humans and another which represents pandas. As your scripts become more powerful, they'll probably need to make use of additional concepts and the interactions between them, which means you'll be adding more than one class. It probably doesn't make much sense for them to inherit from one another, but if you wanted to add some more functionality to both of these classes, you can mix a module into each of them. If you wanted to give them both the ability to do Kung Fu, which would be awesome, you might write something like this. As you can see, you mix a module into your classes by using the include keyword. When mixed in, the module's methods are made available to all of the classes that include them. This means that when we create objects using the person and panda classes, we can call the Kung Fu method provided by the martial arts module from each of them. It's a 1-2 punch, get it? You might have noticed a slight difference in the module method declaration from our namespace example, where before the methods were prefixed by the module name. With mixins, the included module is already restricted to the calling class, so you don't need to prefix the method with the module name when calling it. These methods are designed to be used only from the instances of the classes that mix them in. Hope that doesn't mix you up. Remember our earlier example of the two scripts that needed to send email messages? Now we know that the classes and methods that make up that email code can be organized into one or more modules. We also know that we can import them into other scripts using the require keyword. This combination of the ability to collect code and then use it elsewhere is central to the concept of the programming library. A library is a collection of code, likely organized into multiple modules, that can be reused by any program that imports it. Multiple programs that have no relation to one another can use the code in a library to accomplish tasks. Using libraries means that the work of one programmer can be used by many others who don't have to re-implement the functionality found in the library themselves in their own code. Sharing is caring in the world of coding. Most programming languages come with a standard library, which provides code to accomplish many common and even some uncommon tasks. Ruby's standard library, which is really a collection of multiple libraries, comes built in along with your installation of the language. It provides a programmer with code to do a wide variety of tasks. Libraries exist to do anything from reading and working with CSV files to sending emails or manipulating the system log directly. The full list of libraries available can be found in the next reading, along with documentation on how to use them. Along with the benefits of using libraries we've covered already, collections of code like the Ruby standard library can benefit from general reliability. In order to make it into the standard library, a piece of code must be well tested, exercised, and generally written in accordance with a high standard of code quality. So you know you're getting the best of the best. To get a better idea of what's in the Ruby standard library and how we might use it, let's check out one of the libraries it provides, called NetHTTP. With this library, you can send requests to web servers using the HTTP protocol and retrieve web pages similar to how your browser works under the hood. Including the library in our script is as simple as writing NetHTTP is a pretty neat library since it lets you send HTTP requests to servers in a similar way to your browser. Since it's part of the standard library, the NetHTTP code file is in one of the directories in the special load path variable, where the require method can locate it. Now let's use it to download the HTML for the Google homepage and print it to the screen. This can be accomplished with this line of code. This syntax should look pretty familiar now. Here we specify that we want to use the get method of the NetHTTP module, which takes the host and path as arguments. The double colon symbol indicates that we are accessing the HTTP class in the net module, and the dot notation lets us know that get is a method defined in that class. As you can see, using a library can be really helpful. Even without the knowledge of the low-level details, we were able to create a simple script to send requests to a web server in a couple of lines. Easy peasy. Using the documentation can be super helpful when working with the standard library. Check out the page describing NetHTTP, and you'll see a list of the files, namespaces, and methods it defines, along with examples of how to use it. Ruby's standard library is pretty useful and can help you accomplish lots of different tasks, but it isn't all-encompassing. Luckily, if the standard library doesn't provide the functionality you want, there are other places to look. An even larger collection of libraries exists and can be accessed through the Ruby's Gems package management system. The concept of package management may be familiar to you from a previous course. You might remember package management systems like the Advanced Packaging Tool for Ubuntu or the Chocolatey Software Management System on Windows. Chocolate. Ruby Gems is similar to these, but instead of being used to distribute platform-dependent software, it distributes Ruby programs and libraries. Ruby Gems uses a standard format for distributing packages, called, not surprisingly, the gem. These gems are hosted in a gem repository and can be installed for use by your scripts through the gem command line tool. Although you can create your own private gem repository, programmers will usually use gems available on the public repository. The public repository has over 130,000 packages in the form of gems. You can browse these at the Ruby Gems site and install them using the gem tool from your terminal. That's a lot of gems. To use this package management system, you first need to have Ruby Gems installed in your computer. Any version of Ruby after and including version 1.9 comes with Ruby Gems already. But if you're using an earlier version, you can install Ruby Gems using the instructions linked in the supplemental reading. Once you've got Ruby Gems installed, you can use the gem command line tool to interact with it, and you're good to go. Let's say you wanted to create a program that would be able to send ICMP packets to computers on our network, like the ping command does. Browsing the Ruby Gems public repository turns up a library that could be useful, called net-ping. To install this library, we can use the gem command from the terminal. Once the gem has finished installing the net-ping library, we can use it just like we did with the code from the standard library. In this example, we use the net ping library to send a ping request to the loopback or local address and print the result of the request. If the host has responded, the ping method will return true. Otherwise, it will return false, and we don't want that. You can find RubyGems packages in a few different ways. We've already seen that you can use the RubyGems website to search through the available gems in the repository. To get a list of the gems you've installed on your computer locally, you can issue the gem list command. You can also use the gem command line tool to query the public repository. For example, to get a list of all the packages available, you could run the following. This might be a little too much information though. So if you have a rough idea of what you're looking for, you could perform a more targeted search based on the name of the gem. Although browsing the full list of gems is one way to find new libraries, given the amount of available packages, it's usually a good idea to have a starting criteria in mind to help you narrow down your scope a little bit. A little research using the search engine of your choice is a great way to get an idea of what kind of libraries are out there. You know where you can do that research? In a library. That's pretty meta. While you're there, you might want to study for the quiz that's coming up right after this. In this lesson, we'll check out some of the ways you can use Ruby to interact with file systems. As an IT support specialist, it's likely that you'll usually need to manipulate files and directories on a computer in some way. The ability to perform actions like reading or writing files, renaming directories, or copying data from one location to another can be super useful. Automation can also be a big help if the number of files or directories you need to work with is large. We learned in previous videos that file systems are the way that operating systems like OS X, Windows, or Linux organize and control how data, usually on a disk, is stored and accessed. Data is saved in files, which are located in containers called directories or folders. File systems are commonly organized in a tree structure, with directories and files nested under their parents. The location of a resource, like a directory or a file, within that structure, is given by its path. Remember that when we refer to an absolute path, we're talking about the full path to the resource in the file system. On the other hand, relative paths use only a portion of the path to indicate the location of a resource relative to another. This is usually the current working directory or the current file, as with the require relative method. Relative paths are a kind of shortcut that you can use to avoid writing out the full file path, but keep in mind that they only make sense relative to another location. In the upcoming videos, we'll look at how to manipulate and navigate the file system in your scripts, and how you can use Ruby to handle files. Ready for more? Let's do it. So far, we've seen how you can get data into and out of your scripts by accepting user input at the terminal, like with the gets method, and printing it to the screen, like with the puts or print methods. But the terminal and screen are not the only ways of working with data in a program. Your script can also use files to read in large chunks of data, or write out the results to a location on disk. It's pretty cool, right? Working with files is such a common and useful task in programming that most languages build the ability into their core set of features. Ruby is no exception, and it provides this functionality in the form of the file class. You can use instances of the file class to do all sorts of things with files, like reading, writing, moving, or deleting. For example, to open, read, and display the contents of a file in your computer called birthdaysong.txt, you could write this code. In this example, a new file object, also known as a file handle, is created and assigned to a variable called file. The argument we pass the file class when creating the object is the name of the file. In this case, we assume it's in the same directory as the script we're running, but you could just as easily give an absolute path as the argument to open files in other directories. We then print a single line of the file to the screen using puts and file.gets, and close the file using the close method. This open, use, close pattern is a typical way of working with files in most programming languages. It's a good idea to close files after you've opened them for several reasons. First, while a file is open in your script, it's very likely that your file system will lock it down, making it unusable by other programs or scripts until you're done with it. Second, there are only a limited number of file descriptors you can create before your file system will run out of them. Although this number might be high in practice, it's possible to open lots of files, in a loop for example, and deplete your file system resources. Third, leaving open files hanging around can lead to race conditions, which occur when multiple processes try to modify and read one resource at the same time. Everyone finishes last in a race condition. You might think that keeping track of what files you've opened and remembering to close them is annoying, and the creators of Ruby would actually agree. Instead of creating a new file object explicitly, working with it, and then closing it, the file class provides some shortcuts you can use. One of them is the open method. The equivalent of writing our previous birthday example using the open method would look like this. As you can see, the open method can be used in conjunction with the code block, which contains the work that you want to do with a file. In this case, we want to take a line of data from the file and print it to the screen, which is what puts file.gets does. As a bonus, if you use open within a block, then Ruby will automatically close the file, so you don't need to remember to do so yourself. That's one less thing to worry about. Both ways have their own benefits. The open method with a block is a good way to open a single file, perform some work, and then close the file automatically at the end of the block. On the other hand, if you create a new file handle, you can then use it in other places in your code that aren't restricted to a block. Just don't forget to close it when you're finished. In our file reading examples so far, we've only looked at the first line of the file. Of course, we can examine the rest of the file's contents too. To read and process a file line by line, you can make use of an iterator, something we learned about in the last module. Check out this code. By using the open method in conjunction with the each iterator and a code block, we're able to loop through the birthday song file line by line and print its entire contents. Instead of processing a file line by line though, you can also read it into an array in one go. Each line of the file will be stored as an element of the array. To demonstrate, check out this line of code. This line would produce an array with each line found in the birthdaysong.txt file as a separate element. Although this can be a useful shortcut, be careful when reading the entire contents of a file into your program. If the file is super large, it can take up a lot of your computer's memory to hold it and lead to poor performance. Large files are more efficiently processed line by line, and efficiency is key. Now that you know how to read files in Ruby, the syntax for writing to them probably won't seem too strange. You can see that we're using the open and block pattern we talked about before to open a file called novel.txt. Also notice another familiar friend in the form of the puts method. Hello, friend. We've used puts in the past to display output on the screen, but when it's called on a file object, it writes that output to the file instead, which is pretty handy. The second argument to the open method is new though. So what does that W mean? As it turns out, the file class has several different modes in which it can open a file. A mode is kind of like a file permission, which governs what you can do with the file you've just opened. Since it's the default, we don't have to explicitly pass in R as the second argument when we just want to read a file. But writing is a totally different story. The W character tells the file class that we want to open the file for writing only. If the file doesn't exist, then Ruby will create it. If the file does exist, then its current contents will be overwritten by whatever we decide to write using our script. Opening a file in write-only mode means you can't read its contents, and any attempt to do so will result in the interpreter throwing an error. The file class supports several other modes of opening files, like read-write and append. You can find the full list of them in the Ruby documentation. Check it out in the supplemental reading, and I'll see you in the next video. If you need to work with files in your script, odds are that you'll also need to be able to handle directories. As with files, Ruby provides a built-in class with which you can create, delete, and browse the contents of directories. This is done with the dir class. Here's the rundown. Remember when we talked about the current working directory and its importance when determining the location of a file specified using a relative path? To check the current directory a Ruby program is executing within, you can use the pwd method. If you use a Unix-like system, you may spot that pwd is the name of the command that does the same job. You can change directories too in your program by using the changedir command, provided with the argument you'd like to change to. Just like the file class, you can use either absolute or relative paths as the arguments to methods of dir. The syntax for creating a directory is what you might expect, as is the syntax for deleting one. But using the delete method comes with a hitch. If you try and delete a directory that still has files in it, you'll get an error, and you don't want that. You need to first delete all of the files and subdirectories a directory might contain before you'll be able to delete it. To help with this, there are a few techniques that you can use to look at the contents of a directory. First, the dir class provides a method called entries. This method will return an array, each element of which will be a file or subdirectory within the current directory. You'll also get the dot and dot dot characters as elements of the array, which are used to indicate the current directory and its parent respectively. Dir also provides a shortcut to iterate through each element of a directory, with the for-each method. Sure, this is handy, but the entries and for-each methods only look at the contents of the current directory. They don't tell you about what a given subdirectory might contain. What if we wanted to get a listing of all the directories and their subdirectories all the way down the tree? For example, say we had a directory called oak root directory, with this directory tree structure. dir.entries oak root directory would get us an array with the oak branch directory and oakleaf1.txt entries. To get at the oakleaf2.txt and 3.txt files, we need to go deeper. This is where the glob method can help us. The dir.glob method can take a string pattern as an argument and use that pattern to match items inside a directory. Using the ** characters as the first part of the pattern tells Ruby that you want to search the directories recursively, which means that it will look in all the directories in a tree, no matter how many there are. You can use the second part of the pattern to look for more specific things. The * symbol, commonly referred to as a wildcard, will match anything. So to get the entire contents of the oak root directory, you could write this code. And to match only the files ending in .txt, you could change the wildcard pattern so that the glob method will find anything that ends in .txt. Now that we know how to read, write, and create files, and major kudos on that, let's look at some of the other cool stuff that the file class can do. Using Ruby's file class, you can accomplish pretty much all of the same tasks that you can normally do when working with files. You can change a file's permissions, delete, and rename files automatically. To delete a file, you can use the appropriately named delete method from the file class. Each argument to the delete method is the name of a file to be deleted. If you wanted to delete many files, you could even store their names in an array and iterate through them, calling delete on each file. Pretty cool, huh? Renaming a file can be done just as easily with the rename method. The first argument to the rename method is the old name of the file, and the second is the new. You can also use methods in the file class to get information about a given file. If you wanted to see how big a file is, you could use the size method to return the file size in bytes. To check what time a file was last modified, the mtime method would come in handy. Both of these methods take some functionality available to you from system commands like ls in Unix-like OSs or dir in Windows, and provide them to your scripts. One particularly useful method that the file class provides is the exists method. Remember that methods suffixed with a question mark return a Boolean value. You can use this method to check if a file exists before trying to do some work on it. Exists can be used for all kinds of things, like verifying a log file is present before trying to write to it, or checking that a given file hasn't been created yet so you don't overwrite it. Another feature that the file class provides is the ability to work with relative and absolute paths. In our examples, we've been using relative file names without having to specify their full paths. In some cases, you may need to exactly specify where a file is in order to work with it in your script. This is where the expand path method can be useful. Given the name of the file, the expand path method will turn it into an absolute path. Ruby will use the current working directory, from where the script is being run, to start looking for the file and construct the full path that identifies it. Although starting the search from the current directory is usually good enough, you can also supply the starting point yourself. Sometimes you might just want the name of a file and don't care about its extension. Or maybe you're only interested in the name of the directory that contains the file. The file class provides the base name and dir name methods to accomplish these tasks. If you've got a file called index.html in a directory called website, evaluating this code produces the following. Keep in mind that the dir name and base name methods are actually just operating on the string that represents the name of the file or directory. Neither has to actually exist. We'll talk more about directories in the next video. I'll see you there. The file and dir classes have all sorts of useful abilities that we don't have time to cover here. We hope that these examples have given you some idea of the things that you can do with files and directories in your scripts. Feel free to experiment with these classes and read up on their documentation at the Ruby website. Okay, you've got a quiz coming up, so good luck. I'll see you in the next video. We've covered a lot of content. Awesome job so far. We've seen a bunch of ways of getting information into and out of our scripts. We know that we can read and write to files and accept input from the keyboard and print it to the screen. But what exactly is going on behind the scenes when we do this? How does a Ruby program connect to both the screen and the keyboard? I/O streams are the basic mechanism for performing input and output operations in Ruby scripts. You can think of these streams as pathways between your programs and their sources of input, like a keyboard, and output, like the screen. I/O streams aren't just for Ruby programs either. When you run a system command on your terminal, I/O streams are also being utilized to connect that command to the terminal input and output. This way you can see the results of the command, or even pass its data interactively, if it supports that functionality. In this lesson, we'll dig a little deeper into the concept of I/O streams, especially zoning in on the standard or default streams that are found in most operating systems. We'll see how to manipulate and redirect those streams, and how to use them when writing scripts. Most operating systems supply 3 different kinds of I/O streams by default, each with a different purpose. First, the standard in stream, commonly referred to as stdin, is a channel between a program and a source of input, usually in the form of text data from the keyboard. When you use the gets method to accept user input in a Ruby script, you're using the stdin stream. Remember that the chomp method just cleans up a string, in this case, one read from standard in. Second, the standard out stream, or stdout, is a pathway between a program and a target of output, like a display. Standard out generally takes the form of text printed to a terminal. This is the case when we use the puts method to print information to the screen. The last type of pre-made I/O stream is called standard error, or stderr. Standard error does display output like standard out, but is used specifically as a channel to show error messages and diagnostics from the program, usually to the screen. If you've ever run some Ruby code and gotten an error, then the error message was probably printed using the standard error stream. Keep in mind that these I/O streams aren't restricted to just Ruby programs. When you use the cat system command to display the contents of a file on a Unix-based system, those contents are printed to the terminal using standard out. And when you see an error using an unsupported flag with the ls system command, that error uses the standard error pathway to the terminal output. Standard in doesn't always have to be provided to a script by the keyboard at a text terminal. And standard out or standard error don't always have to be shown on the screen. An important property of these I/O streams is that they can be sent to all kinds of different destinations through the process of redirection. To redirect the standard output of a program to a different destination, you can use the greater than symbol. Like the W file mode used by the file class we talked about in the last lesson. Each time you perform a redirection of standard out, the destination is overwritten. For example, consider this Ruby program, which just prints a single line of text using the puts method. If we were to run this program without redirection, the text would be sent to the display using standard out as normal. But if we use the greater than character to redirect the output like this, something else happens entirely. When this is run, the standard out from standardoutexample.rb script is redirected to a file called newfile.txt. If that file doesn't exist, it's created. If you were to look at the contents of the newfile.txt using the cat command, you'd see the following. If you wanted to append the redirected standard out to the file, you could use the greater than sign instead of a single greater than. Standard in can be redirected too. Instead of using the keyboard to send data into a program, you can use the less than symbol, like this. In this command, the file sumtext.txt is sent through standard in to the textprocessor.rb script, which can then perform actions on its contents. It can also be super useful to redirect standard error to capture errors and diagnostic messages from a program. This can be done using the two greater than characters in a similar way to how we redirected standard out earlier. Here, the 2 represents the file descriptor of the standard error stream. You can think of a file descriptor as a kind of variable pointing at an I/O resource, in this case, the standard error stream. You may want to capture all of the output of a program, including both the normal operating output and any error messages that are produced. This can be done using the ampersand greater than symbols, in this way. With that command, any output, including errors, will be sent to the alloutput.txt file. Like using the regular output redirection operator greater than, this will overwrite the file's contents each time and create a new file if one doesn't already exist. Last thing, it might come in handy to know that you can even redirect I/O streams to other streams. This is a very cool feature. So, let's say you wanted to redirect both standard out and standard error as above, but instead of overwriting the file, you want to append to it. You could do this with this command. This probably looks a little complicated, but since redirection is executed from left to right, we can read through it and figure out what's going on. First, we run the buggy program.rb script and redirect its standard output in append mode to the alloutput.txt file. We've seen how to do this before. The new part is when we redirect the standard error stream, as represented by 2 greater than, into the standard output stream, which is represented by the file descriptor 1. The ampersand symbol indicates that we want to redirect to a stream, not a file. Taken together, we can say that we're redirecting standard error to wherever standard out is going. In this case, it's the alloutput.txt file in append mode. Next up, pipes, pipelines, and more. Along with the techniques we've seen so far, there's another powerful way to perform I/O stream redirection called piping. Using pipes, you can connect multiple scripts, commands, or other programs together into a data processing pipeline. Pipes connect the standard in of one program to the standard out of another, which means you can pass data between programs, feeding the output of one to the input of the next. Pipes are represented by the pipe character, like this. In this example, the output of the ls-l command is connected to the input of the less command, which is a terminal paging program. This particular example can be really useful when you want to look at the contents of a directory containing many files. The list of files generated by ls is piped to less, which displays them a page at a time. Connecting more than 2 programs is also possible with pipes. In this example, we first search for some string in the system log file using grep, which is a file searching command. We then pass any results we find to the sort command through a pipe. The sorted results are now passed to the unique command on its standard in stream, whose -c flag prefixes each unique line with the number of times it has occurred. This output is finally passed through pipe to the sort command once more, The results are sorted numerically from least to most as directed by the -n flag, and prints the final output to the terminal display through standard out. In this way, we can get a sorted count of issues related to some string from a log file, using different system commands chained together with pipes to perform different parts of the data processing pipeline. You can use your Ruby scripts and pipelines too. Ruby can read data from standard in using the argf class, which is part of the core language. Let's say you had a text file called haiku.txt with these contents, which you wanted to capitalize using a Ruby script. Although we could read in haiku.txt with the file class, we could also use the argf class to process each line from standard in. If we wrote this code to capitalize our RB, we could use it in a pipeline like this. The cat command will send the contents of the haiku.txt file to standard out, which we then redirect to our script using a pipe. The capitalizer script uses the argf class and an iterator to loop through each line of standard in and prints the capitalized version to standard out. We should also call out that we didn't need to use a pipe to get the contents of the haiku.txt file into the standard in of our script. Instead, we could use the standard in redirection operator we saw in the last video, like this. With a little practice, creating pipelines is a fast and powerful method, performing many system administration tasks. When a system command doesn't exist with the functionality that you need, you can write a Ruby script to fill the gap and include it in your pipeline. Understanding how to redirect I/O streams can come in handy in many situations when writing code. We'll see an example of this later in the next lesson on subprocesses. But first, another quiz. You got this. But even if you don't, just review the material until you get more comfortable with this stuff. We saw in previous lessons how Ruby's built-in file and dir classes can give your scripts the ability to work with files and directories. We also saw how we could use their methods to get information about the underlying system, like using dir.pwd to get the current working directory. In our first lesson, we went through an example of using the netping Ruby gem to add the ability to ping other computers in our scripts. Having these abilities baked into a class or package is super useful, but what if you needed to run a system-level command like ping directly for some reason? What if you needed to access a terminal command that didn't have a library or gem counterpart available? Sometimes it's easier or faster to use a system command as part of your script to accomplish a task, or get some functionality that just doesn't exist in the Ruby libraries or gem repository. For these cases, Ruby provides a few ways to execute terminal commands programmatically in your scripts using subprocesses. We'll learn all about these in the next video, so get ready to submerge yourself into some subprocesses. There are a number of ways to use system commands in a Ruby script, but they mostly involve creating a child process or subprocess. When you run a Ruby script, you can think of the currently executing script as the parent process. When the code in your script executes an external command, a child process is created. To run the external command, a secondary shell is created in a child process, which then executes the command. Remember from the operating systems course that a shell is a command line interface used to communicate with your operating system. While the parent process, which is your script, waits on the subprocess to finish, it's blocked. This means that it can't do any work until its child finishes. After the external command completes its work, the child process exits and the flow of control returns to the parent, where the script continues its normal execution. This might all sound a little confusing. One way to run an external command in Ruby, in a subprocess, is to use the system method. This method takes the command name as an argument and returns either true if the command succeeds, or false if the command has failed. To run the system command chmod to make a file world readable, writable, and executable from a Ruby script, you could execute this code. The first argument in the system method indicates which command should be run, and subsequent arguments are treated as command line flags. This code is equivalent to running the chmod command from your terminal, like this. The system method will return true when the command that it's running returns a 0 exit status, and false if the exit status is non-zero. Remember that in Unix-like operating systems, the 0 exit status of a child process usually indicates success, while a non-zero status generally indicates some kind of failure, with the number returned providing more information. The Ruby system method is useful if we just want to run a command and determine whether or not it was successful. This can come in handy for system commands without much useful output, like chmod. But if we wanted to capture the output of some external command, we need a different strategy. And we'll learn all about that in the next video. See you there. Welcome back. Another way that terminal commands can be executed through a subprocess is by wrapping that command in backticks. When external commands are executed through backticks, their output is returned through the standard out stream instead of their exit status. On a Unix-like system with the ls command installed, you could execute this code to get a listing of the current directory from a Ruby script. Similar to the system method, Ruby creates a new child process and uses it to execute any command specified between the backticks. Once the command finishes running, the output is returned as a string. In our backtick example, we saved the output to print it, but we could just have easily used that output in another portion of our script. Although the exit status of the external command isn't returned, we can actually still determine whether or not the command executed successfully. This is because the return code of the command is automatically saved to a special variable represented by $?? This variable stores the status of the last executed child process, which in our example would be ls. This variable has a success method defined on it, which can be used to determine if the last command was successful. You can also use the %x character as an alternative to backticks. It will return the output of the command and set the $? variable too. To run a command using the %x syntax, just wrap the command in a set of delimiters. Parentheses are commonly used like this. Using backticks, or the %x syntax, along with the $? variable, is an easy way to execute commands and get both their output and return codes. But it does have some drawbacks. For example, if we run this command on a terminal in a Unix-like system, we'll get an error as there's no command called lazy on our system. But what happens if we run the same bad command from a Ruby script using backticks? Yikes. The error was printed to the screen, but the whole script exited and neither of the put statements were evaluated. This is because when an error occurs in a subprocess we've generated using backticks, it gets returned to the parent process. If the parent process has no way to handle the exception, it can cause the parent to exit. This is different than our example of the system method, as you can see here. If an exception happens with a child process created with system, that method just gobbles up the exception and returns false to indicate that it failed. We can't just store the error in the output variable and continue to execute the rest of the script. This is because when we use backticks to run subprocesses in Ruby, only the standard out IO stream is captured and returned. Remember that failure messages use the standard error stream. But don't worry, there's a way around this. Our friend redirection. If you remember from our last lesson, you can redirect standard error to the same place as standard out by using the 2, greater than, ampersand, 1 symbols. We can do this in our Ruby scripts also. See how the second put statement has executed and printed its text to the screen, as we've redirected the error stream to the output stream. This will collect the error text on standard error and redirect it to standard out to let the program continue. Although it works, this solution isn't ideal since it means we have to remember to put the magic 2 greater than ampersand 1 string into each of our backtick statements. It also means that if we don't check the status of the command using the $? variable, we may be hiding failures in our scripts. This is an example of silent failure. As we already learned, silent failures in automation are a dangerous combination that should be avoided at all costs. As we learned in the last video, silent failures can be dangerous for automation. Don't worry though. You should know by now that Ruby always finds a way. In this case, Ruby provides a solution to get both the standard error, standard out, and return code from a finished subprocess without having to resort to redirection. Because Ruby is a boss and never lets us down. Enter the Open3 module from the standard library. Since Open3 is a module in the standard library and not built directly into the Ruby core language, we'll need to include it in our scripts using require, as we saw earlier. This module has a very handy method called capture3. Let's see it in action. Awesome, right? Similar to what we saw with the system method, Open3's capture3 method takes in a command as its first argument, followed by whatever flags we might wish to pass to it. This piece of code is using a technique we haven't seen before though, called multiple assignment. Multiple assignment is a super cool Ruby feature that lets you assign values to multiple variables at once, all in the same line. In this case, capture3 returns 3 values in this order: the standard output obtained from running the command, the standard error, and the status. To receive these values, we've created the stdout, stderr, and status variables, which all get filled when capture3 returns, which is pretty awesome. We can also see what happens when the command in the subprocess run by capture3 fails. As you can see, capture3 method from the Open3 module gives us easy access to the return status, like the system method did, but it also lets us look at the text produced by running the system command, like we got with backticks. It also swallows the error if the system command fails, but lets us easily save and examine the failure output from standard error. Not too bad for a single method, not bad at all. The ability to interface with the underlying system directly in your Ruby scripts through subprocesses and terminal commands can be really useful, especially if you need to accomplish a specific task quickly. Sadly, it comes with some drawbacks. Using these system-level commands builds assumptions into your scripts about the infrastructure your automation will be running on. This can lead to unexpected effects or failures if those assumptions change. Let's take a closer look. These kinds of assumptions can change in many ways. What happens to your automation if the flags for a terminal command change and your script continues to use the old ones? What happens if you switch operating systems from Ubuntu to Windows? Will your scripts fail outright or succeed in unintended or even harmful ways? Any change to the system or the external commands your scripts utilize is an opportunity for breakage, which can sometimes be subtle and hard to detect. If you're automating a one-off, well-defined task where the speed of developing the solution is the biggest requirement, then using system commands and subprocesses can help out a ton. If you're doing something more complex or long-running, it's usually better to use one of the libraries, modules, or gems provided by Ruby. Before deciding to use subprocesses, check the standard library and gem repository to see if the task you want to accomplish can be done with native Ruby. In this lesson, we've explored some of the ways that you can use external terminal commands to interface with the underlying system in your scripts. We focused on 3 methods of accomplishing this, each with different positives and negatives. Some simple rules of thumb for deciding on the right tool for the job are here. If you want to run a system command and only need to know whether or not it succeeded, use the system method. If you want to quickly run a command and capture its standard output, use backticks, as long as you're okay with the script failing if the command doesn't succeed. If you need to capture both standard output, standard error, and the return status, import the Open3 module and use the capture3 method. It's worth noting that there are other ways to run subprocesses in Ruby that we haven't covered in this lesson. For example, you can use the fork method to run a command in a separate process that doesn't block the execution of the parent. This way, the rest of your code can execute without waiting for the child process to complete. If you're curious, you can check out the process section of the Ruby documentation. You can also find some great tutorials online with a little research using your favorite search engine. And now it's quiz time, so good luck. I'll see you in the next lesson. By now, you've seen how to extend the usefulness of your scripts by importing external code and using libraries. You've performed I/O operations with files and manipulated directories, run external commands using subprocesses, and constructed I/O pipelines to process data. Combined with the coding techniques introduced earlier, you've learned a lot about the tools you can use to create automation through scripting. Quick timeout though. Look at all that you've learned already. Really awesome work. Okay, now let's forge ahead. In this lesson, we'll pull together what we've learned so far to write a script from the ground up. Yep, our very own script. We'll start with the task that we want to accomplish, do a little research on the subject, and plan out what we might want our code to look like. Then we'll dive into coding it up. At the end of the lesson, we'll have a working script and hopefully demonstrate lots of the techniques we've seen in our examples. We've got a lot to cover, so let's get started. Imagine you're an IT support specialist at a medium-sized company. Your manager wants to do a security audit of the computers on the internal network and needs a list of all active IP addresses which are connected to it. She gives you the task of scanning the network and compiling this list of active addresses. To determine if a computer is connected to the network, you know that you could run the ping command to send a packet of data to an IP address using the Internet Control Message Protocol, or ICMP. The active computers would respond to the ping, and you could call out their IP addresses to compile the list. This seems like a good solution, but pinging all of the addresses on the network by hand would be a painful task. Consider that a typical /24 network has 254 possible addresses in it. If it takes 10 seconds to type out a ping command, then it would take a total of 42 minutes to ping each and every address on the network by hand. You would also need to ensure no addresses were missed, so keeping track of the IPs that have been tested would be important. If you think that this is a task that is ready for automation, you'd be right. Good job. So we need to write a script to automatically ping each IP address on the network. We should also probably generalize the script to be used on any network. Why? Because if the infrastructure changes later, like by adding another network or changing the setup of the current one, our script could adapt and still be useful. This example of using ping to scan a local network is for illustrative purposes. There are several alternative methods by which this list of IP addresses could be generated. Other options might include viewing the active DHCP leases on the network, like by looking at the var lib dhcp dhcpd leases file in a Unix-like system, or by running the netsh command on Windows. The scan itself could be performed with a specialized tool like Nmap. Some machines on the network might also filter out ICMP packets, which means that ping wouldn't be able to discover them. Now we have an idea for a potential solution, and know that we'd like to use automation to accomplish it. Before we get into coding, let's think about the problem a little bit more. One of the questions we should answer before writing any Ruby is, how big is the network? If we want to ping each address on the network to see if it's up, then we need to know what addresses we should be pinging. Remember from the bits and bytes of computer networking course earlier, that you can retrieve local network information from your computer through the ipconfig command on Windows or the ifconfig command on a Unix-like system. In our example, let's say that running one of these commands tells us that the IPv4 address of our local computer is 192.168.1.10, and its subnet mask is 255.255.255.0. Also remember that you can take a subnet mask and an IP address from that subnet, and use the information to calculate the address range of the network. With this information, we could write a script that calculates the full range of addresses. But your Ruby senses might be tingling at this point. It seems entirely possible that someone may have already written the code to do this. And yep, a quick search of the Ruby standard library turns up a promising result in the IP adder class. Its purpose, according to the docs, is to provide a set of methods to manipulate IP addresses. Searching through the methods available in the IPAddr class, the toRange method seems like it might be particularly useful for our case. If we give the toRange method an IP address and network mask, it can calculate the range of the network. By looking at the documentation for the IPAddr class, we can see that the new IP address objects can be created from an IP address representation of address/mask. This means that we can use the information we have to create a new IP address object in the form of 192.168.1.10/255.255.255.0. Now we know that we can compute the range of IP addresses in the local network by using the IPAddr class from the standard library, along with the information that we receive from our local computer. We also know from an example in our lesson on libraries that there is a Ruby gem called net-ping, which adds the functionality of the ping command to our scripts. If we didn't already know this, we could have performed a search in the public gem repository to find it. With this knowledge, we can get to planning our script, which we'll cover in our next video. See you there. Now that we know what external libraries and gems will be useful in our script, we can start planning it out. As we talked about in the last lesson, methods are a great way to organize code into logical groups of functionality. To split up our code in this way, we might start by thinking about the kinds of subtasks that need to be performed, and how we could group them into methods. First, we know that we'll need to compute the range of addresses in the network in order to make sure that we can scan them all. This will involve using the IPAddr class to create a list of addresses we need to scan, which could be stored in an array to later iterate over. We also know that we'll need to use the net-ping library to test each of these addresses in order to see if they are up. Storing the active addresses for later use seems like another task for an array. Finally, we'll want a way to get this information out of the script. Printing it to the screen would be one way, but since a list of addresses was requested, it would be even better if we could save them to a file that could be emailed or printed. Given all this, it seems like the script could be split into 3 methods. One to calculate the address range, one to test each address, and one to save the active addresses. I think we've come up with a pretty solid plan. Now let's try writing the script out. Let's start by creating a new file called scanner.rb. We know that we'll need to include some external code for our script to work, so the first few lines should consist of require statements to import those libraries. In order for the net-ping library to work, we first need to install the net-ping gem using the gem install net-ping command. Next, we can define the function which will calculate the address range using the local IP and subnet mask we retrieve from our computer. This method will take an IP address and network mask as parameters. It will then build the string representation of the address that the IPAddr class needs in address/mask format using string interpolation. Then we can use the toRange method to create a list of the IPs in the network. We know we want the IPs in string format so that they can be passed to ping, and that we can accomplish this using the toS method that we've seen before. We could use the familiar each iterator to loop through all of the addresses and convert them. But Ruby actually has a special iterator just for cases like this. Here, we want to iterate over some data and perform a transformational operation on each element. For this, we can use the map method. Map will take a block and apply the operations it specifies to each item in the list. In this case, we're using the IP_object variable to represent each IP address and converting them to strings. Map will return an array with all the new string IPs, which we store in the IP_range variable. We could accomplish the same thing using the each iterator like this. Once IP range is filled with all the addresses in the range, we return it. Remember that Ruby uses implicit return statements. If we don't specify the values to be returned in our method, then Ruby just returns the value of the last evaluated expression. Good job. We've got our list of addresses. Next, we can use the netping library to test them. The method to do this might look something like this. This method takes in a parameter called IP range, which we intend to be the array calculated by the calculate network range method. Then we use an iterator to loop through each address in the IP range array using the external class from the net module to send a ping request to the computer at that address. The ping method checks to see if there's a response. If so, we push that address into the active IPs array. Although the each method does the trick here, given what we learned earlier about the map method, it might not surprise you to hear that Ruby provides a more specialized iterator method to do this job. The scan range operator we wrote could be refactored like this using the select iterator. Select is used like a filter. It returns a list of all the items for whom the Boolean test in the block evaluated to true. In this case, this will be a list of all the IPs that responded to the ping command. As you can see, by using the specialized iterator methods that Ruby provides, we can cut down on code length and complexity, which improves the readability of our scripts. After we've tested all of the addresses, we return active IPs. Remember that because of implicit returns, we don't have to say return active IPs. Since the active IPs array is the last value in the method, it is the value to be returned. The last method needs to write out the active IP addresses we found to a text file. If we use the examples we saw in the lesson on writing to files, this method could be written as the following. Active IPs is the parameter for this method, which is intended to be the list of IP addresses we found using scan range. The file class is used here along with a block to create a file called activeips.txt. Inside the block, we use the each iterator to loop through each active IP and write it to the file. After we're done, the file is automatically closed. Now let's wrap this up in the next video. With our methods done, our script is almost complete. We just need to add the code that will use each method and string them all together. We first need to calculate the range, so we need to call the calculate network range method we've defined. This gives us the array of addresses we need to scan in the scan range method, which we call like this. Finally, we need to pass the active IP addresses to be saved to disk. And with those 3 lines of code, we're done. Our finished program looks like this. You run the script, discover the active addresses on the network, and turn this list over to your manager. She is impressed, and so am I. You did some really great work here and should be proud of yourself. This script is a great start and definitely gets the job done, but some small improvements could make it even better. To start with, good scripts should be written to be as generally applicable as possible. In the case of scanner.rb, the local IP address and network mask are hard-coded into the program. If someone wanted to run the script for a different network, they would need to open the .rb file and replace the IP address and mask with data relevant to their network. Instead of having this information in the script, we could ideally pass it in somehow so that each time it was run, a different address and mask could easily be supplied. The most common way of doing this is through command line arguments, which you've probably used yourself when running other programs like ls or chmod. There are several gems and libraries that you can use to parse command line flags, and Ruby provides the option parser class in the standard library for this purpose. It would be even better if we had some tests for this code to increase our confidence that it was doing the right thing. One area ripe for testing is the calculate network range method. We could easily verify the correct range was being created by passing in some test data and verifying that the range it created is the range we expect. Don't worry about this too much now, as we'll cover it in future videos. Hopefully, walking through the creation of this example script has given you an idea of what the automation process can look like, and maybe even inspired you to think of projects you could script yourself. That's the goal. Remember that we did plenty of research and planning before we started writing any code. The adage, measure twice and cut once, applies to woodworking and programming. Hey again, and welcome back. In the last module, we took a deep dive into system programming, where we learned about using packages and libraries of code to get Ruby to work with files and directories. We also talked about how to use streams and pipes to construct data processing pipelines, and even run other programs from our scripts using subprocesses. To cap it off, we walked through a step-by-step example of how to write a complete script that found all of the active IP addresses on an internal network. Now we're going to build on that by looking at how we can use Ruby and regular expressions to process text and formatted data. As an IT support specialist, you'll probably find yourself needing to pull meaning out of raw text data from time to time. This data can come in many forms and from many sources, and might not be easy for humans to read or understand. And some data sources might be too large to read by hand, or maybe spread across lots of files and directories. This is where automation can once again lend a helping hand. To help you understand how useful the ability to process this raw text data is, let's check out an example. Imagine that you're a system administrator in charge of your company's SMTP mail server. SMTP is a protocol for sending and receiving email messages. You receive an alert that the server is producing a ton of errors, so you begin your investigation by taking a look at the logs. You see numerous failures, but also notice that many of the failures are coming from a particular range of IP addresses. Running the whois command, a type of network diagnostic tool available on most Unix-based systems, against several of them, suggests that they're all from the same network. But the number of addresses in the log file is very large, on the order of many hundreds. You might suspect that your server is the victim of a directory harvest attack. This is a technique spammers use to discover email addresses by sending requests to email servers with many random email addresses, in the hopes that some will be legitimate. You can block requests from the suspect network using other tools at your disposal, but you want to make sure that all of the bad requests are coming from that network. Blocking innocent users would be bad. You definitely don't want to read the entire log file and run whois against each IP address you see. So to verify your hypothesis, you write a script to read each line of the log file, parse the errors, and automatically analyze every IP you extract. With the script, you're able to verify your suspicion about the bad network, block the directory harvest requests coming from it, and stop the errors. Good thinking. Just a heads up. In the real world, you can mitigate this type of attack by configuring your SMTP server to stop answering with invalid recipient responses when an email fails to deliver. This response is the clue that the attacker uses to determine if the address they're trying out is a real one or not. As savvy IT support specialists, you can leverage the power of scripting and automation in situations like these to get useful information from all kinds of raw text data, then act according to that data. In this lesson, we'll use Ruby's robust string processing and pattern matching capabilities, and see how we can slice, split, join, and process text data to extract useful information from it. We'll even take a peek at how to handle other, more exotic data formats. That's right, data formats are getting exotic. Aren't you glad you made it this far? We'll kick things off by examining the Ruby string class. We've worked with strings before, but in the coming videos, we'll check out some of their more advanced capabilities, which allow us to manipulate text through indexing, searching, and more. I'll see you in the next video. In past lessons, we've seen how useful strings can be when representing text data, along with some of the ways we can work with them. We've seen strings used in expressions and learned about string interpolation. Our scripts have read strings from the terminal on standard in and printed them to the screen using standard out. But what else can they do? We know that strings are objects of the string class. Remember that almost everything is an object in Ruby. So it's no surprise that the string class provides several features that make strings even more useful than what we've seen already. One of the most important of these is the ability to perform string indexing. String indexing allows you to extract or even change certain portions of the text within a string. Think back to our lesson about arrays. Elements in an array occupy slots, where each slot has an index, beginning at 0. With indexing, you can treat the characters inside of a string similarly to how you accessed elements in an array. even using the same square brackets operators. The syntax used to index into strings is of the form string, start, comma, length. Check out this example. Here, we've used indexing to retrieve the first 6 characters in the str string. When you use brackets to index into a string, Ruby finds the position of the starting number, start, in this case 0, and retrieves the number of characters given in the second number, length, 6 in our example. This means Ruby starts at position 0, then counts out 6 characters to return S, T, R, I, N, and G. Indexing can let you access the characters in a specific range, but it can be also used to replace the characters in that range. What if we wanted to change the word string in our previous example to something a little more tasty? We could do this. As you can see, we've modified the string in place, changing the first 6 letters to another sequence of our choosing. Also, the replacement string doesn't have to be the same size as the string it is replacing. As you can see, the word string is 1 character longer than green, but Ruby will help us out by automatically rearranging the output. Along with replacing substrings, using this notation you can delete parts of strings by using empty strings. Substrings are small portions of text that represent a subset of the string you're working with. Insertions are also possible if you set the length portion of the string start length range to 0. You can also use indexing to extract single characters. Let's check out the output of this code. There are a couple of new things going on here. First, do you see that we've only put a single number between the indexing brackets? This is how we retrieved individual elements of arrays in previous lessons, and the same principle applies to strings. Second, the number being used as the index is actually negative. When you use negative numbers in a string, and array indexing, you're telling Ruby that you want to start counting from the last character of the string instead of the first. This means that we get the exclamation point from our example string, as it's the last element. This works for indexing sequences of characters too. Last but not least, Ruby also provides the concept of a range to use along with string indexing. Range is a class in its own right, but range objects can be provided to string indexes to retrieve sequences of characters. This might seem similar to what we've seen with the string start length notation. But the key difference between these methods of retrieving substrings is that with a range, you specify 2 indexes, a start and a finish. With the string start length notation, you provide the starting point and a number of characters to count up from that point. Ranges are specified using beginning ... end syntax, where the end position is inclusive, meaning that the character at the end position is included in the returned substring. Just like before, you can supply negative numbers as range positions to begin from the end of the string. Remember that -1 represents the very last character in a string. Indexing into strings can be super useful, but you might have noticed that it can be difficult to determine the correct index positions, especially if the string is really long. Luckily, Ruby provides several string methods to target specific substrings and give us some shortcuts. We'll start with the index method. As we called out, we sometimes may process very long strings, which makes counting positions difficult. If we want to know what position a particular character has within a string, we can use the index method. We've seen how we can change substrings with the power of indexing, but if we want to replace one string with another, the sub method can come in handy. Let's say we want to switch the word atrocious with the substring delightful in this string. We can use the string method sub to perform this substitution. The sub method takes 2 arguments, the first indicating the word we want to replace, and the second being the string we want to replace it with. The sub method doesn't modify the string in place as we saw with the indexing examples earlier. Instead, it returns a new string with the substitution performed. Ruby also provides a version of the sub method which performs the in-place substitution called sub ! Remember that in Ruby, methods who modify the object that they are called on are defined with the exclamation point in their names. You can view the exclamation point as a kind of warning, since this can be dangerous, as the original working value of the object is lost and replaced with its modified version. It's also good to know that the sub method only replaces the first instance of the matching string, as you can see from this snippet. To perform a string substitution on all of the substrings within a given piece of text, you can use the gsub method. Both the sub and gsub methods can take more complicated patterns as their search arguments, including regular expressions. But we'll explore this functionality more in our next lesson. Sometimes, you'll just want to see if a piece of text contains a given substring. To test this, you can use the include method. Include will return true if the text contains the substring and false if it does not. Remember that in Ruby, methods that end in the question mark usually return a Boolean value. You can use include like so. When combined with the branching logic of an if statement, this method can be used in your scripts to make decisions based on the contents of strings. For example, this code snippet checks the contents of the variable message for an error. If it finds one, it raises an error to stop the program. Although in this example the text being searched is a hard-coded variable, from our examination of working with files, we could just as easily be using the contents of an error log. This isn't directly related to strings, but it's good to know that Ruby's raise method is one way a programmer can cause their programs to crash and exit intentionally. I know it might seem a bit counterintuitive to want to crash your own program, but it can be a useful thing to do if something goes really wrong with your script. It may be better for it to stop rather than keep running in a bad state. We'll talk more about exceptions when we talk about testing later. We've seen ways you can extract and modify portions of strings using the indexing technique and the sub and gsub methods, along with how to test if one string contains another. On top of all of this processing power, the string class provides even more helpful methods for working with text. Some of these methods let you perform transformations or formatting on the string text, like capitalize and its opposite downcase. The reverse transformation is also handy and does exactly what its name suggests. Other methods provide information about the string itself. These methods include length, which returns the number of characters in the string. Another method called count will return the number of times a given substring appears within a string. Some methods process the string for later consumption in some way, like chomp, strip, or chop. We saw chomp in action back when we looked at how to gather input from the terminal on standard in using gets. The chomp method will remove specific characters from the end of a string, which by default include the /n, /r, and /r/n separator characters. The /r character indicates a carriage return, which means that the cursor should be moved to the beginning of the line. And the /n is a new line separator, indicating that the cursor should be moved to a new line. Although useful when printing formatted text to the screen to be read by humans, these separator characters can sometimes get in the way when we want to perform text processing in our scripts. For example, if you collect input from the command line using gets and view the length of the collected string, you might be surprised to see it's one character larger than expected. There are only 6 characters in the input, so why does the length method return 7? Using another of the string class's built-in methods called dump is helpful here. The dump method will print out all of the characters of the string it's called on, including special separator characters. Aha! There's our extra character, in the form of the /n new line separator. This separator is included in the string because when we hit the enter key on the terminal, the gets method records that as input and represents it by using a new line. To get rid of this extra character, we can turn to chomp. Chomp also accepts arbitrary strings as arguments. If you supply it with this argument, it will remove the given substring from the end of the string, if it's there. If you just want to remove the last character in a string without exception, you can use the chop method instead of chomp. Finally, the strip method will return a copy of the string it's called on, stripped of all whitespace from its beginning and end. Along with whitespace, strip will remove special characters like /r and /n, horizontal and vertical tabs, and null characters. This makes it really versatile when cleaning up text that may be sandwiched between a lot of extra formatting. Even though they go about it in different ways, each of these methods are tools to achieve the same goal of string processing. You can use them to remove the extra bits you might find in raw text data and preserve the parts that your scripts find useful to work with. Even with the variety of string methods we've covered, we still haven't fully covered the functionality provided by the string class. Check out the string documentation in the next reading for more examples and ideas of what you can do with strings. And don't hesitate to do some experimentation. Despite their variety and usefulness, sometimes string methods on their own aren't enough to do a text processing job. Indexing, strip, and gsub are all handy tools to have, but what if we needed to pick out all of the IP addresses from a system log, or find and return just the error code of 500 and above from a web server log? Solving these problems requires more than simple substring matching and indexing. For more advanced text processing, we can turn to regular expressions, which we'll talk about in the next video. A regular expression, also known as a regex or regexp, is essentially a search query for text expressed by a string pattern. When you run a search against a particular piece of text, anything that matches the regular expression pattern you've specified is returned as a result of the search. Regular expressions allow you to answer questions like, what are all of the 4-letter words in a file? Or, give me all of the email addresses in a request log. Knowledge of regular expressions can be useful for anyone who needs to perform text processing. From IT support specialists to software engineers, site reliability engineers, and system administrators, a working knowledge of regular expressions is a handy tool to have in your toolbox. Regular expressions are a pretty big topic in computer science. In this course, we'll shoot for a working introduction to them rather than an exhaustive survey. For your scripts, basic regexes will usually be enough to get you started, and will enhance the text processing ability of your program. You'll pick up more advanced techniques with time and practice. Many languages implement their own version of regular expressions, and Ruby is no exception. Some tools like grep in Unix-based systems also allow you to perform searches and filtering using regular expressions. Although the implementation details may differ from tool to tool or language to language, the principles should be similar. In Ruby, regular expressions are represented by the regexp class. In the next set of videos, we'll explore this class and its methods to see how it can be applied to processing, parsing, and extracting meaning from text read by your scripts. Let's dive in. At this point, you might be asking yourself, the string processing methods we talked about in the last session seem pretty helpful for text processing. So why not just use them? It's a great question. The answer lies in both the power and flexibility of regular expressions. Say, for example, you wanted to extract the process identifier portion from logs with this general format. In this case, that's the numbers between the square brackets. There's a lot of extra text in that string that you don't need, like the date, computer name, and other info. We could extract the process ID by using string indexing. The index of the square bracket is 39, which we could obtain either by counting the characters in the string or using the index method. If we don't want the square brackets, we should start at index position 40 and count 5 from there. Although we do get the text we're after, there are a few problems with this method. First, we don't know for sure how long the process ID string will be in all cases. In this example, we can see that it's 5 characters long, but that may change in the future if the computer is restarted or the number of processes increase. Another drawback of this indexing approach is that it quickly becomes obsolete. The next day, the date will change to August 1st, and the fact that the string August is 2 characters longer than July will throw off our indexing solution. This is where the flexibility of regular expressions can come in handy. This regular expression will work no matter how long or short the line is. As long as there's a single sequence of numbers in the string delimited by square brackets, this regexp will extract those numbers for us. If the regular expression assigned to the regex variable looks like a bunch of random text at this point, don't worry. We'll explore the syntax and usage of the regexp class in the coming videos. Soon you'll be able to read and unpack statements like the one in our example previously. We'll check out basic syntax in the next video. See you there. So how do we write regular expressions in Ruby? regexps are commonly defined using the slash symbol as a delineator, like this. Similar to how string objects are delineated by the quotation marks, this example creates an instance of the regexp class containing a regular expression. In this case, that regular expression will match the literal character sequence Ruby. The easiest and fastest way to find out if a regular expression pattern matches a string is to use this basic pattern matching operator. If the pattern does match, this operator will return the starting position of the substring that matched the pattern. If there's no match, it will return nil. Regular expressions have their own syntax, which can be as complicated as it is powerful. Ruby regular expressions reserve several characters that can give extra meaning to the patterns that you're creating. Let's say you wanted to match any string that contained the characters IGERS, which might optionally start with the letter T. You could write this pattern and check it against several strings. As you can see, both tigers and ligers match the pattern, and the starting position of the matching string was returned as expected. On the other hand, bears didn't match the pattern, resulting in the nil value. There are many characters like this that can be used to make your regex patterns super flexible. Among these are the caret and $ anchor characters, which indicate that the regexp should match from either the beginning or the end of the line respectively. You could use these anchors to match only words that start with the letter X or end with the letter Z. The caret and $ specifically match the start and end of a line, not a string. If you have a string that spans multiple lines, you can use the /A and /Z anchors to match the start and end of the whole string, not just the line. Ruby regular expressions can also accept modifier characters after their final /, which can be used to further refine how the pattern matching is to be done. One useful modifier is the I character, which ignores case when performing a match. Another special character that can come in handy is the dot symbol. Usually dubbed a wildcard, the dot character can be used to match almost any character you'd like. Remember that you can combine special characters, anchors, and modifiers as needed to create patterns to match the text you want. For example, this regexp will match any word that ends in ickle, ignoring case. Regular expressions also support the concept of repeated matches. For example, it's common to see the wildcard dot symbol used in conjunction with repetition characters in order to match multiple characters in a pattern. Repetition symbols include both the plus character, which means match one or more occurrences of the preceding character, and the star symbol, which means match 0 or more occurrences of the preceding character. For example, using the 0 or more occurrences operator of star, we can match the following strings. As the plus operator indicates we want one or more occurrences, it's a little more strict, since at least one repetition must occur for a match to be found. When used with the wildcard symbol, the repetition character can match a pattern containing any number of characters. This pattern will match any string, no matter how long as it starts with a capital A and ends in a lowercase a. Remember that since star means 0 or more matches, this string would also match the string capital A, lowercase a. Given the fact that the regexp class reserves so many special characters for pattern matching, you might be wondering what would happen if you needed to match a string containing one of those special characters themselves, like $ or question mark. This can be done through the concept of the escape character, represented by the \. Without the escape character, it will be impossible to match the character literal $ in a regexp. As you can see, the $ symbol is evaluated by Ruby to match the end of the string. In this case, the string is 6 characters long, so the value of 6 is returned to represent the position of the last character. To match the $ symbol itself, in this case the first character, you can escape it in the regexp. Escaping works for / too, which are usually used to delineate the bounds of the regular expression itself. First unescaped expression results in an error, while the second matches the / character in the string literally. Finally, it's important to call out that the Ruby regexp class supports another way of specifying regular expressions, along with the / syntax we've seen so far. If you begin your regular expressions with the %r symbol, you can use whatever delimiter you want instead of /. This can come in handy when your pattern might need to match on many / characters. like a Windows directory path, and you don't want to escape them all. There are tons of special characters, anchors, and modifiers that the regexp class supports. We've only taken a peek at a few of them. If you'd like to take a deeper dive, you can find the documentation for the regexp class in the next reading, with specific links to anchors and meta characters. Check it out, and when you're done, meet me in the next video, where we'll talk about advanced matching. Simple regex pattern matching can be achieved using the approximately equals operator, but you might be interested in things other than the position at which the match text starts. For example, you might want to know what the actual substring was that matched your pattern, or which portions of the text didn't match. For this and more, the regexp class provides a method called match. The match method is called with the string to match the pattern against, and an optional positional argument to specify where in the string to start the search. You can use the match method in this way. If no match is found, nil is returned, as with the approximately equals operator. If a match is found, instead of the starting position of the match text, the match method returns an object of the match data class. This match data object contains all of the information resulting from a regex pattern match, like the regexp you used, the original string, the matched and unmatched portion of the string, and more. Let's check out some of the features match data objects provide. First, you can print the original string you were searching for in your pattern with the string method. Similarly, you can print the pattern you were looking for with the regexp method. To see the string that matched your pattern, you can use matchdata's toS method. Matchdata also provides methods for checking out the text before and after the match. You can also give the match method a block, just like we've seen before with iteration and looping. The matchdata object will be passed to the block, where you can manipulate it as needed. Remember that if there's no match, the nil value is returned, and the block won't execute unnecessarily. Another super useful feature of matchdata objects is that they also separate any matchdata captured in parenthetical groups. Regular expression patterns can be grouped using parentheses, usually called capture groups, like this. As we know, combining the wildcard and repetition symbols will match any number of characters. In this case, we use this pattern to signify that we're only interested in the text that contains both the ABC and 123 substrings. In plain English, you could read this regex as the following. Match ABC, followed by any number of other characters, followed by 123, followed by any number of characters. The capture groups, represented by the parentheses, both group the regular expressions inside of them and capture the text that matches them for later use. We can see this by utilizing the captures method of the resulting matchdata object. The inspect method just gives you a representation of the object it's called on. In this case, showing that m.captures returns an array. Here, each element of this array corresponds to the text matched by a capture group in the regex pattern. You can also access the capture information contained in a matchdata object by indexing into it. The first element contains the text matched by the entire regular expression. Each successive element contains data that was matched by every subsequent match group. We'll examine some practical applications of capture groups in the next few videos. Along with capture groups, repetition, anchors, and other pattern matching features of regular expressions, the regexp class supports using character classes. Character classes, delineated by square brackets in a regexp, allow you to match against the set of characters contained within them. Take, for example, this regexp, which will match both the strings capital R Ruby and lowercase r Ruby. You can use a dash to specify a range of characters in your character classes. For example, to match any number between 0 and 9, you could write this. You can even combine character classes. This example matches any lowercase letter and any number between 0 and 9. Ruby also offers some specialized meta characters that behave like character classes. These can be used as shortcuts to match specific types of text. Instead of using the square bracket syntax to match a numeric digit, you could use the /d metacharacter. These become even more useful when you combine them with the repetition functionality. To match exactly any 3 numbers, you could write this. Remember the example from the beginning of our lesson of regular expressions? We should now have enough information to be able to understand it for ourselves. Let's walk through it step by step. The regular expression begins and ends with the slash delimiters, so anything between them must be the pattern we wish to match. The first character of the pattern is the backslash, which is used as the escape character. This means that the next character, a square bracket, is treated literally for matching purposes. After the square bracket comes the first parenthesis. Since it isn't escaped, we know it will be used as part of a capture group. The capture group parentheses are wrapped in the /d plus symbols. From our discussion of metacharacters and special characters, we know that this expression will match one or more numerical characters. After the closing parenthesis of the capture group, we have the closing square bracket symbol, also preceded by the escape character. When the match method is called, we know that because of the usage of capture groups in the expression, we can access the matching data by using the captures method. This gives us the process ID that we're after. Perfect. Along with the regexp class, the string class also contains some methods which support regexes as arguments. We saw in earlier videos how the sub and gsub string methods could be used to substitute one string in place of another. By adding regular expressions, we can make substitutions based on patterns. Since the question mark symbol means the character before it in a regular expression is optional, Ruby reads the string and uses sub to replace the first substring that matches, swapping tomato with banana. If we wanted to replace both the tomato and tomato substrings, we could use gsub. You can also iterate through a string using regular expressions and the scan method, which accepts a regexp as an argument. This means that you could iterate through each letter in a string using the wildcard character in this snippet. Another super useful string method that accepts regular expressions is called split. You can use split to chop up a string into an array using either a character or regular expression to tell Ruby where to do the splitting. For example, if you wanted to break an IP address into its constituent octets, you could use the split method. Here, we've passed a regular expression that matches the dot character literally, because we've used the slash to escape it. Split uses this pattern to break the string into chunks. This gives us each octet stored in an array, which we can then print. We've covered a lot of really technical stuff in the last few videos. You might be feeling overwhelmed at this point. That's totally natural. Regular expressions can make even the most experienced system administrators sweat, and they can be tricky to get right. As with many things, the best way to get comfortable with regular expressions is to use them. If you have access to a computer with Ruby installed, you can try out the examples we've gone over and invent your own regex patterns to see how they behave. If you don't have access to Ruby on your device, you can find many sites on the internet which run their own regular expression parsing applications. Although the syntax might be slightly different from site to site, they can still be a great way to test out your regular expression skills and do quick pattern matching checks. The bottom line is, regular expressions can be confusing, but don't let them intimidate you. They can save you a lot of time and effort if your script needs to do some text processing. Practice makes perfect, so keep at it and see what you can do. Up until now, most of our exploration of text processing has been pretty theoretical. In this video, we'll dive into a concrete example centered around processing chunks of data, the kind which you might find in a syslog or a web request log. If you need to work with log files in a script, your first step will likely be to open them so your code can access their content. We covered various methods of operating on files earlier in this course, but to recap, a common technique we can use is the open method from the file class to load a file into a program and iterate through each of its lines using the each iterator. For example, to open the file located at the absolute path /var/log/syslog, we could use this code. Remember that when files are large, it's generally a good practice to read them line by line instead of loading their entire contents into memory, for performance reasons. To demonstrate, let's say the log file at /var/log/syslog contains these messages. The server that generates this log file has been acting strangely, and you suspect it's because of a cron job started by one of the system administrators. Remember that cron jobs are used to schedule scripts on Unix-based operating systems. So you want to audit the log files and see exactly who's been launching cron jobs on the server. By looking at the sample log, we can see that the line that contains the cron substring will be of most interest to us. This line also has the user who started the cron job wrapped in parentheses, in this case, not a user. With this info, we can ignore any line without the cron substring in it. In a previous video, we learned about the include string method, which returns true if it finds the target string in some given text. We could use include to narrow our search to only the lines that contain the substring cron, like this. Now that we know we're processing the right log line, we can use our knowledge of regular expressions to extract the user's name. This can be accomplished in several different ways, but for this example, we'll use escape characters, capture groups, and the end of string anchor. Since the username is found at the end of the log line, we know we can use the $anchor to begin our search there. The username is also wrapped in parentheses, which means we'll need to escape them with the backslash. Finally, we could use a capture group to obtain only the contents between the parentheses. This might look something like this. We can test this regexp like this. Now we can add our regular expression to the framework we've constructed. Our script is shaping up nicely. We've located each of the users which started to cron in our log file and printed them to the screen. To improve our output even more, it would be good to have a count of how many times each username appears in our log. We can do this by using the hash data structure we talked about in our first week, along with a little creativity. Remember that hashes are data structures used to store information in key-value format. Each entry has a key with an associated value. We can create new hashes similar to how we create new arrays, but with curly braces instead of square brackets. But by using the new method of the hash class, we can actually supply a default value for all of the keys in the hash. For example, we could specify a default value of 0 by writing this. This will come in handy when we apply hashes to our current task of retrieving username counts. Remember also that each key in a hash is unique. There can be no duplicates. If we had a hash containing usernames as keys and counts as values, we could increment the value associated with the admin key by 1 through this code snippet. Armed with this insight into hashes, we can modify our code a little to record the count of usernames in the log file. The changes we've made are small but important. First, we've added a username variable to hold the username text matched by our regexp. Remember that when we use capture groups in a regexp, the text matched by each group is stored in an array, with the first element containing the entire string we were searching. Since we've only got one capture group in our regexp here, we can access the text matched by the capture group by indexing into the second element of the array, using the index of 1. We can use this username value to then access our hash. Remember that in a hash, when we access an element using a key that doesn't exist, the default value is returned, in this case 0. As we learned in previous lessons, the += symbol means increment by, so we increase the value of the key identified by the text in username by 1 each time we match it. This gives us the count of each username in the log file. You've now got a good idea of who and at what frequency has been starting cron jobs on the server, and can investigate the issue more deeply using this information. Time to nab that culprit. Using regular expressions in your scripts gives you a ton of flexibility when processing log files and other text data sources. In a script, you can program any kind of behavior you want in order to manipulate and process text data. Many terminal commands exist that can also provide a range of text processing functionality. Plenty of them also support regular expressions. When these commands are linked together in a data processing pipeline, like we talked about earlier when we discussed subprocesses, they can be a powerful addition to any IT support specialist's text processing toolbox. For example, you can use the grep command on Unix-like systems to perform text searches in files. Continuing from our cron log example, to find the usernames that match not a user in the syslog file, you could run this command from your terminal. To get a count of the number of times that username shows up in the log file, you could pipe the output of the grep command to the word count or WC command, using the -L flag to indicate you'd like to count the number of lines instead of words. Grep also supports searching using regular expressions, meaning we could approximate the script we wrote in our previous video using something like this. The first grep command in the pipeline finds all of the files in the log file with cron in them. The next uses a regular expression to match the usernames. The -E flag indicates we want to use extended regular expressions, and the -O flag means we want to print only the matching parts of the line to the screen. Remember that the documentation for any system command you use can be helpful in discovering its capabilities. On Unix-based systems, this documentation can usually be found in manual or man pages. See our System Administration and IT Infrastructure Services course for our deep dive into man pages. Sometimes it's inconvenient to write a full-blown script to read a file in and perform some text processing. Along with saving scripts to a file, Ruby also offers system administrators the ability to process text from the command line itself, without having to go through the whole trouble of writing and saving a new script file. You can combine system utilities and command line Ruby scripts together to create fast and convenient text processing workflows. Let's use this ability to update our log file cron parser example. We started with this program saved in a file. So how do we transform this into a text processing pipeline with Ruby? Well, first, we know that we can get the contents of the log file into standard out with a utility like cat. To process this output, we'll use the same Ruby interpreter command we've invoked in the past to run our script files, with some extra flags specified. The first flag that we'll want to use is -E. This flag lets us execute code we pass directly into Ruby on the command line, without the need to save it to the disk first. Check it out. As you can see, the -E flag will execute any code you pass into it. It's pretty cool. Next, if we want to process our log file, we'll want to be able to read each line we get from the standard in stream. The flag to do this is -N. This flag tells Ruby that we want to apply our code to each line of standard in until there's no more. You can think of it as being equivalent to this while loop. Ruby stores each line of the output in a special variable called $_. A little cryptic, I know, but we've got enough information to start processing our file using Ruby right from the command line. First, we want to filter the input for anything that has cron in the line. Next, let's refine our script a bit more to pull out those usernames from the log lines we filtered. You can see that we've put all the logic into one command and processed the log file directly from a terminal using a pipeline. One thing that you might not have seen before are the semicolon symbols in the command line script. Ruby uses these characters to chain multiple statements together on a single line, kind of like the pipe separator is used to chain multiple commands together. Constructing pipelines of system commands can usually give you some information very quickly, without the need to write a full script, and can be extended with Ruby code as we've just seen. But their availability depends on the platform you use, since some commands might not be written to work with certain operating systems. System commands are also not as flexible or robust as writing a script, where you have access to the entirety of the Ruby language. Despite this, they're a great option to keep in your IT support specialist toolbox for quick, on-the-fly processing. Along with speed, using single-line Ruby scripts can be a lot more simple than chaining together a huge pipeline. Consider this bash pipeline, which capitalizes each word in a file named story.txt, and the Ruby script that provides the same functionality. So far, we've looked at ways to process plain text data using Ruby's string class and regular expression capabilities. But there are a lot more formats that data can take besides text, some of which you may need to manipulate in your scripts. Formats are generally used to give some kind of structure to data. Remember that computers like structure and precision. In order to be able to process a dataset, it helps to know how that dataset will be arranged beforehand. You've seen this already in some of the examples we've used, like the structure of the log file lines. If you can expect data to be represented in a certain way, it becomes easier to extract meaning from it. A very simple example would be knowing that if the word cron appears in the log line, the process which generated that log line was a cron. There are many types of formats used today to structure, store, and transport data. Some of them you might be familiar with already. HTML is a markup format which defines the content of a web page. JSON is a data interchange format commonly used to pass data between computers on networks, especially the internet. Ruby provides classes and modules for working with many of these data formats in its core and standard libraries, like CSV and JSON. Even more libraries are available as installable Ruby gems, hosted in the public gem repository, like Google's protobuf format, or the Nokogiri gem, which can parse, which means analyze and process, many different types of data. I've linked to these repositories in the next reading so that you can check them all out. In this lesson, we'll check out how you can use one of the data processing classes from Ruby's standard library to work with a type of formatted text called CSV. We'll start with how to read these files in the next video. See you there. CSV stands for comma separated values and is a data format which represents data as segments of text separated by commas. CSV is a fairly simple format. CSV files are stored in plain text, and each line in a CSV file generally represents a single data record, and each field in that record is separated by a comma. For example, if you were storing information about customers, you might have this data. Ruby's standard library includes a class which allows you to read, create, and manipulate CSV files. To use it, remember that we must load it with the require statement, like so. Opening and iterating through a CSV file can be done in a way that's very similar to how we've worked with files before. Here, we use the inspect method to show that the CSV data is now in array form, with each array corresponding to a line in the CSV file, and each element in the array corresponding to one of the fields in that line. If you want to read and parse the contents of the entire file, the CSV class provides a read method which can accomplish this. The return value of the CSV read method is an array of arrays, which means that several inner arrays are nested inside an outer one. To access data inside the structure, you could use the indexing technique we've seen before to access array elements. If you wanted to access a particular element inside of this inner array, you can extend the same technique. This just means you want to access the first element of the people array, and since that's also an array, you'd like its first element. Once you've read the CSV file into your program, you can use the find or find all methods to search for something within the CSV data. These aren't methods provided by the CSV class itself, but by the array class. Since the CSV data is saved into arrays, as it's read by our script, We can make use of the array class's methods. Our knowledge of regular expressions can come in handy here, since we can use a regexp to match the array elements. For example, to retrieve the record for anyone with the first name Pearl in the CSV file, we could use the find method, like this. Let's step through this. We first read the CSV data into a variable called people, which we know is an array of arrays, one for each line in the file. Then we use the find method to iterate through each subarray, checking if the first element, index number 0, of each subarray matches the regular expression /programmer/. If it does, find saves the array to the programmer variable, which we print to the screen. Hi, Pearl. The find all method is similar to find, but will return all of the elements that match your search terms. You could use find all to locate the records for each person whose name starts with Ruby. Now that we can read and search through CSV files, we'll learn how to modify them by adding more record lines or rows. We can add rows of CSV data with the addRow method from the CSV class. Let's say we wanted to add a new person to the CSV file we've been working with. We can accomplish this with this code, which will result in the contents of the CSV file.txt being changed to. There are a few interesting things going on here. First, check out that we've used the csv.open method to open our CSV file. This will probably look familiar to you from our lesson on the file class. The important difference between file.open and csv.open is that with file.open, you append strings to a file. With csv.open, you append rows which are represented as arrays. We also used the A file mode to open the CSV file, which stands for append. Using this mode means we want to add rows to the end of the file. The data itself is an array, stored in the newPerson variable. The addRow method accepts this array and automatically converts it to CSV format for us, inserting commas after each element. Knowing how to work with CSV files can be super useful, and demonstrates some of the capabilities that Ruby can provide your scripts for working with many different data formats. Many programs are capable of exporting data as CSV files, including spreadsheet applications like Microsoft Excel or Google Sheets. It can be helpful to think of a CSV file in terms of a spreadsheet, where each line corresponds to a row and each comma-separated field corresponds to a column. Along with the CSV module in the Ruby standard library, there are several gems that can be installed to parse CSV files, like faster CSV. Gems can be a great way to extend the data processing functionality of your scripts, especially for more complex data formats. In the next few videos, we'll check out one gem which can be used to parse the HTML data that makes up most of the content on the web. Documents written in HTML, which stands for Hypertext Markup Language, are one of the building blocks of the web. Any web page you visit will make use of HTML in some way. The HTML data format describes and defines the content of a web page. It uses markup tags to annotate the content for web browser programs to read, understand, and display. For example, to add a title element to a web page, you would use the HTML markup title tag. The ability to scrape, which means to download and process, web pages, can be a useful tool to have in many automation situations. Parsing HTML documents comes in handy if you need to extract data from one or many pages on a website, where reading each page would be time-consuming. Or if you're waiting for some information to be posted to a web page, like a new product availability, you might regularly scrape the page with a script and have it notify you through email. Easy, right? Some of the techniques and tools we've seen so far can help us process data from the web. For example, we could construct a pipeline of commands to pull down an HTML document from the internet and search through it for a particular string. Check out this pipeline. It will retrieve the Google search homepage using the curl command and pipe it into grep to look for instances of the word Google. While quick and easy, we've already learned that this method of data processing isn't as flexible or robust as using a script. So knowing this, you might be tempted to turn to regular expressions to parse HTML documents. Although this is fine for a few very simple cases, you'll run into trouble if you try to process anything more complex. Matching up nested opening and closing HTML tags can be very difficult with a regexp. And constructing an expression that is generic enough to correctly parse every web page is almost impossible. Luckily, there's no need to reinvent the wheel if you need to process HTML files in your scripts. You can use a library that will provide the parsing functionality you need. I'll tell you how in the next video. Although the Ruby core and standard libraries provide a lot of support for many tasks, they don't contain a core or standard HTML parser as of now. But we can still turn to Ruby gems as a source of library code. There are many libraries available in the gems repository, which can be used to process HTML, and a quick search of the public repository will turn up a list of them. One of the most popular is a library called Nokogiri, which can be used to parse HTML along with several other data formats. In these examples, we'll demonstrate how to use Nokogiri to process HTML files. Since Nokogiri is packaged in a Ruby gem, in order to use it, we must first install it using the gem install command, then import it using require. With that setup taken care of, we can start parsing HTML. The simplest way to parse HTML with Nokogiri is by reading it from a string. We can use the Nokogiri HTML module to create an HTML document like this. Then we can use the parsing abilities of the library to print out the title. More often than not, you'll want to access HTML formatted data from an external source rather than a string. For this, you can use the super useful file.open method. If we have an HTML file called webpage.html with these contents, we can use file.open in conjunction with the Nokogiri HTML module to parse the text, line by line. Even better, if you combine the parsing functionality with the OpenURI class from the standard library, you can download and process files directly from the internet. We first import both the Nokogiri and OpenURI libraries so we can use them. The open method from the OpenURI library lets us access web pages by their URL, which we can then work with as if they were files. In this case, we pass the HTML text contents of http://www.google.com to the Nokogiri HTML module, which parses the page. We can then access the page title just as we did earlier. So far, we've been using the shortcut method title to retrieve the text wrapped in the title tags of the HTML documents that we've parsed. If we wanted to retrieve the text between any HTML tag, though, we can use the CSS method Nokogiri provides. To get the value of the p tags, which stands for paragraph in HTML parlance, from our example file, we can use the search method like this. There are all sorts of other ways you can scrape and parse HTML pages with the Nokogiri library. These include retrieving the attributes of elements along with their text, or selecting specific nested sub-elements. The Nokogiri documentation contains some helpful tips and examples too. Last but not least, don't forget that this is just one of the many libraries you can use to parse HTML pages in Ruby. Feel free to explore and experiment with others. In this lesson, we've explored some of the ways you can read and process different kinds of data in your scripts, including CSV, or comma-separated value, and HTML, hypertext markup language. Ruby's extensive collection of libraries makes easily parsing a wide variety of data formats possible, which means your automation can be flexible when reading and writing data. Next, we'll put your newfound knowledge to the test. You'll have an assignment that requires you to parse a log file in order to answer some questions about the recent activity of the underlying system. Good luck. A version control system, or VCS, is a term you might have seen before, either managing configuration files or when maintaining the source code of programs and scripts. At first glance, VCS can seem like a complicated, even intimidating tool, but don't worry, it's easier to use than you think. If you look closer, you'll see that it's really just a system that stores files, but unlike a regular file server which only saves the most recent version of the file, a version control system also stores previous versions of each file as you save your changes. Not only does this let you see past versions of a file, but it also allows you to see who changed which files and how each file was changed, and even when the changes were made. You can also make edits to multiple files and treat all of the edits like a single change. This is known as a commit. A VCS even provides a mechanism where the author of the last change or commit can record why the change was made. Having detailed historical information for your organization's configuration files and automation code is critical for teams trying to manage change within IT. It lets you, the administrator, see what was modified and when, which can be critical to troubleshooting. It gives you a documentation trail explaining why the infrastructure is the way it is for future IT members. It also provides a way to undo a change completely without the human error associated with trying to revert it from memory. We'll see more of that when we talk about rollbacks. A VCS is critical to maintaining a healthy codebase for all kinds of IT resources. It lets multiple people collaborate on the same coding projects together. In the next few lessons, we'll introduce you to a popular version control system called Git. We'll teach you some of the ways you can use it and how to set up an account with a service called GitHub. There, you can create your very own remote repositories to store your code and configuration. Get it? Good. There's a lot to learn with Git, so we'll break it down step by step. That way you can fully understand how it works and why it's so useful for IT support specialists. In the next few videos, you'll learn about some of Git's introductory features so you can understand how and why it's used in organizations. We'll also introduce more advanced features like branches and merging. Plus, we'll demonstrate how having a working knowledge of a VCS like Git can be a big help in emergency situations or when debugging. A VCS is a key part of managing the code in any organization that produces software. There are other things that keep a code base healthy, like having a robust set of tests to make sure the code is working properly. We'll also take a quick tour of the world of software testing to get you up to speed. That way you'll understand some of the ways you can make your scripts more robust, stable, and less error-prone. Let's get started. At first, using a VCS might seem like a lot of overhead for an IT support specialist to set up and learn. It might really seem like overkill if you're the only member of your IT team that writes code, or maybe even the only member, period. So, can a VCS help even if you don't need to share your scripts or work on them collaboratively with others? The short answer is yes. A VCS can be invaluable even in a one-person IT department. A VCS stores your code and configuration, true, but it also stores the history of that code and configuration. A VCS can function a lot like a time machine, giving you insight into the decisions of the past. Whenever you write a commit message after making a change, it's as if the current version of yourself is explaining your decisions to future you, or others who may maintain the codebase. This can help you avoid situations where you're staring at a piece of code someone else, or even yourself, wrote 3 months ago, puzzling over how it works or why it even exists. With a VCS, you can view, track, and select snapshots from the history of your project, so nothing you do is lost. Code isn't the only thing that can go into a VCS. You can use a VCS to store and manage configuration files. This contributes to the stability and reliability of IT systems. Let's say you've stored the DNS zone file in a VCS. Remember that a DNS zone file specifies the mappings between IP addresses and host names in your network. If you use good explanatory commit messages when you update the zone information, you'll have access to meta information about the new IP addresses and host names present in the zone file. This might include info like when they were added and for what purpose. If anything breaks after you add a new entry, you can rely on the VCS to tell you what the file looked like before the change. That can be a real time saver. You can revert to the old version quickly, which lets you fix the problem fast and figure out what went wrong later. This functionality makes the systems you'll operate more reliable. Because of the audit trail provided by the VCS, you know exactly which version of the file to roll back to, and the time it takes you to fix the problem is reduced. It's usually better to quickly roll back and stop the errors, rather than spend time trying to figure out what went wrong. You can code up the fix after the bleeding has stopped. Figuring out the bug might take up valuable time, and even worse, your solution could contain bugs itself. We've cooked up a quick quiz for you. Then we'll do a recap on what exactly Git is. Git is a VCS created in 2005 by Linus Torvalds, the developer who started Linux. Git is a free, open-source system that's available for installation on Unix-based platforms, Windows, and OS X. Linus Torvalds originally created Git to help manage the task of developing the Linux kernel. This required facilitating software collaboration with a whole bunch of programmers who were writing the code in different places all over the world. Linus wanted the system to work and perform in a specific way, but the VCSs at the time couldn't handle it, so he wrote his own. Git is now one of the most popular version control systems out there. It's used in thousands of projects. Unlike some version control systems, which are centralized around a single server, Git has a distributed architecture. This means that every developer or IT support specialist has a copy of the code repository they're working on locally on their own development machines. Collaborators can share or pull in changes that others have made whenever they need. Because the repositories are all local, doing most operations is super fast. You could set up a repository on a server as a kind of hub for others to contribute to and base their work on. But Git doesn't rely on any kind of centralized server to provide control or organization to its workflow. You can install and use Git on a single machine without a network connection. Or you can install Git as a server on a machine where you want to host your repository. You can then access the repository from another machine, or even the same one, using Git like it's a client. Git clients can communicate with Git servers over the network using HTTP, SSH, or Git's own special protocol. If you're curious about Git's architecture or communication protocols, check out the documentation in the next reading for more details. You've already learned that Git is a distributed VCS, where each developer has a copy of the repository on their local machine. Even though each copy is a peer of the others, we mentioned the idea of installing Git on another machine, like a kind of Git server, which hosts a remote repository. If you don't want to set up a server yourself to host your Git repositories, you can use a service like GitHub. GitHub is a web-based Git repository hosting service. It adds extra features to the version control functionality of Git, like bug tracking, wikis, and task management. GitHub lets you share and access repositories on the web and copy or clone them to your local machine so you can work on them there. GitHub is a really popular choice and has a great feature set, but there are other services that provide similar functionality, like Bitbucket and GitLab. We'll be using GitHub for the examples in this course, but feel free to use the tool that best fits your needs. I've put links to the tools in the reading right after this video so that you can dive in and explore your options. GitHub provides free access to a Git server for public repositories, and offers a private repository service for a low monthly fee. We'll be using free public repositories in our examples, which is fine for educational use and small personal projects. But I want to call out that information about your organization's IT infrastructure can be very useful for hackers attempting to break into your network. Let's not help the hackers along. All that information should be treated as confidential. For real configuration and development work, you should try and use a secure and private Git server with limitations on those authorized to work with it. That way you keep your clients and their information safe. To use GitHub, the first thing you'll need to do is create an account if you don't have one already. Signing up online is free and pretty simple. We'll go through an example of a typical Git and GitHub workflow in the next lesson so you can get the hang of it. Having access to a VCS is great, but you need to know how to use it in order to take advantage of its capabilities. Let's dive into the nitty-gritty details of version control systems, using the Git program as a platform for our examples. In this course, we chose Git for its popularity, multi-platform support, and awesome set of features. As with most things in the IT world, though, there are many tools that can be used to accomplish the same task. Other VCS programs exist, like Subversion or Mercurial, and you should feel free to experiment with alternatives if you think another VCS might be the way to go. Using Git can definitely be confusing at first, so it might help to keep a few things in mind for the examples and exercises that are coming up. First, you can think about Git as representing your project, which includes code and associated files in a series of snapshots. Every time you make a commit, which is when you add code to your project using the git commit command, Git records a new snapshot of the state of your project at that time. It's a picture of exactly how all those files looked at a certain moment in time. Combined, these snapshots make up the history of your project. Next, there are three main states that any file in a project tracked by Git can exist: modified, staged, and committed. If a file is in the modified state, it means that you've made some changes to it, or it's a new file. It hasn't been added to the snapshot yet, since it hasn't been committed to your project. Modified files show up like this in the status of a Git repository. Next, staged files are files that have been modified or newly added, and are marked as ready to be committed to the project. Files that are staged will be part of the next snapshot you take. This status message shows two files that are staged, a newly added file to the repo, and a modified file that was already part of the repo. Finally, if a file is committed, then it's safely stored in a snapshot in the Git database. The typical lifestyle of a file is modified, staged, committed. Any Git project will have three sections: the Git directory, working tree, and staging area. You can think of the Git directory as the database for your Git project, where all of the snapshots you've taken from your commits are stored. When you clone a repository, this Git directory is copied to your computer. When you run git init to create a new repository, a new Git directory is initialized. The working tree is a checked out snapshot of your project. You can think of it like a workbench or sandbox, where you perform all of the modifications you want to your files. When the changes are ready, you stage them by adding them to the staging area using the git add command. The staging area, also called an index, is a file maintained by Git that has all the information about what files and changes are going to go into your next commit. Remember that files marked as staged will be included in the next snapshot that you take. So, to wrap things up, you work on modified files in your working tree. When they're ready, you stage these files by adding them to the staging area. Finally, you commit the changes sitting in your staging area, which takes a snapshot of those files and stores them in the database that lives in the Git directory. The git commit command is used for this part of the process. It's also good to know that Git uses an alias called head to represent the currently checked out snapshot of your project. which is how the contents of your working tree are set. The current snapshot can be a construct that Git calls a branch, but can also be a regular old commit in certain cases. Head is how Git marks your place in the project. It's like a bookmark that you can use to keep track of where you are. Even if you have multiple books to read, the bookmark indicates where you are now. When you run Git commands like diff, branch, and status, Git will use the head bookmark as a basis for whatever operation it's performing. We'll see head used later when we check out how to undo things and perform rollbacks, and we'll talk about branches in later videos. As a shortcut, it's simpler to think of head as a pointer to the current branch, but remember that you can change the commit that it points to as needed. Does all of this seem overwhelming? If it does, don't worry. We'll see all of these file states and project sections in action when we review the basic Git workflow. But first, let's dive deeper into the details of a commit message in Git. In the last video, we briefly talked about the idea of committing snapshots of changes to the Git repository. Writing a clear, informative commit message is important when you use a VCS. Future you and those developers or IT support specialists who read the commits later on will really appreciate the contextual information as they try and figure out some part of the code or configuration. So what makes a good commit message? It can be helpful to keep your audience in mind when you write commit messages. What would someone reading the message weeks or months from now want to know about the changes you've made? What might be especially important or tricky to understand about them? Is there extra information that might help the reader out, like links to design documents or tickets in your ticketing system? Similarly to how style guides exist for writing code, like the Ruby guide we discussed in the first module in this course, your company might have specific rules for you to follow when writing commit messages. Even if they don't, it's good to use a few general guidelines to make your commit messages as awesome as possible. A commit message is generally broken up into a few sections. The first line is a short summary of the commit, followed by a blank line, which is in turn followed by a full description of the changes, which details why they're necessary and anything that might be particularly interesting about them or difficult to understand. When you run the git commit command, Git will open up a text editor of your choice so that you can write your commit message. A good commit message might look something like this. As you might have guessed from the text of the message, there are some rules about line length that you should follow. The first line is usually kept to 50 characters or less, and subsequent lines are usually under 72 characters. Sticking to these line lengths are really helpful for readability, making the commit message more digestible by the reader, in a way that's similar to the line lengths we talked about when we talked about Ruby style. Additionally, another Git command used to display these commit messages, called git log, won't do any line wrapping for you, meaning long commit messages will run off the edge of the screen and be difficult to read. Check out the lines in the commit message that start with the hash symbol. Just like in Ruby, this indicates that these lines are comments and won't get included in the commit message. Git just shows them to you to be helpful as a reminder of what you were working on. Following these guidelines can help make your commit messages really useful, and the investment of work now will really pay off later. If you're interested in learning more about Git commit style, there are plenty of resources out there to read, including the Linux kernel documentation itself, along with impassioned opinions from other developers. Now, we'll focus on working with a local Git repository. We'll dive into remote repositories and cloning a little bit later on. Before you can use Git, you have to install it. The directions found in the Git documentation are thorough and really helpful. Check them out for the best way to get Git into your platform of choice. We'll be using Ubuntu in our examples. That way we can use a package management system like apt to download and install the software. Once it's installed, we should be able to verify the version we've got with this command. First, all of the files you want to manage with Git have to be part of a Git repository. Remember the Git directory we learned about in the last video? Well, you can load a Git repository in any file system directory with the git init command. So, for example, this set of commands will create a normal file system directory called scripts on a Unix-like system. Then initialize an empty Git repository inside of it. Your shiny new Git repository can now be used to record the changes to files inside of it. Very cool. Let's check it out by changing into the newly created scripts directory and having a look at the git config. This config can be examined with the git config command. There's a lot of info in there, some of which we'll cover later, but pay special attention to the user email and user name lines. This information will appear in your public commit logs if you use a shared repository, and you might want to change them for privacy reasons. You can check out setting your email in Git and keeping your email address private on the GitHub help site for how to do this. If you add a new file in the directory, like the scripts directory we just mentioned, it starts off as untracked. You can make all kinds of changes to the file, but until you tell Git to track it, Git won't do anything with an untracked file. You can do this with the git add command from inside the repository. The git add command will send a new file from untracked to the stage status and change a modified file to staged. Remember that when a file is staged, it's been added to the staging area and is ready to be committed to the Git repository. Anything that's unstaged at this point, like stuff that you haven't run git add on, will not be committed to the repository. To initiate a commit of staged files, you issue the git commit command. This will launch a text editor, which is set in most operating systems by an environment variable like $editor. This is where you can write your commit message. Voila, you've just recorded a snapshot of the code in your project. It's stored in the Git directory we spoke about in the last video. Remember that every time you commit, you take another snapshot, annotated with a commit message that you can review later on. It's good to call out that at any point in the workflow, you can check the status of what's tracked or staged using the git status command. For example, to check the history of commits for your project, you can use the git log command. Since we've done 2 commits so far, we get 2 entries in the log when we look at it. Check out what Git tracks as part of the log. The first line has the word commit. If we add the -- decorate flag, we can get even more information. Do you see the head master portion? This line gives us information about the commit itself. The long string is the ID of the commit, and the head master portion shows which branch head is pointing after the commit was made. We'll dive deeper into this later. Next, you'll see the person who made the commit is named the author. That's followed by the date and time the commit was made. Finally, the commit message is displayed. Remember that even though these commit messages are fine for providing examples, in a real commit, you'd want to follow the guidelines we outlined when we dove into the anatomy of a commit message. Remember, you can always go back and rewatch these videos to review the materials at any time. You should check them out if you're having any commit issues. You've seen how to use Git locally and gotten a taste of the local development workflow. It's time to take things to the next level. In this video, we'll look at how we can use Git in conjunction with a remote repository hosting service like GitHub. Since we've already got Git installed locally, the next step is to create an account on github.com. You can follow the workflow at github.com/join, which will set you up with a free account, a username, and a password. After you've made your account, you can follow these steps to create a brand new repository on GitHub. We've called ours IT-support, and you can find the full list of steps in the next reading. With Git installed on our local machine and a fresh remote repository ready to go, let's get to work. The first step is to copy the repository from the GitHub servers to the local machine. This can be accomplished using the git clone command. This is where we'll clone the repo into the home directory on our Ubuntu computer. In this example, we'll use the HTTPS URL that GitHub gives us, which tells the Git program on our computer where to find the remote repo. Just like that, a copy of the remote repository has been downloaded from GitHub and onto the local machine. This means we can perform all of the actions we were able to do in the earlier video on the Git workflow. Git does give us a little warning that the repository is empty, but that's exactly what we expect since we just created it. Let's make Git happy and add some content to the repo by making a README file, then committing it. Our README file will contain some wisdom from a friendly cow and look like this. As you saw before, we'll need to first start tracking the new file by adding it to the repository. Then, commit it. This is good, but we've seen it before. We've got a remote repository set up on GitHub, so let's use it. We can send our changes there by using the git push command. It'll gather up all of the snapshots we've taken, only one in this case, and send them off to the remote repository. We'll talk more about the mechanics of git push and remote repositories in general in a later video, but the mechanics here are pretty simple. To push our README up to GitHub, issue this command. You'll then be asked for your GitHub username and password. Now, if we check our repository on GitHub, we should see our README and the message from the friendly cow displayed. Pretty cool. We've taken the local changes on our computer and then pushed them up to a remote repository hosted on GitHub. But wait, did you catch that stuff about origin and master? What exactly is going on here? And how can collaborators use this repository anyway? What if we needed to retrieve changes from the remote repo that someone else pushed? The answers to these questions and more are headed your way, so keep watching. Warning, geeky stuff ahead. But before we go any deeper, let's try to cement the basic workflow and concepts with a quiz and some practical exercises. Then we'll get more done with Git. You can get a lot of mileage out of the basic track, stage, commit workflow. And the status and log commands will give you access to a lot of the metadata that makes using a VCS so useful. But Git can do a lot more. Spoiler alert, you're about to find out how. One useful shortcut to know about is how to skip the staging area altogether. Let's say you've got a tracked file in your working tree that you make some small changes to. If you decide the full workflow is a little heavyweight for the change you've just made, Git will actually let you skip the staging area entirely and go straight to committing. Helpful, don't you think? You can provide a description right on the command line by using the -A and -M flags, where -A automatically stages every file that is tracked before doing the commit. So you can skip the git add part. At first, you might think that git commit -A is just a shortcut for git add, but don't be fooled. Git commit -A doesn't work on new files, those which haven't been committed to the repo already. Instead, git commit -A is a shortcut to stage a file and commit it in one step. If the file hasn't been committed yet, you'll still need to use git add to track it first. The -m flag lets you inline your commit message, so you don't need to open up a full text editor to type out the description of your change. It's just like using the regular commit workflow. The commit will show up in the log along with the message, as usual. Let's say that you've decided to clean up some old scripts and want to remove them from your repository. Or you've done some refactoring, which makes a particular file obsolete. You can remove files from your repository with the git rm command, which will stop the file from being tracked by Git and remove it from the Git directory. File removals go through the same general workflow that we've seen, so you'll need to write a commit message describing why you've deleted them. Git also has an mv command, which works like you might expect to move files around. This example moves the new script2.rb file to a directory called subdirectory. Git also gives you the ability to ignore files that you don't want to track. This can be super helpful if your scripts produce automatically generated files or artifacts you don't want in your repo. It also helps if your operating system automatically creates files you don't need in your commits, like the .dsstore file in OS X. You can do this by creating a git ignore file, where you specify rules to determine the types of files Git should skip. If your git ignore file looks like this next example, then any files that end in .rb will be ignored by Git. But you probably don't want to ignore your Ruby scripts. Remember that the dot prefix in a Unix-like file system indicates the file or directory is hidden and won't show up when you do a normal directory listing. You can check out the next reading for a few common examples of file patterns to exclude. One of the coolest things about a VCS like Git is the ability to undo changes you've made. In Git, you do this by rolling back your project to an older snapshot. Before we do a full rollback though, let's talk about a few other ways you can undo things in Git. Let's say you've just finished committing your latest batch of work, but you've forgotten to add a file. Whoops. Or maybe you've just committed, but decide that your commit message just wasn't descriptive enough. No need to worry. You can solve these issues using the --amend option, which will take whatever is currently in your staging area and run the git commit workflow to overwrite the commit. In the next example, we perform a commit which doesn't add all of the files we want. It only commits new file 1. It's good to call out that while git-amend is okay for fixing up local commits, you shouldn't use it on public commits, which are those that have been pushed to a public or shared repository. This is because using amend rewrites the Git history, removing the previous commit and replacing it with the amended one. You should try to avoid this because it can cause some confusing situations when working with other people. So remember, fixing up a local commit with amend is great, and you can even push it to a shared repository. But try to avoid doing the same to commits that already appear in that repository. As you can see, git log can take options too. The --stat option tells it to print out some extra information about the changes we've committed, which means that we've changed only one file, new file 1. Oops, this isn't right, so let's fix it using the amend option. Awesome. We've changed our earlier commit to include both files, new file 1 and new file 2. You can also amend the message of the previous commit if you run the git commit --amend command when there are no changes in your staging area. Git also lets you work with files in the staging area. If you've added a file to your staging area with git add, but don't want to include it in the current commit, you can unstage it by using the git reset command. This happens a lot if you use git add star, where star is a file glob pattern to add everything in the working tree to the staging area. It's kind of like a regular expression. Sometimes, grabbing everything in the working tree includes files you don't want to commit. For example, well, you definitely don't want to commit a bad file. Luckily, the git status command tells you how to unstage the file right there in the output, which is pretty handy. Check out the head argument. You might remember it's used as an alias for the current commit that your current working directory is based on, which in this case is the same commit as master or the current branch. Now you can run this to remove bad file from the staging area. Ta-da! The file is back on your working tree and no longer staged. You might also find yourself in a situation where you've made a bunch of changes to a file but decide that you don't want to keep them. You can change a file back to its earlier committed state by using the git checkout command. Much like how it showed us an example of unstaging a file, git status will give us instructions on how to discard changes too. If we follow the suggestions from git status, this command will reset the new script.rb file to the last time it was committed, throwing away the changes we've made in the interim. Let's keep rolling right along into the next video, where we'll learn all about rollbacks. I'll see you there. Fixing some work before you commit it is good, but what happens if it's already been snapshotted by Git? Let's say you host a Git repository on a company server that contains all kinds of useful automation scripts that you and your coworkers use. One morning before coffee, you make a few changes to one of these scripts and commit the updated files. A few hours later, you start to receive tickets from users, indicating some part of the script is broken. From the errors they describe, it sounds like the problem is related to your recent changes. Big mistake. Why do anything important pre-coffee? Yikes. You could look at the code you updated to see if you can spot the bug, but more tickets are pouring in and you want to fix the problem as fast as possible. You decide it's time for a rollback. There are a few ways you can roll back commits in Git, which I've linked to in the next reading. For now, we'll focus on using the git revert command to get this done. In Git, revert doesn't just mean undo. Instead, it creates a commit that contains the inverse of all the changes made in the bad commit. Cancel them out. So if a particular line was added in the bad commit, then in the reverted commit, that same line will be deleted. This way, you get the effect of having undone the changes, but the history of commits in the project remains consistent, leaving a record of exactly what happened. Get it? Got it. So git revert will create a new commit that is the opposite of everything in the current snapshot. You can run it like this. Remember that since you can think of head as a pointer to the snapshot of your current commit, when you pass head to revert, you tell Git to rewind that current commit. Once you issue the git revert command, you'll see the text editor commit interface that you've seen before. You should write a good explanatory commit message in it to justify the rollback. This will also help your future self understand why it happened. Your future self is so on top of things. You'll see that Git automatically adds some text to the commit indicating it's a rollback, like revert, followed by the first part of the reverted commit message. In the Git log, you can see both the bad commit and the rollback. Here, we're using some of the options that the git log command has to display some additional information. The -p flag will show us the diff, or difference, between what was committed in the current and previous snapshot. The -2 option just tells git log that we only want the last 2 commit entries from the log. You can see the line of code that introduced the error in the second, older commit message, marked as an additive diff by the plus before it. The same line shows up as starting with the minus sign in the newer commit message, indicating that it was removed. Just like that, the bad commit is reverted and the errors stop. Phew. Now your code is in tip-top shape and you can get back to enjoying that cup of coffee. Once you're recaffeinated, we'll see you back in the next video on how to identify a commit. We've used heads so far to specify the most recently checked out commit in our Git history. In our bad snapshot example, this also happened to be the most recently created commit, but you might want to work with other older snapshots. You can target a specific commit by using its commit ID. You've actually already seen commit IDs when you've run the git log command. They're the complicated looking strings that appear after the word commit in the log messages. Here's one. The commit ID is the 40-character long text after the word commit, which starts with 59C9. This long jumble of letters and numbers is actually called a hash, which is calculated using an algorithm called SHA-1. You'll learn more about cryptographic hashes in the IT security course in this program. Essentially, what the SHA-1 algorithm does is take a bunch of data as an input and then produce a 40-character string from that data as an output. In this case, that 40-character string is the commit ID. Cryptographic algorithms like SHA-1 can be really complex. We don't go into too much detail on them here, but you'll learn more about them in the security course. I know, you're probably wondering, why on earth would you use a long jumble of letters as an ID for a commit instead of an incrementing integer like 1 or 2? To answer that, let's take a quick look at the reason Git uses a hash instead of a counter, and how that hash is computed. Although SHA-1 is part of the class of cryptographic hash functions, Git doesn't really use these hashes for security. Instead, they're used as a way to guarantee the consistency of your repository. Having consistent data means that what you've got is exactly what you expect. To quote Git's creator, Linus Torvalds, you can verify the data you get back out is the exact same data that you put in. This is really useful in distributed systems, which Git is one of, because everyone has a copy of some data, like clones of a Git repository. Computing the hash keeps data consistent because it's calculated from all the information that makes up a commit. The commit message, data, author, and even the entire history of the commit itself. The chance of two different commits producing the same hash, which is usually called a collision, is really, really small, like almost impossible. If you use a hash to guarantee consistency, you can't change anything in a Git repository without the SHA-1 hash changing too. Remember our dive into undoing things with the -- amend command? This is why it's important not to use -- amend on public commits. This means if a bad disk or network link corrupts some data in your repository, or worse, if someone intentionally corrupts the data, Git can use that hash to spot the corruption. Aha, it'll say. The data you've got isn't the data you expected. Something went wrong. But enough backstory. How can you use commit IDs to specify a specific commit to work with, like during a rollback? Well, let's say you have a commit that looks like this, and you'd like to revert it. You can use the full commit ID as part of the command, like this. That is a lot to type. Luckily, Git is smart enough to figure out the whole hash, even if you only provide the first few characters of the commit ID. If you don't provide enough of the ID for Git to make the right guess, it'll let you know. Usually, around 4 characters will suffice. The revert command generates a new commit ID to identify the rollback, and the ID of the rolled back commit is also added automatically to the commit message. As you can imagine, knowing how to pick a specific snapshot through its ID comes in handy. If you still feel like you're struggling with the basics of Git, don't worry. Lots of IT professionals have been where you are, so you're not alone. This stuff is challenging. It's totally normal to feel unsure of yourself when learning something for the first time. Sometimes that feeling of uncertainty can be a good indicator that you're heading in the right direction. Constantly learning new things is one of the awesome benefits of IT, since you'll never get bored. So embrace the discomfort. You're challenging yourself and growing. No one ever became an Olympic athlete or an accomplished programmer on their first try. Take a moment to reflect on how far you've come on this path to becoming an IT professional. It's important to remember that Git is a tool, not a programming language. There are also tools that provide Git with a graphical user interface, or GUI. You may find it helpful to explore that if you're struggling with the text-based commands. We won't be using Git GUIs in this course, and the lessons will continue to be text-based. You can always feel free to use these other tools, though, on your own. Remember that it's always okay to ask for help. The course discussion forums are an excellent resource, or you can even use other external websites like Stack Overflow. When you're an IT support specialist, you'll need to learn new skills all the time. Remember that just because something is difficult at first doesn't mean you're not capable of mastering it. Keep practicing the commands you learned in your own Git repo, or check out other sources on that topic if you get stuck. Stay the course. You've got this. The next few lessons go into some of the more advanced functions of Git. If you feel comfortable with the basics of Git, feel free to check out the next set of videos. Remember, you can always go back to the previous lessons in this course and other courses to review the material until you feel you've mastered it. And be sure to use the discussion forums to ask for help. You're not alone. If you're ready to learn more advanced features of Git, check out the next video in this lesson. If you don't feel like this material is appropriate for you at this time, that's okay. Check out the next set of videos that aren't labeled optional. Up until now, we've only briefly mentioned branches. You might have seen text like on branch master in commit messages, or you might remember that we talked about branches in the context of the head pointer. So what's a branch, and what's it used for? Great questions. In Git, a branch at the most basic level is just a pointer to a particular commit. But what it represents is an independent line of development in a project, and the commit it points to is one in a series of a particular chain of development history. The default branch that Git creates for you when a new repository is initialized is called master. All of our examples in development have taken place on this branch so far. The master branch is commonly used to represent the known good state of a project. When you want to develop a feature or try something new in your project, you can create a new branch to do your work in without worrying about messing up this current working state. If this seems confusing, maybe an analogy will help. You can think of a Git project as an assignment your teacher gives you in class. You do all your work on the assignment in a set of notebooks, with each notebook representing a different branch. You use some notebooks to jot down rough drafts and experiments, but you always keep one notebook ready to copy the polished versions of these drafts into. This is the master branch. Branches make it super easy to experiment with new ideas in your projects. When you want to add a feature or fix something, you can create a new branch and do your development there. You can merge back into the master branch when you've got something you like, or get rid of your changes without any negative impact if they don't work out. In Git, branches are used all the time as part of the normal development workflow. Let's think back to the network scanning script we wrote a few lessons ago. An improvement we mentioned that could enhance the flexibility of the script was to pass the IP address and network mask as arguments on the command line. If we used Git to manage the network scanner project, we could create a new branch and call it something like add arguments. We do the work of adding the command line argument feature to the script in that branch, then merge those changes back into the master branch once they're working correctly. Voila! Now, let's branch out into learning how to work with branches. Branches may encapsulate your changes, but they aren't actually containers for them. As we said, branches represent a pointer to a commit in a series of snapshots. The fact that they're simple pointers makes creating them easy and fast, since there isn't any data that needs to be copied around. Head points to the commit your current working directory is based on, which is usually the same as the branch that you're working on, aka the master. When you switch branches, you check out a different commit and head, along with your working directory, are updated accordingly. Head floats around with you, like a free spirit. You can use the git branch command to list, create, delete, and manipulate branches. Running git branch by itself will show you a list of all the branches in your repository. I should call out that the current branch, master in this case, is also indicated in the command's output with an asterisk and a different color. You can also use the git branch command with the -d flag to delete branches. If there are changes in the branch you want to delete that haven't been merged back into the master branch, Git will let you know with an error. It also gives you the command to run if you're sure you want to delete the branch, when you're really sure you want to get rid of it, even though the changes haven't been merged. Creating a branch is a snap. The next command will create a branch called myNewBranch, based on the value of head, which, as you'll remember, may not be the master branch. Git branch lets you do a lot with branches, but when you switch between them, you'll need to use the git checkout command. Checkout lets you navigate the branches you've created using git branch. We saw earlier how you can use git checkout to view old commits. Checking out branches is similar since the working tree is updated to match the selected branch. But when you check out a branch, the git history is also updated accordingly. To switch to the branch called Awesome New Feature that we saw listed using git branch earlier, we can use git checkout, like this. Using git branch will also tell us what our currently checked out branch is called. Before, we were working on the master branch, but now we've changed to a different branch, and it shows in the output. Git also provides a useful shortcut to create a new branch and switch to it in a single command. You can use the git checkout-b new branch to do this. When we switch to a new branch using git checkout, under the hood, Git is changing where head is pointing. In the last example, head went from pointing at the latest commit in the master branch to the most recent commit of the even better feature branch. When you switch branches, Git will also change the files in your working directory or working tree to whatever snapshot head is currently pointing at. To show this, let's create a file called feature.rb in the even better feature branch and commit it. If we run git log, we can see that head is pointing at the even better feature branch, where we just committed the new file. If we list the contents of the current working directory, we can verify that the feature.rb file is there. Now let's switch back to the master branch. Remember, the feature.rb file was committed to the even better feature branch, not master. What do you think will happen when we list the directory contents after we've switched back to the master branch? Whoa, feature.rb isn't there. What gives? This means that when you switch branches in Git, the working directory and commit history will be changed to reflect the snapshot of your project in that branch. When you check out a new branch and commit on it, those changes will be added to the history of that branch. Since feature.rb was committed on another branch, they don't show up in the history or working directory of the master. Check out the log of the even better feature branch. In the first log entry, we can see that head is pointing at the latest commit of the even better feature branch, where we added the new feature.rb file. In the second entry, we see that 3 other branches, including master, are pointing at an older snapshot of the project. So we can say that the even better feature branch is ahead of the master and other branches. If we switch to the master branch and view its log, this becomes apparent. The commits from the even better feature branch don't show up at all, and the latest snapshot is the second entry we saw before. See how since we're now on the master branch, the head pointer has been updated accordingly. The master, fix for bad bug, and awesome new feature branches are all behind the even better feature branch by 1 commit. We now know how to create and switch between branches in Git, and that each branch represents a pointer to a commit in a sequence of independent snapshots. Next, let's say that we've got our feature in pretty good shape and we want to roll it into our master branch. This is where git merge comes into play. Merging is the term that Git uses for combining branch data and history together. Using git merge, we can take the independent snapshots in Git history of one Git branch and blend them into another one. The syntax for running the merge command is like this. This will merge the specified branch into your current branch. So if we wanted to merge the even better feature branch from the last example into master, we would do this. Now we've brought the master branch up to speed, which we can see by looking at the git log. Note the -- decorate flag, which will show the branch. Since we're on the master branch, head points at master. You can see the even better feature and master branches are both at the same commit, but we've left the fix for bad bug and awesome new feature branches behind. If we wanted to catch them up, we'd have to check each of them out and merge the changes into them. Git uses two different algorithms to perform a merge: fast forward and three-way merge. The merge we just performed is an example of a fast forward merge. This kind of merge happens when all of the commits in the checked out branch are also in the branch that's being merged. When this is the case, we can say that the commit history of both branches don't diverge. In these cases, all Git has to do is update the pointers of the branches to the same commit, and no actual merging needs to take place. On the other hand, a three-way merge is performed when the history of the merging branches has diverged in some way, and there isn't a nice linear path to combine them by fast forwarding. This could happen if a commit were made on the master branch and on the even better feature branch. When this happens, Git will tie the branch histories together with a commit. This merges the snapshots at the two branch tips with the most recent common ancestor, the commit before the divergence. Sometimes you'll find that both of the branches you're trying to merge have edits to the same part of the same file. This will result in something called a merge conflict. Normally, Git can automatically merge files for you, but when a merge conflict happens, it will need a little help to figure out what to do. To demonstrate, let's edit the feature.rb file in the master branch by adding a single puts statement to it. Next, let's check out the even better feature branch and make a similar change. We've got our files all set up for a merge conflict. Let's check out the master branch again and try to merge the even better feature back into it. Git tried to automatically merge the two versions of the feature.rb file, but didn't know how to do it. You can use git status to get more information about what's conflicting. To fix the conflict, let's open up the feature.rb in our text editor. We'll see this. See how Git has added some information to our files to tell us which parts of the code are conflicting? The contents of the file at head, which point to the master here, are puts I'm on the master branch. The contents of the file in the even better feature branch are puts I'm on the even better feature branch. It's up to us to decide which one to keep or if we should change the contents of the file altogether. Let's keep the first statement, changing feature.rb to contain the following. To notify Git that we fixed the conflict, we run git add on the file. Then we proceed with the normal commit workflow. And the merge conflict is resolved. Here, resolving the conflict was easy, but in the real world, this won't always be the case. Merge conflicts can sometimes be tricky, complicated, and spread across multiple files. If you want to throw the merge away and start over, then you can use the git reset --hard command as an escape hatch. Using the --hard option can be dangerous since it will also throw out any uncommitted changes you might have. But it'll reset the files in your working tree, which gets rid of the conflicting merge. Next, we'll check out how to use and manage remote repositories, and see how you can use Git in the context of a collaborative environment. Before we do that though, you should reward yourself for getting through all that technical stuff with a break. Grab a snack, or a nap, or both, and let the concept sink in. Let's meet back up when you're rested and ready to tackle the next video. You've already worked with remote Git repositories, but you probably didn't realize it at the time. In an earlier lesson, you created, then cloned the IT support repository, copying it from its host location on GitHub to a QuickLabs workstation. This IT support repo is an example of a remote repository. A remote repository is a copy of a project usually hosted on a different computer. In this case, it's a server maintained by GitHub, usually accessible over the network. Remote repositories are a big component of the distributed nature of Git collaboration. They let lots of developers contribute to a project from their own workstations, making changes to local copies of a project independent from one another. When they need to share their changes, they can issue Git commands to pull code from a remote repository or push code into one. There are lots of ways to host remote repositories. You've already seen and used GitHub, but other internet-based Git hosting providers exist, like Bitbucket and GitLab, which offer similar solutions. You can also set up a Git server on your own private network to host private repositories. A locally hosted Git server can run on almost any platform, including Linux, Mac, or Windows, and has benefits like increased privacy, control, and customization. To understand remote repositories and Git's distributed nature a little bit better, let's go back to the analogy we used earlier. Instead of a generic school project, let's say you and a few classmates are actually working together to design a computer game. Each of you have a different part of the game you're responsible for. One person is designing levels, another the characters, while others tackle writing the code for graphics, physics, and gameplay aspects of the project. All these areas will have to come together for the final product into a single place, which is the upstream remote repository. Even though your classmates might work on their parts by themselves, sometimes everyone needs to send out progress updates to let each other know what they've been working on. You'll need to combine their work into your own portion of the project to make sure it's all compatible. Using Git to manage a coding project works in a similar way. Everyone will develop their piece of the project by themselves in their local branches, but sometimes they'll push finished code upstream to be merged into a central repository. Your local development occurs in branches like master, and Git keeps a copy of the remote repository for you in a remote branch. If someone has updated the repository since the last time you copied it to your remote branch, Git will tell you that it's time to do an update. You'll pull down the code, fix and merge conflicts that might arise, and push it upstream again. This way, Git lets lots of people work on the same project at the same time, merging their work automatically after a push when it can, and telling them to manually perform the integrations when it can't. Good stuff, Git. Good stuff. Whatever method you choose to use to host your remote repositories, Git gives you lots of ways to manage them. You added a remote repository when you ran the git clone command to copy the IT support repo from GitHub. If you wanted to add a remote to an existing repository, you could run the git remote command, passing it the URL of that remote repo. Here, instead of performing a clone, we've added a connection to the IT support repository by using the URL where it's located. We've also named the remote connection Origin, which is way easier to use when we want to reference the remote, rather than typing the full URL into our commands. We can use any name we want, but it's common in Git to use the label origin to refer to the original remote created. When you clone a repository using the git clone command, Git automatically creates a shortcut to the remote repository called origin that points back to the repo you cloned. Super helpful. It's worth calling out that Git supports a lot of ways to reference a remote repository. Some of the most common are through HTTP, HTTPS, and SSH protocols, and their corresponding URLs. HTTP is usually used as a way to allow read-only access to a repository. You can imagine that allowing anonymous, write-enabled connections to your Git repository over the web would be bad, since people would be able to push anything they wanted to your repo. Not good. On the flip side, HTTPS and SSH both provide methods of authenticating users, so you can control who gets permission to push. So what else can remote do? Well, you can list your remotes with git remote, rename them with git remote rename, and delete them with git remote rm. You can also list the remote connections and their URLs with the -v flag. Check out the words in parentheses after each remote, fetch and push. These show which URL will be used to fetch data from the remote repository, and which will be used to push data to that remote repo. They should point to the same place, since what you pushed to the push URL should be what you'd see if you immediately fetched from the fetch URL. Get it? Got it. Good. Speaking of fetching and pulling data, Git doesn't keep remote and local branches in sync automatically. It makes you execute commands to move data around when you're ready. The git fetch command lets you pull data down from a remote repository, so you can see what other people have committed. To fetch all of the branches from a remote repo, you can give git fetch the name of the remote. To only fetch specific branches from that remote, you can add the branch to the command. Fetched content is downloaded to the remote branches on your repository, where you can run git checkout on it, just like a normal branch to have a look. You can see the remote branches in your repo by adding the -r flag to the git branch command. In this case, we've got 3 remote branches in our repo, each for the remote associated with origin. Remote branches have a major difference from local branches we've worked with before. They're read-only, which means you can only look at them, but you can't make any changes. You can use the git fetch command to review the changes that have happened in the remote repository. And if you approve of them, you can use our old friend git merge to integrate them into a local branch. Hey git merge, good to see you again. Let's say you run git fetch to pull down the latest and greatest code from a remote repository, then run git status. Git status helpfully tells us that there are some commits that we don't have in our branch, by letting us know our branch is behind the remote origin master branch. We can look at the git log of the origin master remote branch to see what changed. We can see from the log that head is currently pointing to master, and that the origin master branch has one more commit, which made some updates to a file called sumscript.rb. If we want to integrate the updates to the sumscript.rb file into our master branch, we can perform a merge operation. This merges the origin master branch into our local master branch. And voila! We've merged the changes of the master branch of the remote repository into our local branch. Good work! Fetching commits from a remote repository and merging them into your local repository is a common operation in Git. It's so common that there's a command that combines the actions of git fetch and git merge into one operation, called git pull. Running git pull will fetch the remote copy of the current branch and automatically try to merge it into the current local branch. So this command will synchronize the contents of the local master branch with the contents of the master branch in the remote repository. You can handle any merge conflicts that happen from pulling from the remote in the same way we talked about earlier. You can also fetch and merge changes from a specific remote branch by providing the branch name. This command pulls changes from the origin remote master branch and merges them into the local checked out branch. We know how to fetch, merge, and pull data from remote repositories. To send data upstream, Git provides the git push command. You push to a remote repository by passing both the remote and branch you want to get to push. You may need to authenticate so that you can write to the upstream repository located at origin. For example, if you were to push to a repository hosted by GitHub, you'd probably see this prompt. You can also push all of your local branches to the remote repository by passing a flag called --all. Git will try to merge your local changes into the remote branch. But what happens if the remote repository contains changes that you don't have in your local branch? that Git can't fast forward, like we talked about with Git's merging algorithms. Push will fail and you'll get a message like this. Yikes! Once again, Git provides some helpful information along with the error message, specifically the part about integrating remote changes with git pull. This means we need to sync our local remote branch with the upstream repository before we can push, which we learned can be done with git pull. Git tried to automatically merge the local and remote sumscript.rb files, but found a conflict. Let's fix it by editing the file to remove the conflict. Then committing the newly merged file. And finally, pushing to the remote again. All fixed. Wow, that was a lot to take in. So let's review what we learned in the last few videos about working with remotes in Git. First, we talked about how remote repositories and the distributed nature of Git allow many contributors to develop a project on their own and at the same time. We learned how to pull data down from remote repositories, push our local changes up to them, and resolve the conflicts that arise when our local and remote branches are out of sync. It's a lot of information, and you might be feeling overwhelmed. It's okay to feel that way. Learning how to use a VCS like Git can be super hard, but the rewards are worth the effort. Remember that version control systems give you access to the history of any scripting project, making fast rollbacks possible and fostering collaboration and accountability. Using and understanding a VCS is an awesome skill to have in your IT support specialist toolbox, and one that will set you apart from the crowd. Now that we've seen Git in action, we know how to use a VCS to perform rollbacks of bad code. But wouldn't it be better to avoid pushing out that bad code in the first place? Definitely. Having good tests for your software can do just that, helping you catch mistakes, errors, and bugs before you deploy your scripts to perform real-world automation tasks. Software testing is the process of evaluating computer code to determine whether or not it does what you expect. When you test a piece of software, you want to find the errors and defects and see where things go wrong. Software testing is sort of like the tests performed in the manufacturing process of a new car. When it comes off the line, you want to make sure that when you push on the gas, the car will go. And when you push on the brakes, it will stop. It's the same idea with software. You want to make sure that when you run a program, it runs as it should. You've probably tested some of the scripts you've written for this class in some way already. So, if you've written a regular expression and ran it on some text to see if it worked, you tested it. Formal software testing takes this a step further, codifying tests into its own software and code that can be run to verify that your program does what you expect. Automation scripts in software can fail in all sorts of strange ways, especially as they become more complicated. In all but the most simple programs, it's next to impossible to test for everything that could go wrong. Even though this means that a certain amount of bugs may exist in your scripts without you knowing, don't worry. Writing tests can help you eliminate a lot of them, which will improve the reliability and quality of the automation. Tests can make good code great. In earlier lessons, we talked theoretically about the benefits of testing. We dove into the danger of silent failures, and spoke about how the reliability of Ruby libraries generally stems from their well-tested code. After we wrote our network scanning script, one of the improvements we mentioned was adding tests to it. In the next video, we'll take a more concrete approach to testing, examining the different kinds of tests that exist and how you can apply them to your scripts and automation. You might think that most testing happens after the code has been written. This seems like a natural chain of events. First, you write your script, and then you write the tests that verify the script does what you want. But this isn't always the best approach. A process called test-driven development, or TDD, calls for creating the tests before writing the code. It might seem counterintuitive, but can make for more thoughtful, well-written programs. When faced with a new problem that can be solved by automation, your gut instinct might be to fire up your text editor and start writing. But creating some tests first makes sure that you've thought through the problem you're trying to solve, and some of the different approaches you might use to accomplish it. TDD also helps you think about how your program could fail and break, which can lead to valuable insights and change the approach you take for the better. The test-driven development cycle usually first involves writing a test, then running it to make sure that it fails. After all, you haven't written the code to make it pass yet. Once you've verified that it fails, you write the code that will satisfy the test and run the test again. If it passes, you can continue on to the next part of your program. If it fails, you debug it and run the tests again. The cycle is repeated for each new feature of your script until it's all up and running. So, before you write your next Ruby program, you might want to think about the kinds of tests you could cook up to make sure it's working as you expect. There are all kinds of resources out there if you'd like to learn more about how you can create code using the test-driven development approach. Many of them are Ruby-centric, but the principles can be applied to any language you need to create in. There are many kinds of tests a savvy IT support specialist can use to make sure her software is working as she expects. But testing is usually spoken about in terms of being either black box or white box. White box testing, which is sometimes called clear box or transparent testing, relies on the test creator's knowledge of the software being tested to construct the test cases. With a white box test, the test creator knows how the code works and can write test cases which use that understanding to make sure everything is performing as expected. On the other hand, in black box testing, the software being tested is treated as an opaque box. In other words, the tester doesn't know the internals of how the software works. Black box tests are written with an awareness of what the program is supposed to do, its requirements or specifications, but not how it does it. So, a simple black box test could be to verify that when you type in www.google.com.br in your browser, the Google search page for Brazil is returned. You might not know how Google servers process your request, but you know what the end result should be. Both white box and black box tests have their own advantages. White box tests are helpful because the test writer can use their knowledge of the source code itself to create tests that cover most of the ways the program behaves. Black box tests are useful because they don't rely on knowledge of how the system works, which means their test cases are less likely to be biased by the code. They'll usually cover situations that the programmer who originally wrote the script didn't anticipate. Most of the kinds of tests we'll look at don't always fall neatly into one category or the other. For example, you can write unit tests that are either white or black box, depending on the testing method chosen. If the unit tests are created before any code is written based on the specifications of what the code is supposed to do, they can be considered black box unit tests. If unit tests are written alongside or after the code has been developed, and the test cases are constructed with a knowledge of how the software works, they're white box tests. Even though the tests we'll write in the coming lessons will be white box, one way isn't always better than the other way, since each gives you a different path to make your code more reliable. Next up, we'll talk about some specific kinds of tests and the roles they play in improving the quality and reliability of your scripts. We'll concentrate mostly on unit tests in this course, but it's useful to know a bit about the other kinds of tests out there and their use cases. The goal of a unit test is to verify that small, isolated parts of a program are correct. Unit tests are usually written alongside the code to test the behavior of individual pieces, aka units, like methods or classes. Unit tests help tell the developer that the code does what it's meant to do. An important part of a unit test is isolation. Unit tests should only test the unit of code they target. This ensures that any success or failure of the test is only because of the behavior of the unit in question, and not from some external factor like the network being down or a database server being unresponsive. On the flip side, integration tests verify that the interactions between different pieces of code in integrated environments are working as expected. Since unit tests shouldn't cross boundaries to do things like make a network request or integrate with an API or database, the goal of an integration test is to verify these interactions and make sure the whole system works as expected. Integration tests usually take the individual modules of code that unit tests verify, then combine them into a group to test. Regression tests are usually written as part of the debugging and troubleshooting process to verify an issue or error has been fixed once it's been identified. They're a useful part of a test suite because they ensure that the same mistake doesn't happen twice. Like, the same bug isn't reintroduced to the code. Smoke tests, which are sometimes called build verification tests, get their name from a simple concept in hardware testing. Plug the given piece of hardware in and see if it starts smoking. When writing software, smoke tests serve as a kind of sanity check to find major bugs in a program. They answer basic questions like, does the program run? These tests are usually run before any more refined testing takes place, since if the software fails the smoke test, you can be pretty sure none of the other tests will pass either. Where there's smoke, there's fire. Taken together, a group of one or more tests is usually called a test suite. Lots of different test types can create a better test suite, helping to ensure that your scripts and automation do what you tell them to. There are many more kinds of tests out there, and we've only touched on a few of the most common ones. If you're interested in learning more about how software can break and how to test for that, all kinds of books and articles have been written on the subject. As we said in the last video, the goal of a unit test is to verify that small, isolated parts of a program are correct. Verifying this correctness generally boils down to a simple pattern. Given a known input, does the output of the code match our expectations? So check out this method. How do you think we can test that it works as we expect? Let's validate that for a given input, it produces the expected results. Here, if we give the divider method the numbers 10 and 2 as arguments, we expect that it will return the number 5. The method has produced the output we expected given the inputs we provided, so it passed this unit test. The test focused on a small, isolated piece of code and validated our assumption about how it worked. Because the scope of the test is restricted to a small, specific unit, these types of tests usually run really quickly, and debugging them is simple since there is a limited number of reasons for them to fail. Choosing test cases can be an exercise in creativity, and coming up with all the different ways a piece of code might break can be pretty fun. Besides testing that the code works in the general case, you should also see what happens when you provide it with some input you might not expect it to encounter under normal operations. So what would happen in our divider code if we tried to divide by 0? Well, that looks like an error. On the plus side, we just discovered our first edge case. Edge cases are inputs to our code that produce unexpected results and are found at the extreme ends of the ranges of input we imagine our programs will typically work with. Edge cases usually need special handling and scripts in order for the code to continue to behave correctly. In our divider example, we could handle the 0 edge case by performing a simple check of the denominator before we divided anything. If we use our new method with normal input, we get the same result. But if we try to use 0 as the denominator again, we catch it with our check and print out a message to the screen. Whether or not we handle this error depends on how we want our scripts to behave. Sometimes, you might actually want your program to crash with an error rather than go on as if nothing happened. Remember that it's bad for automation to fail silently. So it's probably best if we let the divider method crash if it tries to divide by 0, since that isn't an operation which should have a real output value. Other kinds of edge cases may include things like negative numbers or extremely large numbers. These types of conditions are good to consider when writing your tests, since they can cause your code to crash or behave in unexpected ways. Better to catch it here than once it's already up and running. Now that you understand some of the principles behind unit testing, it's time to actually add tests to some Ruby code. To demonstrate the testing workflow, let's use the divider method we created in the last video. Ruby doesn't come with a built-in testing framework in its core or standard library, which we dove into in our lesson on system programming. But the test unit gem from Ruby Gems is a great package we can use to get started. So once you install the test unit gem, you can import it into your testing files by using require. Tests should live in a separate file from the code they're testing. If we save the code for the divider method in a file called divider.rb, our testing code could be added to a new file called test_divider.rb. The first thing that we need to do in our test file is import the external code we need for testing. This includes both the test/unit library, which has all the tools we need to write and run tests, and the divider code we want to test. We're off to a great start, but before we write any more code, let's take a few minutes to decide what we actually want to test. This will be a white box test since we wrote the code ourselves. So we'll use our knowledge of how it works to pick the units we want to verify. In the case of divider.rb, we've already seen some of the test input we could pass to it to make sure everything's working as it should. Earlier, we used 10 as a value for x and 2 as a value for y. We also spotted an edge case, 0. We can use the test/unit framework to encode these assumptions into tests, which can verify them. When using the test unit library, you've got to organize your test into classes that inherit from the test case class. We could write the test class for the divider like this. We've called our test class testDivider and indicated that it should inherit functionality from the test case class located in the test unit module. Have a look at the module and inheritance syntax from earlier lessons if this isn't familiar to you. Any methods we define in our testDivider class will automatically become tests that can be run by the testing framework. Let's add a simple test to make sure the divider method works like we expect with the inputs 10 and 2. In this method, which we've called test_basic, we start by setting up our expected inputs and outputs. If x is 10 and y is 2, then we expect the output of the divider method to be 5. We then use the assert_equal method given to us by the test case class we inherited from to make sure that what we've got is what we expected. The assert_equal method basically says, both of my arguments are equal. If that's true, then the test passes. If it's false, the test fails, and an error is printed to the screen when the test is run. The full code looks like this so far. Now that we've got our first unit test, how can we run it? You'll be happy to hear that the answer is pretty easily. You can run this test exactly as if it were any other Ruby program, and the testing library will take care of the rest. So you could type this at the command line. The output is pretty descriptive, printing out some information about how fast the test suite took to run, along with the number of tests and whether or not they passed. Just like that, you've tested your first code. Congratulations. Don't think we've forgotten about the 0 edge case, though. We know you can't divide anything by 0, so having the divider method throw an error is probably the right behavior for it to execute. You might be wondering how we can verify that error is thrown, but the test unit library provides an assertion for this too, called assert_raise. You can use it like this. When something goes wrong in a Ruby program, it's usually the case that an error or exception will be raised. This means that the normal execution of the program is stopped and the program will likely crash. These errors are referred to as runtime exceptions because they happen when the script is run. We saw an exception earlier when we tried to divide by 0, which looked like this. This type of exception is called a zero division error. The test unit library's assert_raise method works a lot like assert_equals. But one major difference is that instead of testing that two things are equal, it makes sure that when a particular bit of code is run, an error is raised. In this case, we tried to divide 10 by 0 in our test. We expected that this would result in a 0 division error and used assert raise to test that. The full code for the test suite now looks like this. And if we run it, we get this output. As you can see, we've now run 2 tests and made 2 assertions, both of which pass. Hooray, good work. We hope you can now see the benefits of writing tests to validate the code you write, and that you've gained some understanding about the different testing techniques available. Remember that good tests help make any automation and scripts you write more robust, resilient, and less buggy. Having reliable automation makes life better for everyone. Many companies take testing a step further and combine it with their version control systems and development process. When engineers submit their code, it's integrated into the main repository, and tests are automatically run against it to spot bugs and errors in a process called continuous integration. Even though it's useful, setting up a continuous integration process can be a major undertaking. If you use unit tests to validate the code you write and a VCS like Git to manage your projects, you'll be well on your way to more reliable and robust automation. For now, though, congratulate yourself on getting this far. We've talked a bit about operating at scale in earlier videos, but it's a topic worth revisiting because of its close ties with automation and managing an IT organization. We mentioned scalability during our earlier discussions of how automation can help keep up with the infrastructure needs of a growing business. Remember that if a system scales well, then an increase in the amount of work it must do can be accommodated by an increase in capacity. So if the web application your company provides is scalable, then it can handle an increase in the number of people using it by adding more servers to serve requests. Basically, a scalable system is a flexible one. The desired scalability of a system has lots of implications for an IT or operations department, and solving a scaling problem is never as simple as just adding more computers to the mix. IT departments need to figure out how the additional machines themselves will be prepared, how hard it is to install and configure each machine, how quickly the setup can be performed and replicated, and how many people they might need to hire to do it faster. Given what we've covered in the last few modules, you might already be thinking about how automation can help you scale IT infrastructure, which is a great first instinct. In the next few lessons, we'll look at how you can apply a concept called configuration management and automation scripts at a larger scale to manage multiple machines in an IT environment. In a large IT infrastructure ecosystem, you might have hundreds of servers organized into different groups based on the role they perform. Even without different configurations for each group of machines, maintaining them manually would be a major pain. Imagine logging into hundreds of servers, one after the other, to install and update or change a configuration file. No thanks. Provisioning, managing, and adapting a large fleet of computers in a scalable way requires some kind of automation. A common model in today's IT world is treating all of this infrastructure like code itself. This infrastructure as code, or IAC approach, revolves around the creation of configuration files that describe how a machine should be provisioned and managed. It's then combined with some automatic tooling that applies these configurations to the different nodes in your infrastructure. In this scenario, a node might be a real or virtual computer, a piece of network gear like a router or a switch, or some other IT infrastructure. IAC is usually applied in cloud computing environments, where machines are treated more like a herd of interchangeable resources and less like individual computers. IAC isn't just for managing computers in huge data centers or globe-spanning infrastructures. It can work for anything from servers to laptops or workstations, even in a small IT department. Whether your fleet of machines are virtual or physical, treating them like they aren't special is actually a good thing. If something breaks, goes down, or catches fire, literally or figuratively, you can easily spin up a replacement. This is because you know exactly what it's supposed to look like from the configuration and can deploy it easily using the automation. Having infrastructure as code also means that you can apply the benefits of a version control system to your very infrastructure. Since the configuration of your computers is stored in files, those files can be added to a VCS. You'll see in this course that you can track your chef recipes in a Git repository. This gives you an audit trail and easy visibility into the state of your infrastructure. Having configuration files means that you can also run tests on them, just like we saw before with our Ruby scripts. It's way better to find out in a test that a configuration file has a typo in it than to find out from your users. Besides, when you need to actually provision a new infrastructure resource, the steps to do it are right there in the file. You can execute the file and apply it to a hardware or virtual resource like a VM, using the associated automation you've chosen, which is nice and easy. Having infrastructure that is testable, repeatable, versioned, and automatically deployable all sounds pretty awesome. But how do we get there? A common way to manage IT infrastructure treated as code is with the configuration management system. There are lots of definitions for the term configuration management, but we'll focus on what it means for us in the IT industry. You can think of configuration management like the set of tools and engineering practices that manage the software, infrastructure, and processes that provide information technology to a company. Using a configuration management tool helps make sure that when you modify a system, those changes are done in a systematic, repeatable way. A configuration management tool can take that infrastructure as code we talked about and apply it to the systems that it manages. This makes changes efficient and consistent, which is exactly what we want. Configuration management systems also usually have some sort of automatic error correction built in, so they can recover from certain types of errors all by themselves. Let's say it was important for all the computers in the IT department to have a certain version of a web browser installed, so users could access a legacy web application. If an update was pushed out that upgraded the web browser, users wouldn't be able to get to that web app. Fixing this without a configuration management tool would probably mean logging into each computer to reinstall the right browser version. But with a configuration management system, the tool could detect that the wrong version was present, then take action to get the correct version installed on each computer. Makes your work and the employees' work a lot easier. Configuration management systems are tools that let an IT specialist or system administrator use all the benefits of IAC in one package. It provides the format for your configuration files, along with some kind of automation to deploy or apply them. Now, there are lots of configuration management systems available in the IT industry today, and an entire ecosystem of configuration management and infrastructure as code tools to boot. Some popular configuration management systems include Chef, Puppet, Ansible, and CF Engine. Most of these tools can be used to manage locally hosted infrastructure, such as bare metal or virtual machines like laptops or workstations that employees use at a company. Configuration management systems might also have some kind of cloud integration in order to manage resources in cloud environments like Amazon EC2, Microsoft Azure, or the Google Cloud Platform, just to name a few. And don't worry, I've included links to all these systems in the readings right after this video. For our lessons and demonstrations, we've chosen to use a tool called Chef. I'll get into the reasons why in the next lesson. Just keep in mind, though, that selecting a configuration management system is a lot like deciding on a programming language or version control system. You should pick the one that best fits your needs. Each have their own strengths and weaknesses, so a little research beforehand can help you decide which system is best for you. There are a lot of tools out there, so don't put any restrictions on your IT support specialist toolbox. Any infrastructure that claims to be scalable has to be able to handle the capacity requirements of growth. Performing an action like adding more servers to handle an increase in requests is just one possible first step. Other things must be taken into account, like the amount of traffic the network can handle, or the load on back-end servers like databases. In a large or complex environment, treating your IT infrastructure as code can give you the flexibility you need to scale your IT systems. A configuration management system can help you manage that code by providing a platform to maintain and provision that infrastructure in an automated way. IAC means that your fleet of nodes can be consistent, versionable, reliable, and repeatable. Instead of being seen as special snowflakes, machines are treated like replaceable resources that can be churned out on demand with the automation provided by a configuration management system like Chef. Viewing your infrastructure in this way helps your IT team adapt and stay flexible. The technology industry is constantly changing and evolving. That's what makes it so challenging and interesting. Automation and configuration management can help you embrace that change instead of avoiding it. In this course, we'll use Chef to learn about configuration management systems. What if, with a single command, you could install Apache, WordPress, and configure a server to display a website? Well, with Chef, you can do this and more. Let's start with the basics of what Chef is and how it can be beneficial for you as an IT support specialist. Chef is a configuration management system, or CM, used to configure and manage IT infrastructure, including the bare metal, virtual, and cloud-based varieties. Chef provides a suite of tools and applications to develop, deploy, and maintain infrastructure as code. We've already seen that this makes the infrastructure versionable, consistent, and repeatable, which are all super helpful if we need to scale that infrastructure while keeping it reliable. In Chef, infrastructure as code takes the form of recipes and cookbooks. Recipes are where the rubber meets the road, or to use a more Chef-appropriate example, how the sausage is made. Sausage. Anyway, Chef recipes contain Chef code, which define the desired state of a set of resources, like services or files. Chef cookbooks are used to group these recipes together in logical units, like a package for your recipes. A cookbook will contain all the instructions, encapsulated in recipes, to configure or deploy some unit of infrastructure, whether it's a web server, graphics design laptop, or router configuration. The analogy is pretty strong here. Recipes go into cookbooks. Cookbooks can also contain supporting elements like images, templates, attribute values, and other extensions. Large companies like Facebook use Chef to manage thousands of servers, which show its ability to scale. In a typical production environment, the development workflow of a Chef configuration might go like this. Create the configuration on your local workstation, test it out, then deploy it to a central Chef server to distribute to client nodes. In Chef terminology, a node is just some machine managed by a Chef server, which could be anything from a web server to a network router. Chef uses the intent-based automation paradigm. This means that you tell Chef what the desired configuration should be, not how it should get there. Sort of like how you would tell a chef your food order, but not how to cook it. So if you wanted to add a file with some text to the home directory of a computer, you wouldn't tell Chef to log into the computer, create a file, then add the text. Instead, you'd specify a recipe that had a declaration of the file in the location you wanted it with the text it should contain. Chef will read that recipe and decide how to get there itself. It's like the difference between executing this series of commands and writing this Chef recipe. As a developer of Chef configuration, You only need to tell Chef what the desired state is, and Chef will take care of the rest automatically. How cool is that? Chef tries to make the operations it performs idempotent. Here, an idempotent action means something that can be performed over and over again without changing the system after the first time the action was performed, and with no unintended side effects. Let's take another look at the recipe we saw before. Creating the file resource in this recipe is an idempotent operation. If the file already exists, then Chef will understand that no action has to be taken. If the file doesn't exist, then Chef will create it. No matter how many times Chef applies that recipe, the same file with the same text will be created. Idempotency is a really valuable part of a configuration management system or piece of automation. If a script is idempotent, then it can fail halfway through its task and be run again without negative effects. Most Chef resources provide idempotent actions, except for execute. The actions taken by the execute resource, which is responsible for running a command, are typically not idempotent. This is because they're usually unique to the environment in which they're run. Consider the result of this Linux mv command, which moves file.txt from the home folder to the desktop. What happens if we run the exact same command again after it's been executed once? We get an error because the file isn't in the same place. As you can see, this was not an idempotent action, since executing the same thing produced a different result and the unintended side effect of an error. Another important aspect of the way Chef works is its test and repair model. When Chef takes an action specified in a recipe, it only makes changes to the system if they're necessary. This means that it first tests to see if the resource being managed, like a file or package, actually needs to be modified. If the file exists in the place we want it to, no action needs to be taken. If a package is already installed, there's no need to install it again. The set of steps Chef takes to move the system into the desired state is called converging the system. You could say that Chef generally takes idempotent actions to converge the system to the state described by its configured recipes. So how does Chef know about the state of the system it's trying to manage? When the Chef client is installed on a node, it uses a program called OHI to gather information about the node. Chef client is a piece of software that runs locally on nodes and is used to apply configuration, which we'll dive into later. OHI is executed at the start of every Chef run in order to determine the state of the system. It stores this information in attributes, which are bits of specific detail about a given node. Other configuration management systems often use similar tools to gather node information, like Puppet's factor service. The majority of Chef is built on top of our good friend Ruby, even though some of the parts of it, like the Chef server, are written in a programming language called Erlang. Yes, that's an actual programming language, even though it sounds like something out of a sci-fi movie. Anyhow, our survey of Ruby will be really useful when working with Chef, since the configuration code it uses is based on Ruby. To write Chef recipes and configuration files, Chef implements what's called a domain-specific language, or DSL. A DSL is specialized computer language that's used for a specific purpose, like declaring resources within a Chef recipe. The Chef DSL is built on top of Ruby, which means that not only will it look pretty familiar, it also gives us access to the full power of the Ruby language to customize Chef how we want it. You might be wondering why Chef went to the trouble of creating a DSL in the first place. Well, by using a DSL, Chef and other configuration management systems gives its users a batch of expressions tailored to focus on the tasks of system administration and configuration. It also still allows access to the full Ruby language underneath. This means that you don't need to be a programmer to use Chef, and the configuration you write will be focused on the domain-specific goal you're trying to accomplish. DSLs aren't just for configuration management systems, though. You can find them in monitoring applications like Google's Borgmont system, build tools like Gradle, and Facebook's spam-fighting FXL. A lot of the same principles we've learned in earlier videos on writing and managing software can be applied to a DSL, since it's all just code in the end. Chef even has a style guide for its Ruby-based DSL, which can help you keep recipes clean and organized. I've put links to these sites in the next reading. Let's check out the elements of crafting a Chef configuration before we dive into an example of using Chef to configure one or more nodes. Recipes are the basic ingredients of configuration used by Chef. You write them using the Chef DSL, and they express system administration concepts in a Ruby-ish way that you'll probably recognize. Chef uses these recipes to understand how you want a system to be configured, specifically through the use of resources. Resources are statements of configuration that describe the desired state of an item of configuration, like a file, a software package, or even a script. You can use the Chef DSL syntax to define how you want your resources set up, and add them to a recipe for Chef to execute. The syntax for defining a resource and its state might look something like this. There are lots of types of resources, and each type has actions it can take and properties it can use. For example, if we wanted to make sure that Apache 2, a popular open source web server, was installed and started on a node, we might write this recipe. Given how well you know Ruby, the overall look of the recipe might seem familiar. There are two resources in this recipe. The first one is a resource with the type of package, with the name of Apache 2. The package resource is used to install software on a node, and in this case, it'll make sure that the Apache 2 package is installed. The second resource is of type service, which is used to manage services on a node. In this case, we're telling Chef in this recipe that we want the Apache 2 program to be started as a service automatically on the node. Each resource specifies an action. In the service resource, we've actually given two, grouped together in our old friend the array. In this case, the two actions are enable and start, which makes sure that the Apache 2 service will be automatically brought up on the node. There are lots of different kinds of resources that Chef knows how to work with, and you can find a list of them in the Chef resource documentation in the next reading. A resource generally has four components. The first is a type, like package. The second is a name, like Apache 2. The third is one or more properties, and the fourth is one or more actions, like install. Some of these components are provided through default values, like the package name for package resource, so you don't have to explicitly write them out. For example, since the default action for the package resource is to install it, you could rewrite that resource block like this and get the same results. Since we know a bit about recipes and resources, let's look at a higher level of configuration: cookbooks. Cookbooks generally represent a set of configuration for a single infrastructure unit or scenario, like it's stated in the official Chef documentation. One scenario might be, I need to install and configure MySQL. A cookbook would contain all of the recipes and other configuration to do just that. Sort of like how Ruby uses the Ruby Gems repository to host packages of Ruby code that other people have written, Chef offers a platform called the Chef Supermarket. The supermarket contains all kinds of cookbooks that other administrators have created and decided to share. We won't dive too deeply into the supermarket and its tooling, but it's good to know that it's available if you need it. We said an important part of having your infrastructure represented as code is the ability to test that it works. To do this, Chef uses a test-driven development environment called Test Kitchen. The Test Kitchen lets you test your recipes and cookbooks in a sandbox environment so that you can make sure they work before they're deployed to production nodes. Test Kitchen works in conjunction with some virtualization tools to create disposable virtual machines with Chef software installed on them. There, you can deploy your configuration code and test it out. Test Kitchen comes standard as part of the Chef development kit, but to use it, you might need to install some additional software to run and manage virtual machines. In the example that we'll show you in the upcoming videos, we'll use a hypervisor called VirtualBox to manage our disposable virtual machines, and a tool called Vagrant to configure them. These are just two of the tools available to perform these kinds of tasks. The Test Kitchen can support other ways to create test machines, like in cloud environments. The Test Kitchen is configured using a file called .kitchen.yml or kitchen.yaml, usually located in a cookbook directory. The kitchen.yaml file defines all of the things you need to run tests on your cookbooks and recipes. A simple example might look like this. The kitchen create command uses this file to figure out how to create the disposable virtual machines. In this case, it would use the Vagrant tool to create an instance of an Ubuntu VM. The kitchen converge command uses the kitchen.yaml file to actually apply the cookbooks from the run list to the test VM. As a final step, kitchen destroy cleans up by shutting down the VM. Don't worry though, we'll show you examples of each in the coming videos. If you're interested in learning more about Test Kitchen, you can find a full rundown of the kitchen file attributes and options in the Chef documentation in the next reading. Overall, the layout of the Chef project and cookbook might look something like this. Before we get into scalable configuration management with Chef Server, let's take a look at how Chef can make changes to your local computer by running it in client mode. In a production environment, the Chef client program will download the latest cookbooks you've added to the Chef server and apply them. It's useful to see how the Chef client works on a smaller scale before we look at the full client-server model. Along with pulling Chef code from a server, you can run the Chef client in local mode. This means that Chef will apply code you've created locally on your computer without having to talk to a Chef server. To demonstrate how the Chef client turns Chef code into configuration, let's first create a directory called chef-code. Inside that directory, we'll create a file called omelet_recipe.rb, whose contents will look like this. Now that we've got a recipe in place to create a file called /temp/omelet with some contents, let's use Chef client to create it. You can run the Chef client in local mode like this. You can ignore the warnings about config files and cookbooks for now. We'll get into that later. The important part is that you should see that a file called omelet now exists in the /temp directory. If we look at its contents, we should see the following. Sweet! Chef has taken our code and applied it, creating a new file with contents that we told it to include. if we wanted to remove the /temp/omelet file, we could write a recipe to reverse the actions we took to put it there in the first place. Let's call this file cleanup.rb.
Boom 2.
Then we can apply it using Chef Client. The file should be gone now, which we can check for ourselves.
Boom 2.
That's pretty handy for administering a local computer, but how can we scale up this configuration management stuff to thousands of computers, or nodes in chef speak? Stay tuned to find out. In order to show how a configuration management system can help maintain infrastructure at scale with Chef, let's take a tour of the Chef architecture and tool ecosystem to see how it all fits together. The Chef platform is made up of lots of subsystems and tools to interact with them. The Chef Development Kit, or DK, is a software package that has the suite of tools you can use to interact with the rest of the Chef platform. The Chef DK is usually installed on your local workstation, where you develop and test your infrastructure configuration. The Chef DK includes lots of tools to help you work with Chef, like Test Kitchen for testing Chef code, and Ohai for gathering information about the target nodes. It also has the Knife tool, which is used to interact with the Chef server and nodes. A tool called Food Critic is included as well, which you can use to detect style inconsistencies and common problems in your recipes. The DK even comes prepackaged with a version of Ruby, a veritable buffet of options. Another important part of the Chef ecosystem is called Chef Client. The Chef Client is a piece of software that's installed on each node you want to manage with Chef, which we saw in action in the previous video. It's responsible for converging the system it's installed on into the state given by the cookbooks and recipes you feed it. The Chef client is also responsible for registering and authenticating the node with the Chef server. Remember that node can mean any system that the Chef client is installed on. Even though the Chef client can be run in standalone mode, in a production environment, it's usually configured to talk to the Chef server. Chef servers are the hubs of the Chef ecosystem, storing all the cookbooks and configuration details the various nodes your IT infrastructure needs. It's important to call out that the Chef server doesn't do any of the work of applying the configuration to its nodes itself. Instead, the Chef client has to ask the Chef server for the configuration it needs, then do the work of applying that configuration to the node by itself. This brings us back to the idea of scalable infrastructure management. By structuring the system in this way, the majority of the work is distributed to the nodes instead of centralized on the server. This means that a single Chef server can handle requests for thousands of nodes before you need to think about adding another one. To interact with a Chef server, the Chef DK provides a command line tool called Knife. Installed on your workstation, along with the rest of the DK, the Knife tool can do all kinds of management operations. It can upload cookbooks to your Chef server, bootstrap new nodes by installing the Chef client, and even run SSH commands in parallel on multiple nodes at the same time. That's an especially sharp knife. To configure the Knife tool, a small .rb file is used to specify things like where the Chef server and cookbook files live. The knife.rb file is loaded every time you use the Knife tool, and it's usually stored in the home.chef directory. A simple knife.rb file might look something like this. As you can see, the path to the cookbook directory is specified, along with the location of the Chef server and some logging parameters. Also, check out the current dir line. This indicates that the variable called current dir is set to the value of the given expression. In Ruby, The underscore underscore file underscore underscore variable points to the location of the current file, in this case, knife.rb. You might then be able to guess that the current dir refers to the directory where this knife.rb file is stored. This variable comes in handy for other lines in the configuration, like client key, since we don't have to explicitly say where the admin.pem file is, the key that Chef uses to validate you are who you say you are. Instead, we just say, it's the file called admin.pem in the current directory. The same goes for cookbooks, as you can see on the last line. There are all kinds of ways you can customize knife using this file, and you can find a list of them in the next reading. The goal of this exercise is to show you the tasks and steps you might encounter during a Chef deployment, the general principles of which you can apply to any type of configuration management system you might want to use. We'll start with a well-defined goal: install and configure the Apache 2 server on a node to host a simple website. Success will mean that we can make HTTP requests to the node and get the responses we expect. In this lesson, we'll give you a hands-on look at how to manage a node using the Chef server. This will help prepare you for the upcoming assignment where you'll manage multiple nodes using Chef server. Let's set the stage. In our example, we'll be working with 2 virtual machines that are already up and running. Each already has the Ubuntu operating system installed. One of these machines has the Chef server program already installed, while the other has Chef client installed on it and represents a node. The architecture looks something like this. On the development workstation we'll be using, we've already got the Chef development kit installed. This means that the tools we spoke about earlier, like Test Kitchen and Knife, are all ready to go. This is the same kind of environment you'll begin with in the exercise at the end of this course. We won't expect you to create virtual machines and install Chef and the Chef DK yourself. Instead, we want you to be familiar enough with a Chef workflow that you can create some configuration on your own. If you're interested in how to create this environment from the ground up, check out the supplemental reading at the end of this lesson. A configuration development lifecycle typically involves a few steps: planning, development, testing, and deployment. These can be repeated as needed to create and push your configuration out. Let's start with a plan. We'll hash it out in the next video. Welcome back. So, it's time to cook up a plan. We know that we want to be able to serve a website on our node using the Apache 2 server. If we wanted to set up a web server without using Chef, we could think of a few tasks that might be involved. 1. Install the Apache 2 program onto your machine. 2. Make sure the Apache 2 service is running. And 3. Create an HTML file in the right place to represent the web page we want to serve. If we think about these steps in the context of a Chef recipe, we can see that there are 3 resources we'll end up needing: a package resource to install Apache 2 on our node, a service to make sure that Apache 2 is running, and a template to represent the HTML page. We've seen packages and services in action already. A template resource is pretty similar to a file resource. It will create a file on the node in the location that you specify. But it also has the ability to expand variables and statements you write in it using Ruby. See how this recipe defines a template file. This tells the Chef client that we want a file called index.html to be added to the /var/www/html directory, and that it should be built from a template called index.html.erb. In Apache 2, the /var/www/html directory is special because the Apache 2 server expects the default website file to be located there. The template file itself might look like this. The template file is just an HTML web page with the extra extension .erb to indicate that the variables inside of it can be expanded. These variables are anything between these delimiters. In this case, the web page will display a greeting with the hostname of the machine which is serving the request, our chef node. Given all of this, we can guess that we'll want a recipe to perform the 3 tasks we outlined earlier, along with a template file to represent the web page we want to serve. To organize all of this, we'll want to store it in a cookbook, which we'll first test and then push to our chef server and nodes. In the next video, we'll create the configuration. See you there! Now that we've got a plan, let's start creating the directory structure for our project. We'll begin by creating a folder on the local workstation called Chef Project. Inside that, we'll want to have a folder to hold our cookbooks. We can just call that directory Cookbooks. Next, we need a cookbook. Let's dip into the tools that the Chef Development Kit gives us to automatically make one for us. We can do this with the chef generate cookbook command. We want to store our cookbooks in the cookbooks directory, so let's switch to that and run the command. The chef generate cookbook command sets up a whole set of directories and files for us. We can use them to organize recipes, templates, and other resources. It also initializes a Git repository, so we have version control out of the box. The directory structure for our project looks something like this now. There's a lot of stuff in there that Test Kitchen has created automatically for us, like the test and spec directories and the contents. You can also see how we've got a kitchen.yaml file, so we can start testing right away. You can read more about all of the different things that Chef Generate Cookbook does in the next reading. For now, we'll focus on writing a recipe. Chef Generate Cookbook has created a recipes directory for us, along with a default recipe. We can use this default.rb file to create the recipe we'll need to install and configure a web server on our node. Let's open it up in a text editor. Aside from app update, we've gone over most of the different resources used here and the actions they take. The app update resource is just used to update the package lists for software managed by the Ubuntu Advanced Packaging tool. We'll need to update these package lists before we can install the Apache 2 package to make sure we get the most up-to-date version. Let's move on to creating the template file. We could manually create a template file in our cookbook, but once again, the Chef DK comes to the rescue with an automatic command. We'll make sure we're in our Apache 2 cookbook directory, and then run this. If we list the contents of the Apache 2 cookbook directory now, we'll see that a new folder called Templates has been created, containing a file named index.html.erb. Awesome. In this template file, we'll write the HTML that our web server will display. We can use the example template we saw earlier. we're really cooking now. We've got a cookbook called Apache 2 that holds a completed recipe and a template file to configure our web server with. We probably shouldn't deploy it directly to prod though. Let's test it out first. We'll do that in the next video. See you in the test kitchen. We've gotten our cookbook, recipe, and script file all set up. But how do we know it works? Let's take this shiny new configuration out for a spin using the test kitchen, which comes installed along with the rest of the Chef DK. Remember that when we ran the chef generate cookbook command to set up our cookbook directory, Chef automatically created a kitchen configuration file for us in kitchen.yaml. This file has been preloaded with the information we need to start a disposable virtual machine to test our configuration out on. To test our configuration out, first we need to create a virtual machine. We can do this with the kitchen create command, run right from our cookbook directory. Kitchen will use the contents of the kitchen.yaml file to bring up a virtual machine by running Ubuntu with Chef Client installed on it to test out our cookbook. When it finishes, we can verify that everything is set up correctly by running kitchen list. Notice that the last error column shows none, indicating that everything went off without a hitch. Perfect. Now we can actually apply our Apache 2 cookbook to the VM Kitchen has made for us. We'll use the kitchen converge command to do this. This will suck up all the files in the cookbook and send them to the Chef client on the test machine to apply. Even though we didn't get any errors during the converge step, we should probably verify that Apache 2 is installed and the website is up and running. Chef provides automated ways to do this, but we won't cover them in this course. Instead, we can check that the page is up and running by manually making a request to it. Kitchen provides a command line tool called kitchen exec that lets us send any command we want to the test VM that we made with the kitchen create. We want to make sure that the web server is up and running, so we can use the curl terminal command to make a request for the home page and execute it against the VM with kitchen exec. Curl can be used to make requests for files like web pages from other computers. In this case, the test VM is running virtually on our development workstation, so we can just use the localhost address to reach it. We'll combine curl with kitchen exec like this to request the homepage of the web server. Sweet! The response is the HTML page that we saved in our template, and it's even been expanded to contain the hostname of the test machine. Since we made sure that the web server is working, we don't need the test VM anymore, and we can tear it down. Test Kitchen gives us the kitchen destroy command to tidy things up. Now that we tested our cookbook works properly and everything is cleaned up, the next stop in our journey is deploying the Apache 2 cookbook to our Chef server and updating the client node. Before we jump in, it's worth calling out that you don't have to do all this testing by hand. There are actually lots of tools available which can automatically test your recipes in cookbooks, like ChefSpec and ServerSpec. These frameworks can do things like automatically run unit tests to verify your cookbooks will work the way you expect, all without having to fire up Test Kitchen manually. I've included links to these tools in the next reading so you can check them out. Otherwise, I'll see you in the next video where we'll be deploying the Apache 2 cookbook and updating the client. Before we dig into the deployment process for our cookbook, let's review what we've done so far. Remember that the infrastructure we're working with looks something like this. All of the development we've done up to this point has been on the local workstation. So far, we've created a directory to hold our project. In that directory, we generated a cookbook and associated files with chef generate commands, which we have access to from the chef DK. We then use Test Kitchen to spin up a sandbox environment in the form of a virtual machine on our workstation to test our cookbook out. As a final step, we cleaned it up after we verified that everything was working. The next part of the process requires us to go beyond local development. We'll need to interact with one virtual machine running the chef server and another virtual machine running a chef client. Remember that the chef server is the hub of a chef ecosystem. It's a place where you can store all of the cookbooks and configuration details that your infrastructure needs. In this case, we need to get the Apache 2 cookbook we wrote up onto the chef server. The knife command line tool is used to interact with the chef server. For security purposes, chef server uses some mechanisms to make sure only the right users have access to it. In any configuration management system, it's good to have these kinds of mechanisms in place to make sure the system can't be abused. You wouldn't want an attacker to install malicious software on all the nodes in your infrastructure. So, in order for us to send commands to a chef server with the knife terminal command, we'll need to have a way of proving we should have access to the server. Chef controls this by using two files, a key and a certificate. Both should be stored on the development workstation next to the knife.rb file in the .chef directory. You'll learn more about RSA key pairs and SSL certificates in the next course. For now, just know that the chef server uses these files to make sure each request, like from the knife tool for example, is properly authorized and authenticated. These files are stored in the .chef directory, which in our case looks like this. We generated both the key and certificate when we set up the chef server. They'll be provided to you in the assignment at the end of this module, so you won't need to create them yourself. But if you'd like to learn more about the security model Chef uses, you can check out the security section of the Chef docs in the next reading. Now that we know that Knife is set up and our requests to the Chef server are secure, let's see it in action. We'll use it to upload the Apache 2 cookbook we created to the Chef server. That looked like it worked. We can use Knife to query the Chef server to get all kinds of information. We can use it to verify the server has the Apache 2 cookbook. Now that we've got a cookbook hosted on the Chef server, we can kick off a run of the Chef client on our node. In this case, our node already has the Chef client program installed on it, so it's just a matter of kicking off a Chef run. We can use Knife for this too, along with the SSH subcommand. We can use Knife in this way to make an SSH connection to our node, then run any command there. Take a look. Let's unpack what we just did. We use Knife SSH to search for a node named node1-ubuntu, then connected to it on port 22 with a username and password, both of Vagrant, in order to run the uptime command. Uptime is a small utility that tells us some information about the computer where it's run, like how long since its last reboot, and how many users are currently logged on. We can see that the node named node1-ubuntu returned this information and printed it to the screen. One of the neat features of Knife is its ability to connect to multiple nodes and run a command on all of them at the same time. Knife does this by returning a list of servers based on the search query you provide it. So, if we had multiple nodes in our production environment, we could change our command to this to print out the uptime of all of them. In this case, we searched for any node with a name, which is all of them, and then ran the uptime command on all of them. This can be both useful and dangerous. You can imagine situations where sending an incorrect command to all the nodes in production would be a total disaster. We'll talk about a better way to manage updating many nodes at once later, when we have a look at configuring periodic Chef client updates. Now, we know a bit about Knife SSH, so let's use it to execute the Chef client command on our node. This seems to have worked, but check out the warning message we got. Node1-Ubuntu has an empty run list. A run list is an ordered list of recipes that the Chef client will apply during a run. Even though we've got our cookbook in the Chef server, our node doesn't know about it yet. Let's tell it about the Apache 2 cookbook by adding it to the node's run list. Cool! Now our node knows what we expect to apply when Chef client is run. We'll revisit the Knife SSH command to initiate a Chef client run. We've just performed a run of the Chef client on our node. Using the run list as a guide for what to do, the Chef client queried the Chef server and retrieved the default recipe out of our Apache cookbook, along with the template file it needed. Apache 2 was installed and the template copied to the right directory. It seems like everything worked, but there's one last test we can do to verify it. Let's request the home page from our node. Hey, it totally worked! We've used Chef to develop, test, and deploy a functional Apache 2 server that responds to requests. Great job! One thing you might be curious about is how this process can scale. Manually pushing the new role list and cookbook might have worked fine for deploying a single web server, but what if you needed to spin up 10 or 100? The Chef Knife program and some other utilities can create connections in parallel to multiple nodes, but the better solution would be to have the client programs, in this case Chef client, automatically pull the server from time to time to get updates about their configuration. In our example, we wanted to demonstrate some of the ways you can administer nodes, like initiating Chef client runs with Knife and adding roles. In the next exercise, we'll give you an environment where the nodes run the Chef client program automatically in order to pull updated cookbooks and recipes from the Chef server. You can imagine that this solution will scale up much better since the nodes do all the work without pesky human intervention. Out of the box, Chef gives you a platform and tools to manage your IT infrastructure. But Chef is flexible and expandable too, and can be customized in lots of different ways. The most obvious place for customization is the recipe code that Chef Client applies to nodes. We've seen a few examples of the resources we can use, like package, template, and file, but Chef has many more, including the script resource. This resource can execute arbitrary programming code using one of the many available interpreters, like Bash, Ruby, or Python. This allows you to apply pretty much any action you can think of to Chef nodes, like changing the color of the Bash terminal or displaying custom messages to users when they log in. Chef even supports the ability to add custom resources, so if you need to perform some type of task that's super specific to your environment, you can create a resource to do it. Along with resources, you can also modify the tools Chef provides in the DK. Take Knife, for example. It can do a lot already, like uploading cookbooks to the Chef server and bootstrapping and managing nodes, but it isn't restricted to just these tasks. You could create a Knife plugin to manage nodes in a specific cloud environment, like AWS, or display a warning if the user is executing a particularly dangerous Knife SSH command, like rm-rf. The programming skills you've learned in earlier modules will be super helpful if you ever need to do some customization of your organization's configuration management environment. Having a flexible platform to manage your infrastructure is a major plus in the IT industry, since new technologies are constantly cropping up. The ability to extend the way you manage your infrastructure can help you adapt, keep pace, and keep scaling. With these basics of Chef configuration, architecture, and tooling covered, let's dive into an example of a configuration management workflow using what we've learned. In the next videos, we'll go step by step through the phases of creating, testing, and deploying a cookbook to manage a Chef server and node. But for now, let's test your knowledge with a quiz. Let's recap the workflow we just followed. We started with the goal of getting a web server up and running on a node managed by Chef. First, we planned out what we needed to do to achieve that goal. Then, we jumped into the development phase to write the configuration to execute our plan. To make sure it worked, we tested that configuration in a disposable sandbox environment. After making sure things went like we expected, we turned to our production environment and deployed our configuration. Even though the example used commands, terminology, and tools that were mostly Chef-centric, the configuration management development process we've used is more generally applicable. It might have seemed like a lot of work to set up a single web server, but we hope that you've begun to realize some of the benefits that using a configuration management system can bring to an IT organization. For example, you've seen the installation and configuration process of a web server distilled into code as a Chef recipe, and have been introduced to some of the ways you can test it. Pretty awesome.
I have to say, this is an amazing career and it's an amazing space to work in. You really can achieve things you never thought. Being a problem solver doesn't just help you in your career, right? It can help you in your day-to-day life and to achieve things that you want in other aspects as well. I think one of the things, if you want to have a sustainable career, is that you have to realize that, especially in technology, that things are going to change and you're never going to be done, right? And once you understand that, you embrace that, there's going to be times when you don't know something and you just need to learn it. And you can have these really big goals that, you just can't get to them because they're so far away. So the more you can break it up into smaller pieces, what would be the halfway point? And then what happens is you get really good at working out what the logistics of solving big problems entails, but it also gives you a starting point, and you start aiming at smaller goals and you work up to it, which allows you to actually auto-correct when things aren't going well and recognize when you need to change directions, because I break down the problem that way. And if you're willing to work hard and dedicate to learning and embracing technology and making that more accessible to others, you really can get to this level.
Okay, time to put your brain on high alert, because in this lesson, we'll talk about the concept of automated alerting and the role it plays in a monitoring system. I promise, no more alerting puns from here on out. But before we dive in though, what do we mean exactly when we say alert? You can think of an alert as a machine-generated notification of a problem, meant for a human to read and then act on. Alerts usually take the form of some kind of electronic communication, like emails, tickets, or pages. To drive home just how important an automated alerting system is, let's do a rundown of the alternative. Imagine that you've set up a whole bunch of monitoring. You've got well-annotated graphs and great metrics, and it's all organized into easily accessible dashboards. You can pick any part of the system and in a few moments know what's going on with it. You feel pretty good that you'd be able to spot failures and issues and have the right tools to debug them when problems crop up. At some point though, you'll need to go home. As fun as IT work can be, it's important to do something else in your free time that doesn't involve staring at monitoring data. But once you stop looking at the graphs, how will you know if something goes wrong? You'll be back in the situation where users will find out about problems first, unless you happen to get lucky and catch the issue by looking at the right graph at the right time. But luck isn't a good strategy. Relying on luck to build a reliable system isn't exactly reliable. One way to avoid doing constant monitoring yourself is to hire more IT employees to help monitor the system for problems. But remember our discussion on scalability? Solving a problem by adding more people to it is rarely a scalable approach to fixing something. Instead, a better solution is to use automation and have computers instead of humans watch out for the problems. That's what we have alerting for. When something bad happens in our systems, it should be detected quickly and automatically. The automation should also send us a notification that an issue has come up. Then we can use dashboards, graphs, and logs to dig into and fix the problem. In the broadest of terms, an automatic alerting system is a program that takes the value of a metric, compares it to some threshold, and fires off an alert if the value exceeds the threshold. These checks are performed on a regular basis, so issues don't slip through the cracks. That means problems will be detected anytime, like in the middle of the night, or when you're in the server room running cables. Even better, computers won't get tired or bored like people sometimes do, so they won't miss anything you tell them to look for. Alerting systems are usually configured by setting up rules to define the situation that should be alerted on. Just like with metrics and graphs, the implementation details of how these rules are specified change from tool to tool. But most systems will provide a few standard parameters to construct alerts. Some common parameters include the alert expression, threshold, duration, and severity. Let's say we wanted to create an alert that fires off if the amount of available RAM on a host node falls below 500 megabytes, signaling that it's running out of memory. In the Prometheus rule configuration language, this might look something like this. Let's unpack this. We start out with a comment explaining what the alert does, followed by a succinct and informative name for the alert, low node memory. The actual condition we want to alert on is on line 3. The if statement might look familiar to you from our lessons in Ruby programming logic, and it performs a similar function here. This is the expression portion of the alert, which will evaluate to either true or false, depending on the threshold. Here, the alert threshold is set to 500 million bytes, which translates to 500 megabytes. So if the value of the metric node memory available is less than 500 megabytes, the expression evaluates to true. Setting the right threshold for an alert is super context specific and depends on what makes sense for your system to use. We've chosen the 500 megabyte value randomly. If the node only has 550 megabytes of memory in total, it makes sense to set the threshold way lower. We can see the duration given on line 4. The duration is how long the expression has to evaluate to true in order for the alert to fire. You can use the duration to reduce the number of false positive or noisy alerts. To do this, you'd set it so that the alert only becomes active after the expression has been true for a sustained period of time. This can filter out the real problems from the short-term issues that might be caught by a shorter duration. Some conditions are so critical that you might want to trigger an alert even if they've been true for a short time, like a presence alert. This alert indicates whether or not a node is reachable at all because it's a test for its presence. Going back to our example, the severity label of the alert is set to page on line 5. As you might have guessed from its name, the severity assigned to an alert should indicate just how much of a problem it represents if the alert does fire. Alert severities and their meaning may change from company to company. Some common ones include page, ticket, and email, each representing the communication method used to deliver them to a human. Typically, page-level alerts are the most important because they cause a lot of disruption to the human receiving them. We'll dive deeper into severities in a later video when we get into alerting philosophy. But when we refer to a page, we're talking about an alert that's delivered to the human responsible for fixing the problem in an intrusive, noticeable way. In the past, this sometimes meant that pages were sent to an actual pager device that would vibrate and ring when it received the alert. Remember pagers back in the day? Now it's more common for pages to be delivered to something like an app running on a smartphone. Lots of paging systems can also be set up to use notification methods like text messages and phone calls, or even through chat applications like Slack. Whatever method you pick, the purpose of the page is to bring attention to a severe problem that a human needs to fix in a noticeable way. You might be curious about the annotations section of our alert rule example. It is both a brief summary and a description. Most alerting systems will give you a similar way to add some additional information that can be delivered along with the alert. Like the axis labels and titles we talked about in our visualization discussion, good metadata can help the human receiving the alert hone in on the problem faster and reduce the MTTR. In our example, we've added a summary and description, but you could easily provide additional information that would help with troubleshooting. You could add a link to a playbook server with relevant tips for responding to a low memory alert, or a pre-built dashboard that has memory-related graphs. When taken all together, the alert we've written might be translated as, if the available memory in a node has been less than 500 megabytes for 30 minutes, then a paging alert should be triggered containing a summary and description of the situation. In a real IT department, there could be lots of alerts like that. They'd be defined using rules like these specific to the monitoring platform and saved as configuration files. So what kind of tool would you pull out of your IT support specialist toolbox to organize and manage those rule files and configurations? If your thoughts turn immediately to version control, your instincts are good. If not, don't worry, you'll get there. Using a VCS is a really great way to maintain alert rules. This is especially true since these files should be updated regularly to make sure the expressions and thresholds don't fall out of sync with the reality of the systems they monitor, or, to borrow a term from an earlier module, suffer from bit rot. The ability to track modifications, get change context, and roll back and forward are all VCS tasks that are useful to maintaining a healthy alerting config. Of course, this can also extend to dashboards and graphs if the visualization tool you've chosen allows you to store the definitions as configuration files, templates, or code. In an earlier module, you learned about how software tests can be classified into two broad categories, black box and white box. It might surprise you to learn that monitoring can also be broken out into the same categories, based on the level of visibility into the system they have access to. This might seem confusing at first, but we can clarify the concepts a bit by looking at situations where we might use one type instead of the other. In our monitoring and alerting examples so far, we've focused mostly on the white box side of things. In a white box monitoring system like Prometheus, you can inspect the insides of the system by instrumenting the host operating system or application code to collect the specific metrics you're looking for. You know how the system works, and you can use that knowledge to pick the things that you want to keep tabs on. White box monitoring can give an IT support specialist or system administrator insight into the different parts of a technology stack. This provides detailed information for debugging purposes, impending problems, or immediate issues. Alerts you create from a white box monitoring system can identify two things: the cause of the problem, like the database is sure slow to respond to read operations, or it can identify its systems, which are issues like none of our users can log in. On the flip side, black box monitoring doesn't have visibility into or knowledge of how a system works. Instead, it concentrates on the ways it behaves as an end user would see it. Because it has no way of peeking into system internals, it can't be used to figure out if a server is approaching its memory limit, but it might be used to alert you that the server has locked up and is no longer responding to requests. So, alerts generated from a black box system are based on the symptoms of the problem, or the errors presented to a user at that moment. A common method of performing black box monitoring is through the use of a prober. A prober is a piece of software that issues logical checks or probes against endpoints exposed by the monitored system. This happens at a regular interval. Then the prober reports the result of the check. When we say endpoint, we can mean any public interface that receives requests. A common example is the HTTP endpoint, which is given by a URL handled by a web server. So the /browse page on www.coursera.org could be considered an endpoint. Probers usually model some kind of end-user interaction with an endpoint, like logging into a website or sending an email by interacting with the mail server. At this point, we've learned the programming skills necessary to create a prober script to check an external endpoint. You can even think of the network scanner script we wrote in an earlier module as a basic prober. It issued requests or probes to the ICMP endpoints of all the machines in the local network, then informed you of the results. We can do something similar with other endpoints. For example, the following Ruby script will send a probe every 30 seconds to the homepage of www.google.com, triggering a response from the Google servers listening there. Whether or not the probe succeeds or fails, an appropriate message will be printed to the terminal. Check it out. The output of this script at the terminal would look something like this. This script uses the URL and net HTTP libraries to create and send the HTTP request. If the response code from Google indicates success, like if it has an HTTP 200 code, the probe succeeded. If the response is anything else, the probe failed. The script also uses an infinite while loop to continuously send the probes, along with the sleep method to wait 30 seconds between each loop iteration. One thing you might not recognize in the code is the call to signal.trap. This just means that when you hit the Control-C keys to exit the script by sending the SIGINT signal, the program will quit gracefully. You can probably think of some improvements to the script given our earlier discussions. Like, it might be useful to create an email alert if too many probes fail, or a way to visualize the success or failure of the probes in a more central location than the terminal. Even though you can always turn to your programming skills to write your own custom black box prober, there are some pre-built tools out there that might fit your needs. For example, Prometheus offers a program called the Black Box Exporter that facilitates probing all kinds of endpoints like HTTP, ICMP, DNS, and more. I've linked to the exporter in the next reading. Although we've talked about the usefulness of alerting and the basic mechanics of creating an alert, let's include a little philosophy around the alerting space. Just like the best practices we learned about when making graphs and visualizations, there are a few principles you can follow to help guide you when creating a new alert. First, think back to the 4 signal types we covered in an earlier video. I'll give you a refresher. They were latency, traffic, errors, and saturation. Those signals aren't just useful for creating graphs, they can also be used to create alert rules too. Whatever kind of system you run and from wherever in the stack your metrics are coming from, you'll probably want to be notified if your system reports a large change from any of those signals. So it's good to have some alerting rules that cover them, even though the specifics may depend on your particular situation. Your monitoring system should help you answer 2 big questions: what's broken and why? We talked about symptoms and causes in an earlier video. The symptom is the what's broken, and the cause is the why. When you create an alert, it's generally more worthwhile to focus on catching symptoms rather than trying to capture causes. Symptoms usually indicate an imminent and real problem with the system. Something like, users are experiencing high error rates when accessing emails. This symptom could have one or more causes that should definitely be investigated, but not always alerted on. Alerting on causes can introduce noise into a monitoring system, which makes it harder to pick out the relevant signals. So, cause-based alerts might trigger even when there's no associated symptom, causing an alert that users don't notice and with no action for a responder to take. At other times, triggering several cause-based alerts could be a waste of time. The problem has already been surfaced by a single symptom-based alert. Even though a good rule of thumb is to focus your efforts on symptom-based alerts, there are exceptions. The presence alerts we covered earlier are cause-based alerts that can be very useful to have, since notification of widespread node deaths is a relevant and actionable signal to have. A good signal-to-noise ratio is important in a healthy monitoring system. When alerts occur too often, human respondents can become desensitized to them. If alerts aren't investigated properly or are even ignored, then the real problems the system is suffering from can get lost in the background noise of bad alerts. Over-alerting can be just as bad as under-alerting. Also, keep in mind that every alert isn't always an emergency. Some alerts might indicate a problem that will become worse over time, but isn't a threat to the system at this moment. This is where setting an appropriate alert severity can be helpful to categorize issues. Filing a ticket might be a good method of alert delivery for a slow memory leak on a single server, while sending a page directly to a human for immediate action might be necessary if the system suddenly loses half of its network capacity. There's a human cost incurred each time a pager goes off. It interrupts whatever the responding person was doing at the time. They might be working on an IT project, or in a meeting, or even asleep in bed. The spike of adrenaline and stress takes a toll. You can only respond to a page with a sense of urgency so many times in a single day before fatigue sets in. So all pages should be actionable. If an issue is worth paging on, it should represent the kind of situation that can only be solved by a thinking human. If the problem can be reduced by a response from a computer, then that automation should be written and the alert removed. Remember that a good monitoring system will evolve and adapt alongside the systems it monitors, and that a VCS makes managing frequent changes easier and safer. If a threshold or severity doesn't make sense anymore for a particular alert, don't wait to update to a better value. If an alert is no longer necessary or useful, just remove it. Regular tending and upkeep can help keep your monitoring systems healthy and useful, avoiding noise and alert fatigue. At this point, you know a bit about alerting and how it fits into a monitoring system. We've talked about how you might use alert rules to automatically generate alert notifications based on the metrics you collect, the parameters used in those rules, and some things to keep in mind that can help guide you when deciding what to alert on. From company to company, an IT department may configure monitoring and alerting systems in different ways, using different tools to manage and deploy them. The information we've covered so far should be generally applicable. Your paging alerts should be actionable, whether you use Prometheus or Nagios as a monitoring platform. And a good dashboard organization and use of VCS is applicable whatever system you've selected. Choosing a centralized monitoring system might seem like a daunting task if your IT department doesn't have one in place already. There are a lot of solutions available in the industry today, and no real consensus on what the best tools for the job are, since what constitutes good can be very context-specific. Some monitoring platforms like Datadog and Wavefront offer a cloud-based system for a fee. Others, like Prometheus and Ganglia, require you to install a monitoring server and possibly monitoring agents in your own infrastructure to record metric data. Software like Nagios and the Elastic Stack offer options for both cloud and self-hosted solutions. There are lots of ways to collect metric data too. There's application instrumentation with client libraries. We saw an example of this with the Ruby Prometheus library. You can also use tools like sysdig or collectd. There's a lot to choose from, and we haven't even gotten into the visualization tools like Grafana or alert delivery systems like PagerDuty. And don't worry, I've put links to more information on all of this in the next reading. If you do need to select a monitoring platform to get insight into your infrastructure, it's helpful to keep some of the touchstones of good automation that we've talked about in mind. First, you want to choose a monitoring system that's scalable. When you need to expand the amount of nodes you monitor or increase the amount of metric data you store, how easy is it to scale up the system to handle it? Next, you'll want a monitoring system that's reliable. During an emergency, your monitoring system will be on the critical path to fixing the problem, so it's vital that the system is there when you need it. In a large deployment, you might even consider the system's options for meta-monitoring in order to keep track of the monitoring systems themselves. Finally, a good monitoring system should be as simple as possible. Managing the collected metrics and making changes to alerting rules should be straightforward. If it's hard to do these kinds of things in a monitoring system, then it becomes much easier for bit rot to set into it, causing bad alerts, useless metrics, and increased noise polluting the system. Keep it simple, and you'll go far. Now that we've covered the basic concepts of a monitoring and alerting system, it's time to see one in action. In the next lesson, we'll look at how you can collect, display, and alert on metrics using the Prometheus monitoring platform and some associated tools. Before that, though, let's take a quiz to see how you're doing. In the next few examples, we'll check out how to set up some host and application level monitoring using Prometheus. At the host level, we'll zone in on the CPU, memory, and disk metrics. At the application level, we'll create a simple Ruby web server and use a prober to make sure that it's up and running. Let's get started. Even though Prometheus is a white box system that mainly focuses on application level monitoring, it does have exporters, which are pieces of software that extend its functionality. We'll be using two of them in this lesson. The node exporter, which can collect operating system and hardware metrics and export them to Prometheus, and the black box exporter, which can issue probes to exposed HTTP and other endpoints. For Windows host level metrics, Prometheus recommends using the WMI exporter instead of the node exporter. You'll find links to all of these in the next reading. We'll also be using another Prometheus component called the Alert Manager, which, as you might guess from its name, handles the alerting portion of the monitoring system. At the end of this example, we'll have a working monitoring platform with graphs and alerts configured to tell us exactly what's going on in our infrastructure. Lots to cover, so let's get to it. Before we can use Prometheus, let's learn a little bit about how it works. Prometheus is an open source white box monitoring system inspired by Google's Borgmon monitoring system. A central Prometheus server collects metrics from properly instrumented programs or jobs, like Ruby scripts, and exporters, like the node exporter we just talked about. Jobs and exporters first export their metrics in a way that the Prometheus server can find them. Then, the server comes along and scrapes them at regular intervals, storing these possibly aggregated metrics as time series data in a database. The information from this metric database can then be queried and used to create alerts, or exported to visualization tools to be graphed. There are a few installation methods for the Prometheus server and its associated components and exporters. Some of them include pre-built images managed by Docker, installation through configuration management systems like cookbooks for Chef, and pre-compiled binary programs. Of course, since Prometheus is open source software, its source code is also available to download and build. Whichever installation method you choose, instructions can be found in the Prometheus documentation, which is really detailed and very useful. You'll find links to these in the reading right after this video. In this next video, we'll have the Prometheus server, alert manager, and exporters all installed in our local machine for simplicity's sake. Keep in mind that in a real production environment, you'd probably have a node dedicated to hosting the Prometheus server and alert manager, with the node exporter installed on the hosts you wish to collect metric data about. The black box prober might be installed on a different node still to further isolate your monitoring infrastructure from your production machines. But we're keeping it simple for you in the next video. So let's get started. With the Prometheus server installed along with the black box and node exporters, let's examine the host level metrics we'd like to collect. The documentation for the node exporter tells us that there are many statistics enabled for collection by default when the exporter is run, and several more that can be turned on if needed. For example, to just collect metrics about the CPU of the host, you could run the exporter like this. Remember how we talked about the Prometheus server scraping the metrics exposed by the node exporter? Well, you can see a full list of them at the /metrics HTTP endpoint provided by the node exporter. This runs on port 9100, as you can see in the earlier output. If you look closely, there are even metric descriptions above the metric names, which can help you figure out what each one does. You can access this endpoint using a browser, like this. We'll want to see statistics about CPU, disk, and memory, so leaving the defaults works for our case. This gives us access to those metrics, and more. Now that's a lot of metrics. Now that we're collecting information about the operating system and hardware, we'll need to start up the Prometheus server and tell it where to find that information. This is done in Prometheus by specifying targets. Are you up for some target practice? The Prometheus server learns about the targets it should scrape from a configuration file, which we'll call prometheus.yaml. This configuration has details about things like what needs to be scraped and how frequently that scraping should happen. To set up Prometheus to collect metrics from the node exporter, our YAML configuration file might look something like this. Here, we've set up a job called node to have its metric endpoint scraped every 15 seconds, and told Prometheus that it can be found at the localhost:9100 address. Again, we've used localhost in our example, but in a production environment, this could be something like an IP address and port of where the node exporter is running. We have a config, so let's use it. The Prometheus server itself could be started like this. The server is now up and listening at port 9090 using the prometheus.yaml file we wrote to guide it. We can access the web-based interface by visiting localhost 9090 in a browser, where we'll be presented with an expression browser. If we type in the name of a metric that the node exporter is collecting, we should see it auto-completed in the expression field. Let's have a look at one of the CPU metrics, node_CPU. The console tab in the Prometheus GUI is now populated with many metrics representing statistics about the CPU activity on a host. In Prometheus, metrics have a specific notation, which looks something like this. The metric name here is node_CPU, and the labels inside the curly brace delimiters add details about where the metric was collected from and other information. Any combination of labels for the same metric name identifies a particular instance of that metric. In this case, the value of 12.66 represents the number of seconds that the first CPU in the localhost:9100 instance of the node job spent in IO wait mode. Even though it's not directly relevant to our monitoring examples, on a Unix-based system, IO wait represents the time spent by a CPU waiting for an IO operation to complete, like a write to disk. There are a lot of modes in which a CPU can spend its time, and in a multi-CPU system, this can trigger a large list of combinations. Luckily, Prometheus also provides a robust query language to do things like perform the aggregation functions we dove into in earlier videos. The query language details are Prometheus specific, and we won't look at them too deeply. But if we wanted to get the total time all CPUs spent in IO wait mode, we could write something like this and execute it in the expression browser to condense that information into a single number. Again, this example is Prometheus specific, but most monitoring systems will provide some kind of language or method to query the metric data that has been collected, which can help to extract meaning from those statistics. For a full rundown of the query language and syntax Prometheus offers, you can check out the documentation in the next reading. Wow, we've seen and done a lot. We fired up the Node Exporter application, which began collecting host-level operating system and hardware metrics, and started exporting them at the /metrics endpoint. We also started the Prometheus server with a configuration file which indicated where the target endpoints to scrape were located. We then used the Prometheus expression browser to query the values of the host-level metrics using the Prometheus query language. That's not all, though. We've also seen how to access metric data through the expression browser. This can be useful for conducting an investigation or debugging a problem, but it would be really helpful if we could visualize the data in a graph. Let's do this by answering a question. How much memory is currently in use on our node? We can find this out using the memory metrics collected by the Node Exporter, specifically these. On Linux systems, these values reflect the state of the different kinds of memory available on a computer. You can find a full description of them in the next supplemental reading, but for now, it's enough to know that by subtracting the values of memfree, buffers, and cached from memtotal, we can get an estimate of the current memory usage on the system. As expressed by the Prometheus query language, calculating used memory might look like this. If you click the graph button next to console, Prometheus will convert this expression into a graph of the memory usage over time. Just like the console feature we saw in the last video, this built-in graphing ability is useful when doing ad hoc analysis, but it's short-lived. Remember that it's a good idea to create pre-built graphs of data that's likely to be useful and organize them into dashboards for analysis. Prometheus does provide support for creating dashboards and consoles natively using a custom templating language. You can find example consoles at the /consoles index.html.example on a running Prometheus server. The pre-built dashboard for the Node Exporter looks like this. The templates used to create these dashboards are powerful and can be versioned in a source control system like Git for excellent management. But full disclosure, it can be kind of difficult to learn at first. While this is a built-in console system, Prometheus can also export its metric data to other tools, like the Grafana application. Grafana can read the metrics that Prometheus collects and display them in customizable graphs and dashboards. The full details for installing Grafana and getting it up and running with Prometheus can be found in the next reading. But a Grafana dashboard for our CPU, memory, and disk I/O statistics might look something like this. Check out the metadata associated with the dashboard, including access labels, titles, and descriptions. See how Grafana contains a small web server so you can use your favorite browser to display the graphs and dashboards you create? In a production system, you might have the Grafana program installed alongside the Prometheus server on the same node, which makes it easily accessible by other members of the IT team. Our monitoring system is really shaping up. We're collecting the data, querying the statistics, and graphing the metrics. But if we don't want to be chained to our computers, constantly staring at dashboards trying to spot problems, we'll need some alerts. Let's get writing. In Prometheus, alerting is handled by a separate component called the Alert Manager. alerting is broken into a few steps. First, the Prometheus server reads the alerting rules you write and evaluates them, sending the alerts that trigger to the alert manager. Alert manager then handles things like grouping similar alerts together, silencing them if the human respondent decides they're not relevant, and sending notifications to the alert destinations like pagers, email addresses, and ticketing systems. To kick things off, we should specify some alert rules for the conditions we'd like to be notified about. We do this by creating a .rules file, which we'll call alert.rules in this example. Let's create an alert to notify us if our file system usage is getting full, which might look something like this. The alerting expression computes the ratio of used root file system bytes to total file system bytes, then multiplies it by 100 to produce a percentage. Then it's checked against a threshold value. Remember that alerting at 10% utilization isn't always a good threshold. But here, we'd like to set it low enough to generate an alert so we can see Alert Manager in action. Since the current usage is around 15%, this 10% should do the trick. We've also added some useful information into the annotations portion of the alert to provide some context and assist the human responder with investigations. With the alert defined in our alert.rules file, we need to tell the Prometheus server about it so that the rules get picked up. To do this, we first need to modify the prometheus.yaml configuration file we made earlier to include a pointer to alert.rules. Then we reload the Prometheus server by stopping and restarting it. If we go back to the Prometheus web UI and click over to the alerts section, we can see that our brand new alert is working and firing. Pretty sweet. So, we've got a firing alert, but we should probably get Prometheus to tell someone about it and not just keep it all to itself. This is where the Alert Manager comes into play. The Alert Manager can be installed in all the ways mentioned in the Prometheus Basics video, and a link to the source code can be found in the next reading. Just like we configured Prometheus with the YAML file, Alert Manager needs a similar file to guide its behavior. We'll create a file called alertmanager.yaml and set its contents like this. Routes indicate the paths alerts should take based on some criteria. So, if one IT team is responsible for web applications and another for database servers, you could route alerts about each service to the appropriate team. Alerts are grouped together by their alert name. So if multiple alerts are sent with the same name, only one alert is actually routed to a receiver. Receivers are the notification mechanisms that should get the alert. Types of receivers include email, as you can see, PagerDuty, Slack, and others. The receiver has the recipient and authentication information for the notification mechanism. In this case, the login credentials for a Gmail account. You can also see an HTML option specified in the config with a template value provided to it. You can set up alert templates to customize the look and information sent to alert recipients, kind of like how you can modify Prometheus dashboard templates. Next up, we should start up our Alert Manager and point it at its brand new configuration file. You can see on standard out that it's up and running, listening on port 9093. We're getting close to having alerts all set up and configured. Great job. The last step is to tell Prometheus about where Alert Manager is running now that it's been installed and configured. This means we need to restart the Prometheus server, adding another command line flag that tells it where Alert Manager lives. Let's check the Alert Manager endpoint on port 9093. If all went well, we should see that there's an alert firing along with the details of the notification. Yep, there it is. But the real test is whether or not we've received an email message from Alert Manager. If we log into Gmail, we should see a message like this. And with that, we've just received our very first alert. Nerd alert, we nailed it. We've learned how to set up monitoring and alerting for host-level metrics that track operating system statistics. Now we can shift our focus to the application level and some black box monitoring using the black box exporter prober. First, we'll need something to probe. We can use Ruby to create a simple web server that serves some text when it receives an HTTP request. This script, called server.rb, will do the trick. This server uses the Ruby socket library to listen on port 2345 of your local machine and serve responses. The details of the script aren't important here, so don't worry if you don't fully understand them. For now, it's enough to know that when you visit localhost:2345 in your browser, the script will respond with a message like this. We'll want our prober to follow the same kind of workflow. Make a request for localhost:2345 and make sure that a successful response was generated. We'll start up our small server and it'll happily sit and listen for requests. Like the Prometheus server, Node Exporter, and Alert Manager, the black box exporter can be installed in a variety of methods, listed in the README file of its source code page, which you'll find in the next reading. Also like those programs, it's configured using a YAML file, which we'll call blackbox.yaml. The configuration is pretty straightforward. We specify a probing module called HTTP_2XX, which will use the HTTP protocol to make HTTP GET requests to localhost 2345, where our Ruby web server lives. If a 200 class response code is returned, indicating a successful HTTP response, the probe passes and we know everything is working. If not, something has gone wrong. It's worth calling out that in our example, we'll be issuing probes from the black box exporter running on the same computer as our web server program. But in a real production system, you want to send probes from a different node. This remote probing is better at simulating requests coming from external users and will give you a more accurate signal of the health of your service. Probes that must travel across the network and exercise the full request path to reach their destination will paint a better picture of the system as a whole, as opposed to just sending messages to the same computer they're running on. We can start the black box exporter like this. Now, we'll need to tell the Prometheus server about the exporter in order for it to scrape the probe metrics. We do this by doing a small modification to the scrape config section of the Prometheus YAML file, like this. As you can see, we've added another job_name called blackbox, which contains the HTTP_2XX module we created in the blackbox.yaml config, and the target that the prober will be sending requests to. We've also added a section called relabel configs, which is used to rewrite the label set of a target before it gets scraped. In this case, we're rewriting the labels to pass the blackbox exporter the target as a parameter. You can see this if you check out the targets page in the Prometheus server GUI. There, you'll see the blackbox prober and its target, along with the node exporter we set up earlier. Finally, we can reload the Prometheus server and check out the graphs. The main metric of interest to us here will be probe success. A value of 1 indicates success. 0 indicates failure. Graphing this metric, we can see the requests to our little Ruby HTTP server have been doing just fine. So, what happens if we were to stop our HTTP server with the prober still running? Let's send it a sig-hup signal to crash it and see what happens to the graph. Aha! The prober is still trying to send requests to the little server, but isn't getting a response anymore, which means the probes are failing. If we were to launch the server again, we'd see the probes begin to succeed once more. From here, the next steps for configuring the blackbox prober are to add some alerts so you know when the server goes down. This could be done the same way we added the file system capacity alerts, by extending the alert.rules file to check if the probe status metric indicated a failure for a given length of time. Pro tip: it's usually better to fire an alert only after a certain number of probes have failed. This is because network blips and other transient issues might cause a few probes to fail from time to time, but not indicate an actual underlying problem. If you've reached this point, give yourself a high five for making it so far. Not only have you learned some of the underlying principles and concepts of monitoring and alerting, you've seen the nitty-gritty of how to set up and configure a monitoring platform with dashboards, alert rules, and probers. The increased observability provided by a centralized monitoring system can help in pretty much every aspect of managing IT infrastructure, especially when it comes to scalability and reliability. Using a monitoring platform means that you don't need to log into each machine on your network to collect disk usage and information. And you can be immediately notified of problems through alerts so you can fix them faster. You might also be starting to think about how monitoring can be paired with other tools we've already put in your IT toolbox. The synergy between storing alerting configurations in VCSs is high, and so is using a configuration management tool like Chef to automatically deploy monitoring like the node exporter to each node in your infrastructure. Having good monitoring will also come in handy for our next course, which takes a deep dive into IT security. After all, how can you know your system is really secure without good visibility into its operations? You'll also learn how good logging can help in post-hoc forensic analysis after a security incident, and how you might be able to prevent it from happening again. Very cool stuff is ahead, but now it's time to put what you've learned to the test. We'll finish off this module with a few quick labs exercises, which should help drive home the techniques and tools we've been covering in the last few lessons.